चालू है। हम्म? हाँ। Good morning, ladies and gentlemen. On behalf of organizing committee, I, Rakesh Kumar Nathwani, welcome you to the inaugural function of one-day theme meeting on operational experiences of particle accelerators in India, organized by RRCAT and supported by Indian Society for Particle Accelerator, ISPA. This is the first of its kind meeting in India on operational aspects of particle accelerator. As we know, particle accelerators are complex machines having combination of various advanced technologies. Hence, their operation is equally challenging, especially for big facilities which are operating in round-the-clock mode. On international forum, workshops on accelerator operations are held every 2 years at various accelerator laboratories around the world. With increasing number of operational particle accelerators in India in the field of research, medical, and industrial application, it is prudent to have a theme meeting like this, which will serve as a good platform to exchange ideas and experiences among experts from various operating particle accelerators in India. I am pleased to inform you that the chief guest of today's function, Sri T.A. Puntambekar, outstanding scientist and additional director RRCAT, has arrived. We are also honored by the presence of our ex-senior colleagues, Shri P. Srivastava, Shri Mahendra Lad, Shri Pramod Bhagwat, and Shri Govind Parchani on this occasion, who have immensely contributed in the accelerator program at RRCAT. With due respect, I invite Shri T. Puntambekar, sir, to the dais. I request Shri Viraj Bhange, Chairman Organizing Committee, Shri R.K. Sahu, Convener of the theme meeting, and Shri Vijendra Prasad, President ISPA, to join him on the dais. Thank you, sir. I now request Shri Viraj Bhange to welcome Shri T.A. Puntambekar with a plant sapling. I request Ms. Shreya, who has recently joined the Indus operation team, to bring the sapling. Please give a big round of applause. Thank you, sir. I now request Shri R.K. Sahu to welcome Shri Vijendra Prasad with a plant sapling. I request Ms. Silpa to bring the sapling. She is also recently joined the operation team. We shall We shall now begin our function by ceremonial lighting of the lamp and seeking blessings of Goddess of Knowledge and Wisdom, Ma Saraswati. I request our guests to come forward. I request Kumari Jyoti of Indus Operation Division to assist the guests. Thank you very much, sir. I now request Shri Viraj Bhange, Chairman of the Organizing Committee, to deliver the welcome address.
Good morning. Shri Tushar Pundamekarji, Additional Director, RRCAT, Director, Electron Accelerator Group. Shri Rajesh Sahu, Head Indus Operation Division and Convener of this theme meeting. Shri Vijayendra Prasad, President ISPA, and Nathwani ji, or Purushottam Srivastava ji, Lard ji, Jishnu Dwivedi ji, Bhagwat ji, and my dear colleagues. On behalf of organizing committee of this theme meeting, I extend warm welcome to all of you, all our distinguished guests, invited speakers, system experts, colleagues, and members of Indus operation team joining here us today. I welcome colleagues and participants who have joined online as well. This meeting brings together professionals who operate, maintain, and continuously improve accelerator facilities systems that are not only marvel of engineering, but also vital tools for fundamental research, material studies in medical science, drug development, industry, and many more. Today, we will be discussing the operational experience of these particle accelerators of various types. We will further discussing the challenges faced during the routine operation, troubleshooting, beam stability, and upgrades. These topics are often remain under discussed compared to design and construction of the accelerator. Most of the engineer and scientists will agree that challenges faced during the routine operations are very critical as well. We are hoping that this meeting will provide dedicated platform to share those valuable learnings, innovations, and insights that can shape better operational practices across the facilities. Today, we will hear from colleagues representing a diverse array of accelerator facilities who will share their real-world experiences. We are hoping this meeting will cover a wide array of topics in operation, training of manpower, safety protocols, maintenance of this complex machine, regularity aspects as well. I hope this gathering not only foster exchange of knowledge, but also encourage collaboration, spark new ideas, and inspire continual improvement across the accelerator community. Let me take this opportunity to thank Indian Society for Particle Accelerator and Director RRCAT for their support to organize this event. Thanks are due to organizing committee, technical team involved in webcast, support staff. Those efforts have made this meeting possible. Once again, I welcome you all. I wish you all productive, engaging, enjoyable meeting ahead. Thank you very much.
Thank you, sir. I now invite Shri R.K. Sahu, convener of this meet, to give a brief overview about the objectives and significance of this theme meet.
Sri Pundamekarji ji, Additional Director RRCAT and Chief Guest of today's function. I will say mentor and guide of our accelerator program also. Sri Viraj ji, Associate Director EAG and Chairman Organizing Committee. Sri Vijayendra Prasad, President ISPA and Head PLDD. Sri R.K. Nathwani, Head IOCTS IOD. Sri Viraj ji has told many things, so I will not repeat those. So we all agree that these accelerators are high-tech subsystems in terms of challenges and demanded accuracy. Demanded accuracy means demand is almost same as possible in best possible conditions in lab, and we want to achieve the same at site. This also gives rise to day-to-day variation and then makes the operation difficult, or it needs experience, which all Indus operation, those involved in Indus operation know very well. So I want to remember at this occasion that for this reason only, during commissioning also, every accelerator takes a long time. For example, we took 4-turn circulation in Indus touring in August 5, and the first synchronous light was seen on 1st December in the same year. Around 100 days it took to see the synchronous light at injection energy. Then successful operation of Indus 2 at 50 milliampere and 2.5 GeV. That is designed energy, but current is 50 milliampere, was done in July 2008. So with this, it was considered a case of operation of machine as per SOP. Means a commissioning phase was over, and it was considered that now a proper training qualification and licensing program should be initiated, and it was taken up. So first round the clock operation by trained and qualified personnel took place from April 2010. So on this aspect, various operational aspect and training and qualification, Nathwani ji will cover. On this also says, means accelerator facilities which are in the beginning stage, they will also share about something about their commissioning phases. We would like to hear from Mr. Rao. And and now with this round the clock operation with trained manpower has been about 15 years with in Indus operation. And during this period, various upgradations are also done. So this gives a confidence that such machines can be opened and then again restarted with all upgradation at the same operating parameters. And then we started paying attention to streamlining the operation procedure like any plant. And in 2018, when our training qualification and licensing program was properly matured, we put the case to qualification incentive scheme of DAE. And from say May 2021, DAE approved qualification incentive scheme for synchrotron radiation facilities also. So before this was other facilities like nuclear power plant, various reprocessing facilities, but synchrotron facilities were not in that list of various facilities. So, Sri Nathwani will also cover about our various stages through which we achieved qualification incentive scheme applied to and implemented at Indus facility. I'm grateful to Dr. Raju Mehta, who came from IUAC. He will tell more about this educational purpose and accelerator for knowledge at IUC. Dr. K.K. Pant, who will be speaking on IR-FEL facility of RRCAT, which is around a year back was opened for users from outside also. Then on various ion accelerators at VECC, Dr. Arup Bandyopadhyay will be presenting his talk online. Dr. SVLS Rao, IITD BRC, will be speaking on LIFA. And as I said, that various parameters of the operating conditions, they vary on day-to-day basis, or they don't have that kind of repeatability because of very high accuracy demanded, which are possible only in the lab conditions. So whole accelerator machine becomes a lab. and repeatability, day-to-day changes are to be taken care. For that, Dr. Surendra Yadav will be speaking on use of AI to take care of that automatically, and it is like a support to the operation team. Then R.K. Agrawal will be speaking on various software supports over the years based on the experience they made to from our controls division they made for easing the Indus operation. And while I speak for Indus operation, it also applicable to all accelerators, because every accelerator, based on their own experience, devise their own method, and uh, as per their requirement, they find the software solution or in present day AI solutions. I also Sri R.I. Bhakt Singh from APPD. He will be arriving soon, and he will be talking about E-beam accelerators. Then Dr. Atanu Jha will be talking about ILU, Industry and Laser Laboratory Uses, EBA facilities. Then Sri Pankaj Kumar will be speaking about our ARPF facility for medical sterilization of medical devices. This is a next level of reliable operation by putting the facility in public domain, which has its own implications and requirement of various certifications, which are not applicable to or which are not must for a R&D facility. So with this, I hope team meeting will be felt highly useful. And based on the feedback and contacts made here among the with our speakers and among the participants, there will be a platform set for repeating the same conference in future like other accelerators. Thank you.
Thank you, sir, for giving a brief overview of the meet and details of the talks which will be delivered. Uh, as we know that the theme meeting is supported by ISPA. During last 1 year, the present executive committee of ISPA, headed by Shri Vijendra Prasad, has organized many theme meetings, workshops, etc. in the field of particle accelerator, including INPAC 2025 held recently. I now invite President of ISPA, Shri Vijendra Prasad, to address the audience.
Thank you, Rakesh. Good morning. Sri Tushar Puntambekar ji, Additional Director RR CAT and Director Electron Accelerator Group. Sri Viraj Bhange ji, Sri R.K. Sahu ji, Sri R.K. Nathwani ji, my ex-Director Proton Accelerator Groups, Sri Purushottam Srivastava ji, Sri Mehan Lad ji, and distinguished guest, especially Dr. Rajiv Mehta, who has traveled and who happily accepted to present his talk in this theme meeting, Dr. S.L.S. Rao and other colleagues, dear SCR members and DSC members. So, and welcome to all of you. As a president of Indian Society Particle Accelerator, it gives me immense pleasure to welcome you to the inaugural session of this one-day theme meeting on operational experience of particle accelerators in India. In India, the particle accelerator technology is now well established, and a lot of accelerators are in operation for the different societal uses as well as fundamental research. We in RRCAT itself, we are having different types of accelerators like this synchrotron radiation sources, Indus 1 and Indus 2, those are operating in round the clock mode for not only the fundamental research, but also medical research. And then we are having this industrial accelerator for the agricultural and medical research and then societal uses. We are having this pre-electron laser again for this fundamental research, and then it may be used in future some other type of research also. So this accelerator, as Nathwani told in the beginning, that on the accelerator operation, there are multiple workshops, alternate 2 years all over around the world, and there are international workshops. But from the Indian, rarely we get opportunity to attend this type of workshop. So organizing this type of workshop or theme meeting in India was felt from a long time. And we got this opportunity. This organizing committee and Sri Tushar Puntambekar ji, Sri Sahu ji, Nathwani ji, they started that we should have this theme meeting on operational experience of the accelerators in India, so that a larger public, means larger these persons who are involved in the operation get benefited. So ISPA readily agreed, well, this is as a part of this Indian Society for Particle Accelerators should support this type of theme meeting also. And we are sure that in future also we will be supporting this type of theme meeting. Recently, we successfully organized the Indian Particle Accelerator Conference, but in that, most of the things were related to the technology and then science behind the accelerators, but the operational part was the missing. So this part, this theme meeting will add additionally to the accelerator community for the benefit. So this operation of the accelerator is now, it's not a, means for the accelerator, it's a highly challenging task. And then operational people, the persons who are involved in the operation, they face lot of challenges related to the beam stability, beam availability to the users, machine protection, radiation safety, control, diagnostic, safety regulations, and then as well as this workforce, the training to the operators, upcoming operation staff who are involved, who are going to involve in the operation. So there are a lot of challenges in operation. Besides the science and technology of accelerator, the operating the accelerator so that it can give the result as decided. So this theme meeting will provide a good platform with good opportunity to learn all the peoples, all those who are attending, and they will go, they will know the intricacies of accelerator operation at various places besides this, what is being used in Indus One, in this Indus operation and then at RRCAT. So let me extend heartfelt thanks to the organizing committee for organizing this theme meeting, all lecturers and participants. I look forward to impactful meeting. Thank you. Thank you all.
Thank you, Vijay Prasad ji. The chief guest of today's function, Shri T.A. Puntambekar, Additional Director RRCAT, is very well known to all of us at RRCAT and to particle accelerator community elsewhere in DAE. He has devoted his entire career in installation, commissioning and upgradation of Indus facility and its successful round-the-clock operation as a national facility. He led the team which developed and commissioned beam diagnostic devices for Indus accelerators. In 2015, he was made head of Indus operations and later on took charge as Director Electron Accelerator Group in the year 2020. As we know that running a round-the-clock facility in a R&D setup has its own challenges, which he has met with skill and dedication. Under his visionary leadership, the operational performance of Indus facility has continued to scale new heights. With these few words, I respectfully invite Sri T.A. Puntambekar to deliver the inaugural address.
Thank you for the kind introduction. Shri Viraj Bhangre, Additional Director EAG and Chairman of the Organizing Committee. Shri R.K. Sahu, Head IOD and Convener of the theme meeting. Shri Vijay Prasad, President ISPA. Shri R.K. Nathwani, Head IOCTS, IOD, DAC, SCR and SCR members, senior officers of RRCAT, our ex-senior colleagues present here, Shri Purushottam Srivastav, Shri Lad, Shri Parchani, Dr. Bhagwat, then our invited speakers who are present, Dr. Rajiv Mehta, Dr. Rao, and those who will be joining later. All the invited guests, distinguished invited speakers and participants of this one-day theme meeting on operational experience of particle accelerators in India. This is held under the aegis of ISPA. A warm welcome and a very good morning to all of you. As we know, the use of particle accelerators is increasing day by day in various walks of life, such as industry, medicine, agriculture, food processing, etc., apart from the research in material science, radiation physics, chemistry, biology, and such fields. The field of particle accelerators has experienced significant growth in India. There are particle accelerators operating in various units of DAE, such as the RRCAT, BRC, TIFR, VCC, TMC, and other R&D and academic institutes such as IUSC, Samir, and some universities in India. Many of these accelerators are operated on regular basis as user facilities for research community or industrial applications or medical applications. And all these accelerators, there are a variety of types, such as electron accelerators like synchrotron radiation source, then electron linacs, proton linear accelerators, heavy ion accelerators, cyclotrons, and so on. As you may be aware, accelerators at RRCAT, which are in regular operation, are Indus 1 and Indus 2 synchrotron radiation sources, electron beam-based irradiation facility for medical device sterilization at ARPF, and recently we added IRFEL, infrared-free electron laser, as the regularly operating facility for users. Just give a brief about, although you may be knowing, just for the sake of completion, I will just mention some features of these accelerators. So Indus 1, which is 450 MeV 125 milliamp per machine, and Indus 2, which is 2.5 GeV 200 milliamp per machine. These are the only two synchrotron radiation sources which are operated in round-the-clock mode as national facility in India since 2010, already mentioned by Shri Sahuji. The user base of Indus facility includes 140 plus R&D institutes, R&D and academic institutes, and 20 plus industries on regular basis. More than 1,000 user experiments are performed annually on Indus beam lines, resulting in about more than 200 peer-reviewed journal publications every year. Already informed by Sahuji, a comprehensive training program, which is we call as training, qualification, and licensing program, that is in short TQLP, is conducted to train the Indus operation crew, leading to their licensing at various levels. At present, 6th batch of TQLP is underway, and this batch consists of our newly joined colleagues in IOD who will be operating the Indus machine in future. So I take this opportunity also to welcome this newly joined our colleagues to this theme meeting. Indus facility is also included under the qualification incentive scheme of DAE QIS, as already informed by Shri Sahuji. Then RRCAT is also developed electron beam radiation processing facility ARPF based on indigenous 9.5 MeV 6 kilowatt electron linac. ARPF started providing commercial electron beam sterilization services for medical devices in October 2022 with license from FDA. The facility is being used by Indian medical device industries. Process quality and integrity is ensured through continuous monitoring of critical process parameters. Recently, ARPF attained a significant milestone of having completed electron beam sterilization of 1 crore medical devices. The E-beam facility is being operated under the quality management system, complying with the requirements of medical device rules, MDR 2017, ISO 9001, ISO 13485, and is providing e-beam sterilization services in conformance with ISO 11137. RRCAT has an operational IR infrared free electron facility providing radiation in the range of 12.5 to 50 micron, acting as a complementary radiation source to our Indus facility. And recently it has also been made open to the external users to carry out their experiments. So more details about these facilities will be covered by the respective experts during their talk in today's theme meeting. As you know, particle accelerators are complex machines involving technologies in multiple domains, such as accelerator physics, UHV, RF, magnets, power supplies, control system, beam diagnostics, precision alignment, accelerator safety systems, and also systems and operate procedures for meeting regulatory requirements, etc. The parameter requirements of each of these systems is very stringent. After building these accelerators, operation of this complex machine is also equally challenging. Further, if the facility is run as user facility in round-the-clock mode or as national facility, then there are additional requirements coming into picture. Efficient and reliable operation of the accelerator with high uptime requires concerted efforts on many aspects, such as system reliability, managing breakdown maintenance promptly in shortest possible time, operator training, planned maintenance schedules, and executing upgradation plans with minimum effect on the machine availability to the users. In this context, this theme meeting will provide an excellent opportunity for the experts engaged in accelerator operation to discuss and share operational experiences of different types of particle accelerator facilities across India. I also take this opportunity to thank the outstation invited speakers and participants who have traveled all the way to RRCAT to attend the theme meeting. At the end, I again wish the theme meeting a great success. Thank you. Jai Hind.
Thank you very much, sir, for your address briefing about the accelerator facilities of RRCAT and its achievements, and for your inspiring words and encouragement. Moving ahead, I request Sri Viraj Bhange to present a memento from the organizing committee to Sri T.A. Puntambekar as a token of our love and respect. I request Kumari Jyoti Sahu to bring the memento. Thank you, sir. As we come to the end of today's function, it is an honor and a great pleasure for me to propose the vote of thanks on behalf of organizers of this theme meeting. First and foremost, we express our sincere gratitude to our chief guest, Shri T.A. Puntambekar, outstanding scientist and additional director RRCAT, for graciously accepting our invitation and taking time from his busy schedule to be with us. Sir, your presence has deeply inspired and encouraged us. We are also profoundly thankful to Shri Unmesh D. Malse, distinguished scientist and director RRCAT, for his unwavering guidance and support. His leadership has been a constant source of motivation for all of us. We would like to express our greatest thanks to Sri Viraj Bhange, Chairman, Sri R.K. Sahu, Convener, and Sri B.B. Srivastava, Secretary of the Organizing Committee. Their tireless efforts and meticulous planning has been instrumental in making this meeting a grand success, bringing together various experts from the field of accelerator operation for a fruitful interaction. We are grateful to ISPA President Sri Vijendra Prasad, General Secretary Dr. Vikas Jain, and Treasurer Sri Anil Holikatti for their generous support in making this event possible. Our sincere thanks are due to all the invited speakers, delegates from RRCAT and from other R&D units, including BRC, VECC, IUSC, New Delhi, and Tata Memorial Center, for accepting our invitation and for making this theme meeting a great success and truly impactful. We also extend our warm appreciation to our senior ex-colleagues for their gracious presence in this function. We acknowledge with gratitude the presence of members of Director Advisory Committee, Scientific Committee of RRCAT, and other officials in this function. Our sincere appreciation goes to the members of the organizing committee, all subcommittees, and volunteers. Your dedication and behind-the-scene efforts have helped in smooth execution of this event. We also thank our colleague from Director's Office, Construction and Services Division, Administration, Accounts, Horticulture Cell, Audiovisual Cell, RRCAT Security, and CISF for their crucial contribution in ensuring seamless arrangements for this meeting. Finally, I request everyone to rise for the national anthem. I now invite Kumari Jhansi Rani, Kumari Jyoti, Kumari Shreya, and Kumari Shilpa to the podium to lead us in the national anthem.
जनगण मन अधिनायक जय हे भारती भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तभी शुभ नामे जागे तभी शुभ आशीष मांगे गाए तभी जय गाथा जनगण मंगलदायक जय हे भारती भाग्य विधाता जय हे जय हे जय हे जय 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 हे जय.
Thank you. I now invite everyone for high tea upstairs in this auditorium. After high tea, we will meet again here itself at 10:45 for the technical session. Photo. तो लिया है
लोग आ गया पाव भेज दिया था अरे इधर लगा लो कल भेज दिया था मैंने
वो सर करेंगे ना उधर से नहीं उनसे वो
स्क्रीन शेयर करना पड़ेगा
यहाँ वो आता है वो सर को करना पड़ेगा
सर बोले
हाँ
अर्पित सर 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 तो बोल रहे क्या सर अर्पित सर को दे दो सर सर इस पीसी को बना दीजिए प्रेजेंटर
इस प्रेजेंटर स्टेज
इसको
स्टेज भी बना दी नहीं शेयर नहीं स्टेज बनाना है ना मेक ए स्टेज
ठीक है बस से प्रेजेंटर जी किस फोल्डर में डाल रखा है तो आपके पास सबके आ गए हो
अभी के तो आ गए हैं, लंच के बाद वालों के ये आगे बैठना इसी में ही है। ब्रेक्स ब्रेक्स एट द एंड विल बी बैक एट 10:40 बोलेगा 45 तक है।
Hello. Check. Hello. Check. Hello. Check. 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 Hello. 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 जय हनुमान ज्ञान गुण सागर, जय कपीस तुहे लोक जागर। रामदूत अतिलित बल धामा, अंजनी पुत्र पवन सुत नामा। और कोई दिल है ईमान। चिक चिक चिक। हेलो। जय हनुमान ज्ञान गुण सागर। अरे दो जने गए, वो आ जाए फिर मैं जाता हूँ। हेलो चिक चिक।
Namaskar. Welcome to the first technical session of this theme meeting on operational experience of particle accelerators in India. In this technical session, we will have 5 talks from the invited speakers. Now it's my pleasure to invite T.A. Pundapekar sir as the session chair for the first session. It's my pleasure to read a brief introduction of Shri T.A. Pundapekar ji. Pundapekar ji has done BE Electronics from prestigious GSITS Indore in the year 1986. After that, he joined BRC Training School in the 31st batch. He joined RRCAT in 1988, and during more than 36 years of remarkable service in this institute, he has played an important role in the commissioning of particle accelerators Indus 1, Indus 2, and their upgradation. He has played a key role in the design, development, installation of various beam diagnostics devices in Indus 1, Indus 2, and Linux. His major achievements includes he has received Homi Baba Award for being the overall topper in the 31st batch of BRC Training School. He is recipient of DAE Scientific and Technical Excellence Award, and he has won several DAE Group Achievement Awards. He has more than 90 publications in journals, conference, and as a co-author and author. He is a life member of ISPA, INS, and ISRP. Presently, he is Additional Director RRCAT and Director Electron Accelerator Group RRCAT. Sir, I request you to kindly conduct the session.
Thank you, Amit, for the introduction. So, in this technical session, the first talk is by Dr. Rajiv Mehta. He will be speaking on accelerators for knowledge at IUAC, operational experience and challenges. I will just briefly read out his biodata and achievements. So he is MSc in Physics and BSc Physics Honors. His areas of research work are accelerator science and associated technology, design, fabrication, and testing of accelerator components, including cavities, charged particle optics. He has more than 50 conference, international and national journal publications, and he has a number of achievements and awards which are listed here. So with this introduction, I invite Dr. Mehta to present his talk.
Thanks for giving this opportunity to IUC. This maybe it will be better because I can move. You'll be playing?
No, sorry, can use this.
Okay, I'll do that. Fine. Then I can say. Thank you. Thank you. Hope I'm audible now. First, I would like to extend our gratitude that you have invited to represent IUAC. And we have many particle accelerator. I'll just go through this. But before I start, I would also like to pay my condolences to all the people who have lost their life in the horrific accident yesterday. So that's very sad, but I mean, we can only say that we are with the family at this moment of grief with them. Okay. So IUAC, I mean, our motto is accelerators for knowledge, and we provide our accelerator facilities outside DAE Institute, which cater to only to universities and research institute. I would like to just focus one point here, which I have been flashing in almost all my talks. This is one vision document which very specifically set the roadmap for the particle accelerators in India. And I think it is highly doable thanks to Dr. Purushottam Srivastava sir under his editorial guidance. There were many, and why I'm flashing this is honor for me because one of the project which is mentioned in this is the project which I am leading right now, the high current injector. So this has been a tremendous, I think, roadmap. And very much doable. I think that whatever has been descriptive there is possible to achieve with this. Like IUAC is, it's a multidisciplinary research institute which provide 24/7, 24/7, 365 days per accelerators facilities to the users. And we have almost all particle accelerator, vision is there. I'm not going through because I would like to complete in 20 minutes. And our mission is, this is the quest of innovation and capacity building in the area of accelerator-driven research. IUAC is India's premier laboratory for university researcher. That's one thing. And what is our top priority is carry out the experiment successfully to provide support and technology development and basic research beside capacity building. And our objective is, because why I'm highlighting this, this has a very much impact on the operational aspect of the accelerators. Because we are providing world-class accelerator system or like experimental facility 24/7. Anybody from institute comes. And so in first of my few slides, I will only go through to highlight the activities of IUAC which are critical in a sense that unless the operational and maintenance are not carried out properly, it can lead to a lot of failures. I mean, this is once I'm very proud to say, thanks to Professor Mehta, we started in modest, like this kind of a land in 1986 and 1989. Within 3 years of time, we could come up to the one of the best accelerator facilities. So that was achievement. Thanks to Professor Patro, our founder director, and Professor G.K. Mehta for this. And I joined around this time. I joined in April 89. This is one aspect that one should know, that IUAC is different from all other DAE organizations. We have so far 700 research groups associated with her, 160 university, 86 colleges, 107 other institutes, includes NIT, IITs, etc. Or more than 1,200 PhDs has been done using our facilities and 400 postdocs. This is the map that footprint the IUAC has over the India. And we have a worldwide also. I'm only talking about the Indian context in this. We started with a modest accelerator like 15 UD Peloton. This is still one of our major workhorse. Without this, I mean, our accelerator facility is not complete. This is one of the strongest point of IUAC. It's the oldest accelerator running in IUAC. Then we went, because as and when user wanted, and as I said that we were innovation in accelerator, capacity building. So we went to a superconducting niobium-based quarter wave resonators, the first in India SRF activities. And we have a complete accelerator facility starting from fabrication, surface preparation, testing, and other thing. Then we have other accelerators. So we have now 7 working accelerators, which we have to maintain and operate round the clock. So this is one, and with the limited staff of, total staff at IUAC is around 150. That includes administration also. Technical staff is around 75 to 800. Then we have, this is the Peloton accelerator, goes into the beam hall 1, where we have a major accelerator facility, heavy and nuclear physics, material science. This is HERA. HERA, as you know, is a diamond. It's our diamond facility at that time. And then we have a material science. Then there's the superconducting LINAC, goes to the different beam line here. National Area of Neutron Detector. Then we have a normal conducting high current injector, which is the longest accelerator at IUAC, which is 40-meter long. It has been commissioned and some testing has been done, which I'll report. So we have a large number of support facilities that need to be maintained and upgraded time to time to keep our facility working. Just to emphasize that only this particular line had more than 350 components installed into this. So that's one thing, that so many vacuum pumps, gauges, etc. are there, which we need to maintain. User perspective is very important to tell you that every year, twice in a year, we call for proposal where people from universities give their proposals, submit their proposal to utilize the beam time. So typically we get around 300 to 400 proposals every year. And these are our footprint. Pan India, you can see almost everywhere we have our user facility. We also provide funds to the universities and other people where they require funds. So these are the fund distribution in 2024, that what we have distributed to various areas. And you can see the map. I mean, it's throughout India. It's not related to a particular one position. Of course, this could be peaked at Delhi or Uttar Pradesh or somewhere, but it's distributed all over. This is one slide which I need to mention very critically. This is have the impact on the maintenance and operational aspect. This is from 1991 to 2019, we are spending almost 3.3 lakh rupees per 8 hours of operations in kind. We don't charge any university people anything, but if you take the cost of this, so any failure, even for 1 hour, can result in a huge financial losses to the center. So this is one important aspect that we have to maintain our accelerator facility. For this, we have devised a technical calendar. Every year we come out with this, which lists everything, and this is available on the website. Due to the size, I'm not able to read, but it has everything, whether it's a vacuum maintenance, water system maintenance, infrastructure, accelerator maintenance, everything is included in this, and every 3 months we review it, whether that has been done or not. So all the preventive maintenance and everything are listed into this, and we follow rigorously that whether this has been maintained or not. Apart from that, academic calendar. Here I would like to mention that we have a theme meeting in November, which is on the LINAC. So we will be inviting you people from this to have. This is one aspect of this, but this is a very important work which leads to a proper maintenance and our uptime of the accelerators. 15 UD Pelletron accelerator is the first accelerator, and I'm not going into much detail. This is how it looks from inside. I'm only talking about the upgrades and other things which we have done to ensure that minimum time is wasted during the user experiment and how we could achieve it. One of the major modification is resistance-based voltage gradient system that we have implemented. Initially, this system came up with a corona discharge system. So to maintain the voltage between the various units, you had a corona discharge. So this discharge takes place and the voltage stabilization takes place. This has a limitation in a sense that when we want to lower the potential, there was not enough potential between this corona to have a proper discharge, and this was not reading. So we had to short that unit by putting a shorting rod and then reduce the voltage. And this will lead to a loss of time. So what we did is, instead of that, we went with the voltage, the resistor-based voltage gradient system. And this has improved the stability in less than 2 kilovolt in 15 million volt. No shorting rod operation was required. Now you can see the limit from almost 3 megavolt to 15.3 megavolt. We don't require any shorting rod operation. Any shorting rod operation requires at least 1 day complete to make sure at least few hours, maybe 8 to 10 hours to make sure that it is done, because it is a risky job. In a high pressure SF6 environment, you have to insert the rods. There is a chances of SF6 leaks and everything. So to prevent that, we went with this, and this has been successfully working and saving time for the users. So this is one of the major achievements from the Pelletron. This is how it looks. This is a resistor chain. Then we also went with the conversion of a doublet units to single unit. Initially, when NEC supplied this accelerator, it was a doublet unit, and it has various electrodes. I mean, there are 74 electrodes which are defined in a various configuration, 2-unit configuration. And in this case also, we had a problem that whenever there is a stability problem or failure, we want to short something, then there is you have to completely short that unit. If there is suppose one particular unit has gone bad, if we want to isolate that, there is no other way other than that putting the shorting rod into that. So this particular configuration, by having a shorting in between, so we have converted a doublet unit, this was a double unit, into a singlet unit. And that also, because of this now, if this unit goes bad, this can simply be bypassed and everything will still work on that. So that has also improved our performance. So regular maintenance of its charging system, accelerating column, and regular unit-wise conditioning has improved the terminal voltage. That is the one aspect. 15 UD Pelletron accelerator also be used as an injector to superconducting LINAC. Uptime is almost 95%, while beam on target is around 60%. Here I would like to mention, since it is a user facility, we provide almost like 500 to 600 shifts. That means correspond to 4,500 hours of beam time to actual beam going into the target. So that is almost like a 51 to 55% of the time. Rest is a conditioning, another thing, beam changing, user support, another thing. But it is a very, and The chain operation is 95%. Here also I would like to mention, we have a preventive maintenance schedule that we operate, open it, see the system. One of the major impact of that, the NEC says that your charging chain, which supplies the voltage charges to the terminal, is 78,000 hours of operation. You need to replace it. It's because of its wear and tear. It's a constantly moving system. We have not replaced it since last 2 lakh hours. So from 78,000 hours to 2 lakh hours. It's a huge this, and this is only because of the preventive maintenance. And I must mention, the preventive maintenance is one of the critical things that we need to make sure, give a time. Like a stitch in a time, save 9, that kind of thing is what we are talking about. So we may think that we have lost 1 month in preventive maintenance, but it can result in a huge impact in the future. So that is very, very critical. Now I'm coming to another accelerator. And in this, I also would like to thank all the operators of the Pelletron and our accelerator facility. They are doing an excellent job to make sure that they are operated properly, they are tuned properly, beam is given to the user constantly without any break. LINAC, as we know, we have a quarter wave resonator. Initially, we developed with the Argonne National Lab. Then we have our in-house development. We have a 3 cryostat, 24 cavities, 8 cavities in each. And this is how it looks like: 4 cavities separated by superconducting solenoid, then another 4 cavities. In this also, we had a major issues, and how we solved it, I'll go one by one. So challenges in superconducting linear operation is, since our structure is little different. Normally, you'll see the devices the quarter wave resonators are tapered one. From the top, it starts with a higher diameter and goes down. In our case, it is a pendulum kind of thing. And because of that, we had a vibrational frequency of that pendulum, which was around 60 hertz. And that was creating a lot of problem. So you can see that if you have a Q of 10⁹, it is 0.1 hertz, and FW it is 50 hertz. And as a result, so because of this vibration, we required more RF power to control the phase and amplitude of and make it stable. The idea is this was an innovative idea. One of our colleague, Dr. Shubhendu Ghosh, he completed his PhD on this. We introduced stainless steel balls into this, and these are basically frictions. So when pendulum is moving, the balls are also moving and providing anti-friction to that. There is a detailed study. I'm not going into that, but we all know that power is proportional to the shake of whatever the delta F we have and stored energy. So the result is, without this stainless steel ball, if we want to operate 3 megavolt per meter, we required 50 watts of power. Whereas, now you can see that the red one is without the SS ball, and the blue one is with the stainless steel. So you have reduced the frequency jitter drastically. And with that help, we have reduced the power by 54%. We could operate 3 megavolt even at 23 watts of power. So this was one of the major things which resulted in system upgrade and operational aspect. And these are you can see these are the frequency which is completely gone here. So this is one upgrade that helped our operation of accelerator. Another one, it looks pretty simple, and we have lost a lot of time on this. It may appear very trivial, but I'm telling you, we had a huge problem with this. And this credit goes to Dr. Kanjilal, who suggested this implicate. We had a helium vessel filling to this, and there was a small opening, so liquid helium was going into this. When we were doing this, we were finding that we are not able to cool the system, and there were some hotspots generating, and we were not able to get the superconducting cavities. So we struggled a lot. We thought, then we introduced a tube inside. We thought maybe there is an air bubble which is there. So we introduced a tube here to here so that the air bubble goes out. We tried everything. Nothing worked. One fine day, Eureka moment, Dr. Kanjilal said, Raji, it's because of this. And he introduced this kind of setup, a kind of a dome structure, which has a buffer volume of liquid helium, and which solved our problem completely. So we didn't have any problem. So this is one of the simplest solution implemented, resulted in a major saving of our time and our issues that we were facing. Of course, we have a high pressure rinsing. We all know that it is, Peter Neisel was the first person to, I think, work on this. And we have this, and which is doing a good job for us. And Because of this, you can see that we have our improvement of the performance. So we make sure that whenever there is a cavity operation, it's a normal procedure. We do the high pressure rinsing and other thing, so that performance of the cavities have improved. The system is running round the clock. We operate our LINAC regularly every year. It is there in the calendar of event. And this time, last year, it was the longest period. Continuously for 6 months, we ran the beam time for the user. LINAC was operational for 6 months. And when we run the LINAC, the cost which I said 3 lakh goes to 10 lakh rupees per 8 hours because of the power, helium consumption, the thing. This is another thing we have introduced in Crystat 1. We have a slow tuner bellow, which is air actuated. So it is slow response time. We replaced it with the piezo connector, which solved our problem drastically. So this is one thing which has been implemented and working fine. Coming to high current injector, this is one project that IUAC is looking forward. As I said, this is one of the major project of IUAC, biggest accelerator as such in terms of this. And it has been commissioned, it has been installed. We did some tests, and during this test, we found that when the beam was passed to the LINAC, LINAC has 24 cavities. After 12 cavities, we found that acceleration is not possible because the main peak was getting shorter and shorter, and other energy peaks are appearing higher and higher. And that was mainly because acceptance of the LINAC was of the order of 100 keVs, in the order of your work. And we were providing almost like a 500, 800 keVs delta E. Because of that, the bunching in the LINAC entrance was only 800 picosecond instead of 150 picosecond. So there was a lot of other spurious peak which were coming, and that took over the main peak. But we could see exactly up to 12th cavity. We got a neon 7 plus beam, which went up to 77 MeV from 36 MeV, which was as per the design of the LINAC. So we could do that. To counter that, as I said, that what we have implemented now is we have introduced a double slit at the exit of one of the achromat band, which will be operated as a dispersive mode. We will cut down the beam. We got almost like 50 PNA of neon beam. And typically with LINAC, with Pelletron, neon is not possible with Pelletron, but otherwise we get hardly 0.1 PNA maximum. So with that 50 PNA, we could afford to cut down the beam by putting slits and coming to the required delta E of the Pelletron, which is acceptable to the LINAC. And we are now waiting for our liquid helium plant to be operational so that we can do the acceleration again. And I'm very hopeful that we should be able to do this acceleration. The only thing, now I'm going to highlight the important issue. Sir, 2 minutes?
5 minutes more.
5 minutes, okay. So what are the challenges that we are facing? And I need your, maybe, I mean, if you people can suggest something. We have a radio frequency quadrupole, and the major issue was when it was designed, we got, after fabrication everything we worked, we found 44 megahertz, which is 4 megahertz lower than the required frequency. To correct for this, though initially I think Sugam and Safwan, they tried that we could replace the whole this thing rather than working on the tuning plate to bring the frequency up. But it was decided maybe it is better idea to put the tuning plates. So when we went with the various tuning plates to increase the frequency from 44 to 48, but every time we had a burning issue, this was burning. This is the beryllium copper fingers, which is spring loaded. So when inserted into, because of the spring, it makes a contact, but unfortunately nothing helped. We went with a water cooling system. We thought maybe water cooling will help that. We introduced a water cooling. This also didn't help, but it introduced another issue, which I'm going to focus, which we are not able to solve so far. I really don't know the reason for that so far. Now, if you see, this is the fundamental frequency. Apart from that, we are getting some other frequency, which is 159 megahertz, which is nowhere subharmonic or nothing. And this is becoming so high that everything this is the reflected power. Everything reflected, and it is stripping the RF amplifier. We really don't know where this frequency is coming from. I have no idea. We tried all this thing. We went back to the original. We thought maybe the water fluctuations or vibrations are causing something. We removed this, went back to the original structure. Still didn't get anything. Still these peaks. So these peaks are becoming now common, irrespective whatever setup you go with. So I'm not sure what is the reason for this. We are working on it. So let's see if we should be able to. So this is one bottleneck which is restricting us to go to the highest power of 100 kilowatt or hour. This, we could only go up to 40 watts, 40 kilowatts. Beyond 40 kilowatts, we are not able to achieve, and hence we are operating at a higher charge rate. Instead of A by Q6, we are operating at A by Q, so that lower power we can get it's a constant velocity structure, so it doesn't matter. The whole HCI is a constant velocity structure. This is one. Now what we are thinking, going back to original, if you don't want to do anything, let's forget about all the tuning plates and everything, go back to original, and this is what we plan. We introduced a SS and copper plate in between so that we can increase the height of the copper plate without affecting the center of the beam line. Introduce this kind of a tuning so that without tuning plate, we should be able to go to 44, 48 megahertz. This is one of the options. For this, we are ready and we have worked on this. And also one of the reason you can see that this port is not aligned with the point where the power coupler should point. So we had a loop which was pretty long and awkward shape going into this, and which will go to copper plating, and this will be like this, and this is so. This will also be solved. Because of this also we are having a lot of issues. This is not a practical design of a copper. And of course, there are other maintenance work we keep on maintenance activities on iron source. And these are the beams that we have developed, and we are generating this beam, not using only one experiment. I can tell you that one experiment has been performed using high current injector beam in the beam hall 2 using LINAC as a drift, where 60 hours of continuous neon beam was given to the user, and we could found that system is stable and operational. Another important thing is this copper plating. And I think RRCAT has been very generous in the initial period. And of course, they have their own limitations, so they could not help us more. But I'll come to that. We tried to develop industry for this. And this is unfortunate that industries are not coming into this field. And you can see the kind of issue we had in this. This one, looks very fine after it came back copper plating. When we powered it, we found suddenly the Q dropped. We opened it and everything came out like a mold. The whole copper plating came out like a mold. We asked them, you do it properly. We gave you the sequence, but industry didn't support anyway. We went to RRCAT. I think in one of the impact, Avinash ji, Patambekar ji and Joshi ji were there. Avinash ji said, why don't you get it done here? And we went to Ram Shankar ji. I think he's retired. He did really help to us in getting this copper plating done. It worked very well. This is still in place. After that, our copper plating could not be got it done at RRCAT because of your own workload that you had. So we looked into another thing, and I found a very good place. It's a CSIR lab in Karaikudi near Madurai.
Dr. Mehta, please.
Yeah, just I'm final.
Please conclude.
Yes, sir. So this is the copper plating that will be done. Thank you. So these are the challenges that we have faced.
Thank you, Dr. Mehta, for bringing out various issues that you have faced during operation and how the solutions were applied, which has resulted in the improvement of the machines.
Yes.
Also highlighting the importance of the preventive maintenance schedules. I think your talk is perfectly aligned with the theme of our theme meeting. So I hope that your experiences will be definitely useful to other experts in the accelerator field. So with this, we can have some 1 or 2 questions.
Yes, sir.
It's heavily loaded. Means you have one pelletron. Yeah, and it is heavily loaded. Are you not thinking of having any redundant or another one?
Because this HCI is the one, na? HCI will make pelletron completely standalone. That is the whole idea. Not only that, HCI, I didn't go into that part because that was not topic of this thing. HCI will not only provide the beam what is possible from pelletron, apart from that metallic beam, noble gases and other thing also will be there. And some radioisotopes, which are short-lived.
No, this is just a comment. First
Yes.
of all, a very nice talk.
Thank you, sir.
See, Rajiv, this resistance grading help in voltage stability, no doubt about it. And operation at lower voltage for pelletron becomes quite easy.
Yes, sir.
Agreed. But shorting rod is still required because you would like to have a good transmission.
Yeah.
And if you don't use shorting rod, transmission is haywire.
Yeah, I
That is
agree
okay.
with you, sir. On this is a good comment. So
And
if you,
I think this is just a comment. You
yes,
don't
sir.
have to.
I agree with it.
I think once I had a long discussion with Amit, Dr. Amit Rai on how much money is required per shift. So you have said 3.28 lakh per shift.
Per 8 hours.
For 8 hours. This is including pelletron and
Yeah,
linac.
all the costs. This is for since 1991 to 2019. That is the 10-year period at that time. That includes manpower and everything.
Thank you.
Any other? Yeah. Srivastav.
Well, I would like to acknowledge the great work done by IUSC in the Mega Science Vision document as well as superconducting technology. Now, in one of your problem, you have shown that you had some spurious thing.
Yes, sir.
It might be due to intermodulation, passive intermodulation. So we can think about it. You can interact on this aspect. But mostly what happens in such structures when your high power is fed, despite of that your carrier is one, there are passive intermodulation products which are
So
generated.
this I'm talking about happening at 4 to 10 kilowatt of power. I'm not even talking.
Even then.
Even then.
Yeah,
Okay.
even then there are chances of having a passive because that may happen even at lower, like in communication systems, even at 100 watt or 200 watt.
How to identify that?
That we can interact on that and we can find out.
Sure.
So how to suppress that particular.
Sure, sir.
Yeah, thank you.
They'll be very useful, sir, because that is one issue we are really having a huge problem. And I also look forward for Vinny Jain, sir. I mean, maybe his experience also could be.
If there are no questions, let us thank
Thank you, sir.
Dr. Mehta again.
Thank you.
And it's my pleasure to present a moment on behalf of the organizers to Dr. Mehta. Next speaker is Dr. Kamal Kumar Pant. He's head of FEL and Utilization Section RRCAT. Yeah, his brief biodata is here. He holds a PhD in physics, MSc in physics. His areas of research work are design, development, and commissioning of IRFEL and the associated user facility, design and development of RF extracting structures for the FEL activity. And he has received Nuclear Physics Symposium Best Poster Award, and he has more than 60 conference and international national journal publications. I invite Dr. Pant to present his talk on IRFEL based user facility at RRCAT, present status and some operational experiences.
Thank you, Puddamigirji, for the introduction. And thanks to the organizing committee for giving us a chance to talk about the status of our facility and some operational experiences. I must say at the outset itself that the FEL is now in the very initial stages of being a user facility. So we are just started gaining experiences, but being not just an accelerator, but an accelerator which produces light in an oscillator configuration. Our troubles don't end with sorting out the accelerator issue, but actually start when we start giving power to the user. And I will bring out a couple of those experiences here, where when we feel that everything has been under control, we are getting good repeatability, we get user feedback that this is not as it was yesterday. And that is operational experience gives us vital inputs on what else we should be looking at. So briefly, I will talk about the current operation status. In the current operation status itself, I will talk about some operational experience, but as I said, this is the operational experience from the machine side. And then when we give the beam to the user, we realize that it is not really what we thought, how well it is working. And that leads us to rethinking on what else could be the issues with the machine. And I will bring out one specific point here. There are many such experiences. And as is also in the scope, the regulatory matters, because there's a large audience here. This is just to highlight that building an accelerator based facility, getting from starting to the license for operation can take up to 10 years, 10 to 12 years. So there has to be some effort, somebody following it, pursuing the things, and that involves multidisciplinary work, because you have to interact with all the expert teams involved to sort out all the issues that the regulators raise. And then I will give a brief summary based on our experience. Now, as Puntambikarji said in his talk, the IRFEL complements the Indus 1 and Indus 2. So if we see the energy scales of the photons coming out from this Indus synchrotron radiation sources, Indus 2 is in tens of kVs to a few EVs. Indus 1 is from keV to 100 millielectron volt, where the photon flux or the brightness comes to about 10 power 10. So if you want science with photons of energy lower than 100 millielectron volt, the brightness will go down here. It will go to 10 power 9, 10 power 10. And there's a lot of science at these low photon energies, where you want to excite vibrational states, molecular dynamics, other such areas. So that is where the FEL complements. This is 100 millielectron volt. The FEL gives you a jump in the brightness at photon energies which are now below the standard range of Indus 1. So from 25 to about 100 millielectron volt, we can give more than 10 power 12 brightness. And that is how it complements the Indus facility. Additionally, it also gives pulsed, short pulse photons, that is 10 picosecond photons. So it can also open up a regime for time domain studies or time resolved studies. So that is how it complements the Indus facilities. Now, this is the picture of the FEL. We have an injector system here, the optical cavity here, and there is a transport line to put the beam into the optical cavity. And as I said, this is an oscillator configuration. So about 80 round trips are needed for the lasing to build up. And that is where some of our operational experience comes in, because since 80 times, minimum 80 times, the electron beam has to interact with the electromagnetic radiation left behind by previous pulses. So there has to be perfect overlap between the subsequent electron bunch with the optical pulse left by the earlier pulse. And there the timing jitters of 1 to 2 picosecond is all we can tolerate. If there is a larger timing jitter than 2 to 3 picoseconds, then lasing is affected adversely. So that is why, as I said, just the accelerator is just the beginning of our problems once we solve the accelerator. But this is where we need to address the issues to be able to give lasing or good output to the user. So present status is summarized here. The design was 12.5 to 50 micron. We have demonstrated that design wavelength. We are routinely generating 20 milliwatt at 2 hertz. The machine was designed to deliver 30 milliwatt at 10 hertz. So by upgrading the injector linac, we are able to deliver 20 milliwatt at 2 hertz itself. For some experiments, users, if they need more power, then we can go up to 4 hertz, and with electron beam operating at higher duty cycle, we have obtained up to 80 milliwatts. I will show that in subsequent slides, which are a mix of the current status and our operational experience. So as I said, brightness, this is at 21.8 micron, and at two extremes, 12.5 and 50 micron, we can give more than 10 power 12. Then power stability, about 10% is regularly achieved. Now this is an electron beam based source, and as I said, we are operating in an oscillator configuration. So the electron gun specifications itself say 5% charge stability over an operation cycle. So any electron beam based light source further where you have an oscillator configuration, it cannot be as stable as conventional lasers. So we over shorter durations, we have achieved up to 5%, but typically better than 10% is regularly achieved. And high duty cycle operation is possible. And current status is we have license from AERB for regular operation as a user facility with external users. So some operational experience, as I said, for if there are users who want high average power, we have operated the machine by changing the duty cycle 1 Hz, 2 Hz, 3 Hz, 4 Hz and up to 80 milliwatts power, CW average power from the machine is possible. This is our standard tuning curve. So from 12.5 micron to 50 micron, we need 3 different beam energies. So that is an important thing, because if a user wants quick tuning, within each band, if a user wants some experiment, the tuning can be done in seconds. But the user itself needs about 10 minutes to find out what is the wavelength, because they cannot trust us. I mean, if we say this is a wavelength, for their experiment, they need to measure the wavelength. So the user, in-house user has developed a Michelson interferometer. So he himself, the user himself needs a few minutes to find out what is the wavelength. But from the machine side, it can be done in few seconds. But if you want to go from one wavelength, the band we have to the other, then we need to optimize the complete machine. And that is where we are doing repeated experiments with different beam energies such that we have an algorithm that one set of usage experiments are complete. Now somebody else wants another thing. We recall that band of parameters, operation parameters for the machine, and then deliver the lasing power. This is a typical experiment that we did recently, because one user wanted a specific wavelength range which were between 2 bands, but they said we want quick tuning and with greater than 20 microjoules per pulse, that is greater than 2 megawatt power at the user station. So for that, we had to optimize the machine and have a operation regime which was between these 2 bands. So such dedicated requests from users for specific experiments, they want to study some nonlinear phenomena. So they want high energy per micropulse. So that also we have done some tuning optimization of the machine. The important thing in an FEL is it gives micropulses, bursts of micropulses. So here we can get up to 85 microjoule, and this is at source. Now, as I said here, the FEL, due to regulatory constraints, initially the user station was planned on top of the tunnel. But then in the process of obtaining regulatory clearances, it emerged that it will be difficult to get regulatory consent if we still insist that we want it here. So we said we will build a user facility, but ultimately the optical beam path happened to be 50 meters. And this has to be transported through reflective optics. So even if we assume 95%, 96% reflectivity at this wavelength, it needs gold-coated copper mirrors. If you see 0.95 to the power 23, you only get 40% power transported up. So that is a necessary evil in accelerator-based facilities, because usage cannot be done there, the radiation. So we get bursts. At source, we get 85 microjoule. But now, as I showed in an earlier slide, users want 20 microjoule. So we are now able to give about 30 microjoule at the user station. We lose about 50–60% of the power in transport. And if users want macro pulse power, then we are able to give about 11 millijoules per macro pulse. This is at the source. So at the user station, it will be about 4 to 5 millijoule energy at the source. The important difference between Indus and here is the tunability curve that I showed. Actually, each point here is like a monochromatic light. It does not give a broadband radiation. So each point here is this monochromatic light with a spectral width of 1.4%. So this is another USP of the FEL. So what I showed as the tunable curve, it is continuously tunable with any central wavelength with this about 1% of the spectral width. And that over each band can be done in seconds. Then it is close to Gaussian. This is at the user station. So we have good lasing. This tells us that we have good lasing. This shows the saturated power. And this shows a short term, about 3 hours stability. Here it is better than about 5 to 7%. But typically 10% we can assume. So this was our, to reach this stage, took us about 2 years of optimization of the machine. And we thought things are good here. And we started giving beam to the user. And that is where we get good operational experience from the user, which is now telling us what more we need to do, because just the lasing average power is not sufficient, because the user wants to do frequency resolved experiments. So they have built a Michelson meter, interferometer, and when they see the spectrum, sometimes they see there is sidebands, sometimes they see there is no sideband. So now it is a question of repeatability. That why is it that sometimes some, as it said here, in December 24 and earlier, till December 24 and earlier, there were lots of sidebands. Now we don't have sidebands. So when that input comes, we go through our logbooks and then find out what are the changes made. And now we have a user coordination setup where any change, they come back to us and say, no, something has changed now. So we have to now have logging of so many parameters and online display so that we are able to make out what happened just now, so that the user saw something different. And that is where there is an importance of diagnostics. Diagnostics, not just electron beam diagnostics, but RF diagnostics, because the more the number of parameters we are able to monitor, the better we will be able to pinpoint what happened. Similarly, this is in a day. So when they are operating, the measuring from 1220 to 330, the central wavelength is the same, but they see some differences in the spectrum. So the power level also changes slightly over operation when we don't touch the machine at all, because the policy is that unless the user complains, we don't tune the machine. Once we have given beam to the user, because otherwise there is a tendency in physicists, because we are the same team who built the machine. So there's a tendency of person sitting there on shift to optimize something. And then the user complains कि कुछ change हुआ है. So even if there is a slight drift in power, we don't touch it till the user says the power is not enough, we are not able to use it. But this is an observation that the user has given us. And this is an important operational experience. And there are certain studies that we are doing. One of them I will bring out here, which will also be important, because future we are planning light sources which are supposed to deliver much better beams. So what are the kind of diagnostics that we should aim for? Similarly here, for some time they could see harmonics. This is the central wavelength, this is second harmonic, this is third harmonic. But then again, from May 25, they say it is better now. There are no harmonics now. This is at when they also, this depends on the resolution. So typically for their experiments, 5 centimeter inverse resolution is good enough for them. So they do all their experiments, or they're doing at 5 centimeter inverse. Okay, here he has said. So 5 centimeter inverse is good for them. So here we see there is the central wavelength is same, but there are some changes in the spectrum. But if they go to a finer, if there is some user who comes for a 2 centimeter inverse resolution, it may be that these are actually 2 peaks. They may be able to find out there are 2 peaks. So we need to be able to find out what is causing this, because we are the presently observable parameters, we don't see any change. So, and then this is another important thing. On some days when they say the pointing stability or the beam stability is very good, that is the laser at that point also, the pointing stability is good. Even when they ask us to tune the machine to different wavelengths, they see that the interferogram is quite good. But on certain days when the beams, the optical beam stability is not good, it is their observation, they say that the interferogram shapes are also not good. So these are the kind of inputs that they have given us. After we thought we have commissioned the facility and we are able to deliver good power, good quality, stable output to the user. And that is where it led us to some experiments, because now we are also bringing out an operations calendar. So we have kept some time for ourselves, and typically we start plotting the power, CW power output. So this is the kind of our mainstay. 12 to 15 milliwatts is our mainstay. That is the regular operation. Some optimization we do to try to go to 20 milliwatt. But here what is ideal is we should have a very almost like a line. because day-to-day repeatability, when we have same operation parameters, we should have a thin line here. But when we do some study that daily when we start, after giving 1 hour of warm-up time, when we set the klystron modulator as a certain fixed voltage and the input phase, that is the phase set, is at 0 degrees every day. That is the first study that we do. And we measure the power output at the accelerator, power input at the accelerator. When we see the power and the phase, we have about 6% change in power, but 47% change in phase at the input of the accelerator. So this may not be much, because 47%, if 18 is the mean, then it is about like 6 to 8% variation in phase. But here there is an important thing, that this is where for future light sources we need to improve, because this itself is with an accuracy of 5 degrees only. So what is the best phase measurement? The power measurement is like 0.3 dB accuracy. So how better can we go? Because if there is a 5 degree measurement accuracy, then we don't know what we are measuring is actually the right thing or not. So that is why when we look at literature, there is available in literature, there is a note here, research note here, which says that they have seen variation in SF6 pressurized waveguides from pressure variation of 2.6 to 3.4 bar. They have seen a phase change of 119 degrees due to some dimensional changes and due to dielectric constant of the gas. This is an internal report. And they have presented some theory there. So for us, the expected phase variation is 30%. We are measuring about 47%. So on top of this, their waveguide is all temperature stabilized. It is at 30 degrees plus minus 0.1 degree. It is one aspect where we thought waveguide does not need to be cooled. But there are people who are using cooled waveguides, because even this is a 40-meter long waveguide. So in a 40-meter long waveguide, they have this, and after that they say they have seen this kind of variation. For us, we thought that it is in air controlled atmosphere, because the tunnel has an AHU and the high power klystron room has an AC. So we thought it does not matter, but probably ambient temperature changes cause change in tunnel temperature, because there our specification is 5 degrees. The temperature control should be 5 degrees. But here, when they do this and then find this thing, so these are some of the things which we now feel we will explore more. Similarly, Pohang Light Source has a report where they say that in the 2.5 GeV LINAC, they have seen up to 210 to 200 MeV change in the mean energy in the LINAC. And that again they have seen is due to environmental conditions. This is the note. And now when our user says that they are seeing these fine things, we are also paying attention to such things now. Like for example, a simple thing that we have seen is, initially we never worried about the waveguide pressure. But at 27 kV when we start daily, we used to get about 9.07 megawatt at the input of the accelerator. Some days we get 8.9 megawatt. And the only observable we had is, we checked everything, we saw that the waveguide pressure is little low. So we called the experts, they increased the waveguide pressure, we got 9.1 megawatt again, 9.05 megawatt. Now, we are not
5 minutes.
So we are not able to put our finger exactly on that, but this is an operational experience that we have gathered, that just by changing waveguide pressure, we are able to get back to that same setting that we get repeatedly. So these are the kind of experiments that we need to study based on experience, and that experience also comes from the user, because once they start using the beam, they tell us what is the finer change in the wavelength. The mean energy is same, so that means the energy of the electron beam is not changing, but something else is changing. So some thoughts: advanced diagnostics are essential to characterize an accelerator, particularly for an FEL in terms of jitter in electron beam properties and in any light sources. So gross measurements of mean energy, beam emittance, and energy spread, they are not done online. They are done in separate experiments where we take the beam, have only 2 quadrupoles operating or only 1 quadrupole operating, center the beam properly, and then measure. But when we are actually doing the lasing experiments, we are not doing this. What is the emittance of the beam at that time? What we expect is that the LINAC is giving that beam, So that kind of beam is going through. But then are we filtering the wrong energy particles? The sidebands or the other wavelengths that we are getting could be because there are other bunches which are getting through which have different energy, slightly different energy. So those are the kind of things, diagnostics which we need. Bunch length diagnostics is essential. For an oscillator FEL, timing jitter in electron beam is essential, and then phase measurement, because timing in electron beam is related directly to the RF phase jitter in the accelerator. So those measurements are important. And then advanced transverse diagnostics, because the wavelength that we predict from FEL equation does not match the wavelength measured by the user. There is about 0.5 micron or 1 micron at best change. Now that is because the beam energy we assume is from the bending magnet setting. But bending magnet setting can give you the energy only if the injection is on axis and at the right angle. But in experiment, we are not able to verify that. So if we have BPIs where at multiple points we are able to make sure that the beam is exactly at same position every time, then we know that the injection is at the same angle. So now there is scope for further improvement based on operational experiences, but again I come back to the status thing that we are using it. We have about 6 user ports planned in the facility. 2 ports are already commissioned. This port will come up soon now because we have transferred a laser, and the user has done some initial experiments using this. So usually they in the study of transitions, they do the first order phase transition, they measure using the resistance change. But they have been able to do same using optical measurements. So from the FEL light, they have been able to see, yes, there was a first order phase transition in the material. And the importance of FEL over, and if you see here, so far the tool that they had was FTIR. If you see the FTIR, any conventional lab source based FTIR gives you this kind of transmission measurement because the power level of those sources is low. But with an FEL, the photon flux is so high that the signal to noise ratio can be reduced tremendously. Similarly, they have done a BISCO or a bismuth based superconducting sample study, and this FTIR has been artificially pushed up into the same, actually the FTIR reading will be much below because it is a low powered thing. But to make sure that the modes here, the FTIR readings are same as the FEL readings, to make sure we are having the same frequency measurement with the FEL, they saw that they are getting the same readings, but because of the high photon flux from the FEL, they are getting some additional modes here, which they could not see with FTIR. And that is where that physics is now being studied. Is it some photo-excited phonon modes, additional modes, which FTIR is not able to show? They have also done some imaging. So although we will keep improving the machine, utilization simultaneously is essential. And as this is the regulatory consent is also an important part of any accelerator, and it is in the scope of this thing. I just want to show this, that starting from siting and construction clearance, which was obtained in 2012. So the application started in 2010. And in 2010, to get this clearance, you need to have a full layout, machine layout, with a study of by the health physics of where the radiation hotspots are going to be, how you are doing shielding. And starting from there, trial operation we reached only in 2016. And from trial operation to get to commissioning, actual commissioning with final machine, it goes to 2019. And regulatory license comes to 2024. So it is a long journey for any accelerator based facility, which needs meticulous paperwork, documentation, because for ARB it is very easy, come again. And come again, they have meetings once in a year or once in 2 years, sometimes twice a year. So that puts you back because you cannot operate the machine without this. So this documentation, and this documentation needs inputs from all the divisions, all the expert groups involved. So that is why any accelerator based facility
Dr.
is
Pant,
an
please
interdisciplinary.
conclude your talk.
So to summarize, a unique IR based user facility is commissioned now. In-house experiments have qualified, and some outside users have also used the facility in December, starting December. We are also getting some samples from more outside users. Operational experience gives important feedback for improvement of machine, but for a light source, the best operational experience is available from the user, not from the machine builders, because our measurements are different from what the actual user wants. And from the initial experience, we feel advanced diagnostics are essential. So we have to go in for advanced diagnostics to be able to actually link what we are seeing with what is happening. And regulatory requirements, initial stages, we took 3 years to get even siting clearance because we tried to argue with the regulators. But then we realized it is better to just comply with what the regulators want to have a smooth sailing. So fulfilling all the regulatory requirements is important for smooth running. This area may not seem to be technically fulfilling because it is a lot of documentation, but it gives an important overview of the full facility to whoever is involved in doing this. They get a very good overview of the facility. Thank you for your attention.
Thank you, Dr. Pant, for a very nice talk on the IRFEL facility and importance of advanced diagnostics, and also bringing out the importance of user feedback for improvement in the machine, because finally it is the user whom we need to satisfy for his requirements. So thank you. So now the talk is open for a few questions. So there are, oh, okay, one question. Back, Manitosh.
Sir, in presentation, in one of the slides you have shown noise was coming because of the temperature variations. That is suspected based on the literature.
Yes. No, this is our measurement, but then we looked at literature. Has anybody, this is our measurement.
Yes, sir.
This is not noise. This is daily startup for same initial settings. We measure what is the power that we are feeding at the LINAC and what is the phase for same set parameters. And then we look at literature and see if somebody else has this experience, and it is available in literature that these things are found to cause such problems.
So are you going to improve anything in this cooling circuit?
Yes, yes, yes. I did not have time for that. Our microwave group has made a higher version of the phase measurement and the amplitude measurement facility. So right now we are at 0.3 dB and 5 degrees accuracy. And they have said that it will improve both the accuracies which they are now testing in the noisy environment. Because here it is a noisy environment. So first they are qualifying their instrument in the noisy environment. And once they say that they are able to get good readings, it will be implemented in the FEL.
Okay, sir.
So let us thank Dr. Pant once again.
Thank you.
It's my pleasure to present you a memento on behalf of the organizers. Next talk is by Shri Rakesh Nathwani. He is head of Indus Operation Coordination and Training Section, Indus Operation Division, RRCAT. He is BE in Electronics Engineering and passed out from 31st batch of BRC Training School. His areas of research work are operation of synchrotron radiation sources and accelerator beam diagnostics. And he is the recipient of many DA Group Achievement Awards and has more than 15 publications in journals, conferences as author and co-author. I invite Sri Nathwani ji to present his talk.
Pointer. So, thank you for the introduction. So, I will. कौन सा pointer था बोल? सही है. So, my talk will be on the experiences of round-the-clock operation of Indus facility and its training program. So as we know, the Indus Accelerator RRCAT has indigenously designed, developed and commissioned 2 synchrotron radiation sources, and these are the largest particle accelerators in our country. And Indus 1 is a 450 MeV to 125 milliampere electron storage ring with 7 beam lines. Indus 2 is a 2.5 GeV, 200 milliampere machine with 20 beam lines in operation. And it is being operated in round the clock mode since 2010 for a large number of researchers from universities, academic institutions and national laboratory. It is operated under the license from AERB. So this is the schematic of the Indus complex. We have injector microtron which is delivering a 20 MeV beam, and it is then it is a booster synchrotron which increases the energy to 450 or 550 MeV. This together forms injector part, and then this beam is used for storing the electrons in Indus 1 or Indus 2, and some pictures you can see of the Indus 2 ring. And see, as Indus accelerators are complex subsystems, so we have so many subsystems which are with almost all advanced technology, magnets, power supplies, RF, beam diagnostics, ultra high vacuum, LCW, compressed air. So, and it is complex machine, so all the systems have to be in place and operating continuously round the clock. And it is worthwhile to know that these are all the systems have been developed indigenously within RRCAT and with the help of local industries. So this is the injector system, the picture of microtron and booster synchrotron, and then transport lines are used for transporting the beam from microtron and booster to Indus 1, Indus 2. So this is some parameters of the Indus synchrotron Indus 1 source. So we have the 4 super periods and 1 RF cavity is there, and frequency is 31.613 megahertz, 7 beam lines. And this is the typical operation mode. We are normally fill this is an operation mode for 1 day. So 1 or 2 fillings we have, and we can have more filling based on the user requirements. So typical beam filling time is around 4 to 5 minutes injection time. And presently we are having a beam lifetime of around 3 hours at 100 milliamperes. And this is about the Indus 2. This Indus 2, this typical user mode operation. We inject the beam in say 1 hour around 50, whatever the current is, so up to 200 milliampere, and then we inject at 550 MeV, then we stop the injection, then we ramp the energy. And then the beam is provided to user in this period the user is using, and typically we have a lifetime of 55 hours at 100 milliampere presently we are having. And so some of we have 6 RF cavity, 3 insertion devices, undulator installed, and 20 beam lines are in operation. All are having permission from AERB. So these are the few pictures of Indus 2 ring. This is the TL3 joining Indus 2. This is so you can see the beam lines, front ends coming from the dipole magnets, dipole chambers, and these are RF cavities, and this is a picture of undulator which we have installed in 2015. So this is the operational performance of Indus accelerator in the recent years. So typically we are getting providing beam about 7,000 hours in Indus 1 and around 55 to 5,600 hours at 2.5 GeV in Indus 2. And our operation days are, if you leave aside the COVID days, around 330 to around 300 days. And beam availability, if we translate into per day, it comes out to be around 20 to 21 hours in Indus 1 and around 16 to 17 hours in Indus 2. And these are the usage about so we have users from almost all areas, from the universities, all IITs, research institutes, and also now we have users from the industries also, mostly pharmaceutical industries. And the number of user experiments has crossed 1,000 mark, and we are maintaining, and these are the publications coming from the Indus beamlines. This both this Indus 1 and Indus 2 both together. Now coming to the operation of Indus accelerators, the day-to-day operation, maintenance and upgradation activities are managed by the Indus Accelerator Coordination Committee. The staff deployed in the operation is pooled from various subsystem groups which have built the accelerator. So we don't have a dedicated operation crew. We pool the manpower, and for a few days they work in shifts, and then for the remaining day they do R&D in their respective parent divisions. And we provide them training for around 8 months, which is the training is in line with whatever the training program of other this nuclear power plant and fuel reprocessing facility, etc. of DAE. So we have checklist, clearing, walkthrough, and then the licensing qualification interviews. So we have presently we have pool of 60 trained and qualified operators which are operating the machine, and we have 6 persons in a shift. And the maintenance is done by the subsystem groups. So for day-to-day operation, we have a Indus server which contains the real-time data and information about the operation and the performance of subsystems. We also get the historical data of subsystems. And we also have a web-based modules developed by our accelerator controls group, and these applications have simplified the operation management and made life easier for the operators. So some of these are a daily work plan we can upload on the Indus server, and at a time for 10 days work plan we can upload. Then we have our logbook is totally electronic, online based, and then we have a fault logbook, beam time, booking manager, and machine experiment. So all this information we can see from our sitting on from the Indus server. And we have also started using AI techniques in the regular operation, which have also greatly simplified the work of operators. And there will be separate talks on both these features. So as you can see, the operation calendar of this Indus is displayed well in advance. So this calendar for 2025 was released in the December 24. And as you can see, we are operating almost 330 days. On the red ones are the shutdowns. So we have only 5 shutdowns for preventive maintenance. And it is displayed on the RRCAT website also. And users can book the machine. Then based on the dates, they can book the beam time. And we also have 2 days every month, 2 days dedicated for the machine experiments, where we do the experiments for improving the machine performance. So just now I told that we are operating 17 hours per day, 17 hours per day in Indus 1. So what about the remaining, whether it is down? No, it is not down. We have calculated the uptime of the machine. So for 24-25, so maybe number of RTC operation days were 328 days, and beam availability is at 2.5G 5900 hours. And then apart from this, some other time is also goes in the preparation of this beam. So time taken for injection and ramping for this year to 775, time taken in magnet cycling. So we have to cycle the magnet every time we refill it. So considering 1 filling per day and 40 minutes of cycling time, so it is 216 hours. And then normally we have a separate maintenance days for plant every alternate month. But for urgent maintenance, we do on weekends if there are some urgent maintenance works which has to be done. So we do on weekends, and on that day also that beam is affected because of that. So it is mostly on every Sunday we do it actually. So it is 400. So if we calculate the total availability means uptime, and 7,300 hours for 24-24, and maximum number of hours is considering 328, it is 772. So we get the uptime, which is 92, around 92% in both the machines. Similarly, for Indus 1, we don't have injection, only the cycling and maintenance time. So we get this figure, and this is maintained. If we see the last recent year of performance, it will be around 85 to 95% of the uptime. Now, just to give a fault, so we maintain a fault logbook. So faults in the machine in a recent year have been seen. It has been given for around So it is reducing, it was 23, it was more, and here it is COVID affected. So now these are not the all the faults. These includes all the total faults of the all the even microtron booster Indus 1, Indus 2, and these fault, every fault do not result in the killing of the beam. So if we find that only 40% of this fault will result in the killing of the beam in Indus 2, Indus 1 or Indus 2, where user will be affected. Otherwise, some general faults will be there, na? And in case of many faults, so if beam gets killed, so we can fill in within few minutes to few hours. For example, if it is Indus 1, we can fill it. We attend the fault and immediately fill it within few minutes. So this is the, so it is not, fault is not affecting much to the users. So this is a typical distribution of fault, subsystem wise distribution for the year. So typically see RF power supplies and in all subsystems. So this is just for information. And there are some non-concluded and some faults. So this all this analysis is done by the system expert. The operator logs the faults, and email is generated through the expert. And experts attend the fault, and he writes the description what went wrong, and some faults which cannot be diagnosed there, and some others means they are not related to machine or the building maintenance, fire, like general services of the facilities. They are also comes under the others. And some faults which cannot be so attributed to any other subsystem. So for example, some power supply has tripped. So it is due to the water, LCW, or some other, or controls. So it is sometimes lack of data we cannot find. So it is not concluded. So further going into the fault analysis, we have another measure of the operational performance, which we call as a breakdown event. So faults which take longer time to resolve have been categorized as the breakdown event, and it is defined as the fault due to which beam is not, if user is on board and beam is tripped, and if user is not able to get beam within 8 hours, then we call it as a breakdown event. And the number of such breakdown events for the recent year has been like this. It is quite within reasonable number. Now coming to some of the, see, it is a constant in Indus, so we are constantly, and sometimes we encounter the faults and we overcome that. So just I will discuss one or two case studies. So in one of the incidents, we have observed a vacuum leak in dipole chamber 1 of Indus 2, and suddenly the vacuum went down from -10 millibar to -8 millibar. And normally we have this the dipole magnet which is opened, and this is the dipole chamber which goes inside the dipole magnet. So normally earlier used to get the leaks, leaks on the outer side. So it can be identified, and we spray the sealant and it is addressed. But in this case, it was a very peculiar thing that the leak was identified on the inner side. So it was a very challenging task how to access this. This portion was not easily accessible. And then to address this, what options were there, that we have to open the chamber, and otherwise this magnet we cannot move. It is a very huge magnet, 5 ton, and so it was a very tricky situation. So our vacuum team developed a setup. A small mechanism was made by which this spray bottle, which is vacuum sealant, was inserted. A sealant was made, and mechanism was made to move from outside. And this mechanism was inserted through this few gap is there through this some small portion, and then it was continuously sprayed, and then at the time of where the leak was there, it immediately vacuum improved. So in this way, this work was done, and it has saved a lot of time and effort. Otherwise, opening the chamber will take 4 or 5 weeks, restoring the vacuum. So this is a good effort by our UHVTS and AMTD team. And also during this work, when it was not that machine was not operated, so it was a minor leak. So the machine was operated with slightly lower lifetime. So when this in the process, when this in the lab, this mechanism was made. So this is way how it is addressed. And in another case, during routine inspection, we found some this you can see them brown patches were observed on the bus bar of the quadrupole, and these were observed only on the few quadrupoles which were downstream of the dipole chamber. All other quadrupoles were not affected, and it cannot be attributed to the heating because it was patches were there, and it was not seen on the all the quadrupoles. So our this task was given to it was thought that it may be possibly due to the radiation damage. So our HP unit carried out study by using the radiochromic films placed over the bus bars, and then it was confirmed with this that these radiation it is due to radiation damage, and is what is scattered SR which was from the termination ports of the dipole chambers which were not in use, and this flange was shielded, and this issue was resolved. So this work was executed by our health physics unit. So now see, we are not only operating but continuously upgrading the Indus accelerator for improvement in beam quality, operational performance and reliability. So just giving you a timeline, in 2014 we commissioned 2 undulators U1 and U2 which resulted in improvement of photon flux by 2 to 3 orders. And then in the following year we commissioned Apple 3 undulator. Then in 2016, we replaced the leaky ceramic chambers of injection kickers of Indus 2. Then successful installation and commissioning of the indigenously developed RF cavity. Earlier, we are having RF cavity from Electra. So it was a good, and so this made our whole machine indigenous. And then we also installed and commissioned new injector microtron and upgraded TL1. Then 6th RF cavity was, and the LMBF kicker cavity was installed in 18. And then installation of vertical pincher magnet, horizontal pincher magnet. Then high power circulator indigenously developed and is successfully deployed in Indus 2 RF system. It is working very smoothly. Then we upgraded that because of the aging effect. It is all more than 25-year-old machine. So we upgraded the TL2 in 23. Then in last year we carried out the major upgradation of Indus 1 synchronous SRS, whereby we installed new diagnostic devices and steering magnets. And recently we have also, earlier we are operating at relaxed optics, now we have deployed low emittance optics in Indus 2 and it is in regular operation. So this has also helped the user. And you have to also appreciate that all these works, these are all very big works and they were done in a tight schedule. And see, we are operating for 300 days and all this has to be done within the shutdown days. So it is a very tight schedule, and this thanks to all the teams of all the subsystem groups of Indus facility who have done this. So this is
3 minutes.
Yes, sir. So I have some few more slides. So this is just a milestone in which in June 2014 we achieved 200 milliampere for the first time in Indus 2, and this is the picture taken our former director Dr. P.D. Gupta. You can see here he immediately rushed. This was achieved in the afternoon, and all the persons were there in the control room. We took the picture. And this is another milestone which is showing more than 120 hours of continuous beam operation in Indus 2 in a single filling. So this actually normally we every alternate day or every day we kill the beam because of the user want higher current. So we refill the beam, but it so happened that in this duration our injector was down, and normally we replace the cathode during shutdown, but it went down during the operation cycle. So we continued the beam because this replacement of cathode takes 2 days. So we continued the beam, and it continued for 5 days. So it has shown a demonstration of improved reliability and the performance of subsystems. So this beam was continued, and it was killed intentionally at the end of 5 days when our injector became available. Now the performance, so we also have a safety systems for our Indus facility. So we evaluate the performance by the safety score. And we have in safety score, we have attributes of various safety attributes are there, and we assign weightage. And so far we have achieved a safety score of 99% for the last 3 years. And further, and we have started calculating only recently. So this it is also linked to our PRIS target. Now coming to the training, qualification and licensing program. So it is, we are having a elaborate, as it was told in the morning also, so TQLP we call it, and it is started in 2009. So far we have, when we are qualifying personnel at 3 different levels, namely level 3, level 4, 5, it is like similar to all DA units like nuclear power, and more than 150 personnel have been trained, and refresher training is also imparted to these operators every year. And this is our stages of training program. This we have training through lectures, then written examination, on-job training checklist, walk-through test, and then final assessment through oral interview, which is done by the licensing committee or assessment committee, which is appointed by Director RRCAT. And the requalification is done after every 3 years. So now this is a major our achievement, that this inclusion of Indus facility under the qualification incentive scheme of the DAE. So our training program is going on since 2009. But we in 2016, under the leadership of our then chairman of IACC, Shri Thakurta, we sent a proposal to DAE for inclusion of Indus facility. Which was then applicable for this nuclear power plant, NFC, heavy water, and fuel, like this nuclear facilities. So, so we initially prepared it was in the form, so we approached the DAE sent it to the qualification implementation committee of the DAE, forwarded it to this QIS implementation committee. And the committee, then we made a comprehensive document. Earlier our training program was in the form of minutes of meetings. So we made a document, proper document for that. And in 2018, we presented our proposal to the implementation committee, which is headed by Director Operations. So in the first meeting itself, they agreed in principle to include the, in principle agreed to include Indus facility. But there was some problem that the office memorandum for this, it was not having the accelerator facility mentioned in that. So they told that we will write to a DAE to include that synchronous radiation facility in this QIS. So that they did, and after that the review committee of QIS visited the Indus facility. They saw our training infrastructure and our other checklists, etc. And subsequently in 2020, so these meetings are held only once in a year. So in 2020, DAE amended, on the recommendation of the DAE amended the OM and included synchrotron radiation facility as eligible for QIS. And then subsequently this AERB also helped us. They sent a note on the acceptability of TQLP, our program, training program, and agreed for constitution of assessment committee of qualification process by the Director RRCAT, because these assessment committees for nuclear power plants are constituted by SARCO. But in our case, they agreed that it is sufficient if it is Director RRCAT is constituting the committee. So then further in 22, DAE issued OM on, and they included the Indus synchrotron radiation facility under the QIS, and Indus became the first accelerator facility to be included. And we have at present we have QIS approved for 102 posts, and presently 60 personnel are getting this incentive. It is a big achievement and is a recognition by the department for our training program. So to conclude, the Indus synchrotron radiation sources are being operated successfully in round-the-clock mode as a national facility. The operational performance and utilization of the facility has shown consistent improvement over the years. The uptime of the machine has been in the range of 85 to 95% in the recent year. The training program for operators is well established and recognized by the department, and the facility has excellent track record in maintaining safety. So now coming to the acknowledgement, because it is a complex facility and so many groups are involved. So this work presented is a collective work of the staff of various subsystem groups of RRCAT involved in developing, running, maintaining and upgrading the facility and maintaining safe working environment. The efforts of each one of them is gratefully acknowledged. Thanks are also due to the Indus operation crew members who are successfully operating this facility in round-the-clock mode since last 15 years. Special thanks to all beamline scientists of the Indus facility and users for their immense contribution in the utilization of the facility. Thank you.
Thank you, Shri Nathwani, for bringing out the aspects of training, qualification of Indus for operators of Indus facility and its importance. Now the talk is open for questions. Yeah, Ravlani ji.
Nathwani ji, compliments for wonderful presentation, and definitely you are acknowledging efforts from all the subsystems. I have one because a curiosity hai. What is the cost of per shift in case of Indus? Because that's a very important figure, sir has shown for the facility.
Cost of per shift, actually it is a, you can take electricity only the.
Not only electricity, there are many things. I'm curious to know.
We have not worked out, yeah. There is no dedicated shift. We have pooled the manpower cost is zero because we have pooled the manpower.
I think we'll jointly calculate. Let us commit this.
Yeah, so it is 4 megawatt, I think 5 megawatt power. Yeah.
From if look, see the mega science vision document which was shown by him. So that had, I mean, the cost of the operation shift. I mean, different people have calculated. So you can look at the document that gives you the cost of shift operation for IUC accelerator, for the Indus, and for other accelerators also.
Any other question? Yeah, Manitosh.
Sir, our facility is for public use, basically, for universities and even pharmaceutical industries or scientists who want to use it. What I could not understand up to now, what we are doing to make it more that publicity point of view, that this way you can utilize this facility, because the users from the local area, like we are in MP, but from MP universities, users are very less, what I feel.
No, our utilization division is has arranged a lot of theme meetings. They have gone to universities, and it is through word of mouth it is spreading. Actually, if one person comes from one university, he will tell to his colleagues that it is you can do it. And in this way, we are getting users from all over India, even from Indian, from MP also people are coming. But that depends on how the research work, the quality of research work which is going on in the universities.
Yeah, Dr. Mehta.
We follow an acquittance program where we go to area where we don't have users and just give one day team acquaintance that these are the facilities, this is how you can use it. And that's how slowly we have built up on that. Yeah. So maybe this kind of an acquaintance program can
we are also doing
must
that.
Be having
those type of outreach activities for Indus accelerator. I believe that Dr. Dr. Fakhri is here. He has given such lectures and programs in Ujjain, Vikram University, Ujjain. So like that, we are also conducting such type of outreach activities. Yeah. So that is a good this thing.
So our utilization division is
enhance that program. So let us thank Shri Nathwani ji for nice presentation. The next talk is by Dr. Surendra Yadav on operation in autopilot mode, an AI support system for operation of Indus 2. A brief introduction to Dr. Surendra Yadav. He is Head of Diagnostic Software and Devices Development Lab of Beam Diagnostics Section at RRCAT. And he earned his PhD in engineering physics in 2022 from HBNI. He is a Bachelor of Engineering in Electronics, and his areas of research work include AI-based system optimization and control, implementation and optimization of longitudinal and transverse feedback systems for Indus 2, development of Betatron tune feedback system and beam diagnostics facility, beam experimentation on beam loss control, and improvement in the beam performance. He has more than 40 conference, international and national journal publications. With this, I invite Dr. Yadav to present his talk.
Thank you, sir. Thank you for giving me such a nice introduction for me. And first of all, I want to thank organizer to giving me an opportunity to talk here in this forum. And my talk is not for the accelerator, whole accelerator. It's a particular part of the accelerator, and that is for Indus 2 beam injection optimization by an automated system, which is AI-based techniques. So the topic is the operation in autopilot mode, an AI support system for the operators to do the operation in Indus. So this is the outline of the presentation. So because there are so many systems in the subsystems in the Indus accelerators, so we have start with the introducing the system. Then part by part we will go ahead, like improvement in the booster beam current, then improving the beam injection efficiency, then controlling the pulse magnets current, and finally the integrated system, that is the autopilot system, which do the injection by autonomous means. So the synchrotron, you know that in the synchrotron there is majorly the injector. So we have a injector microtron plus there is a booster synchrotron where we inject the beam in the booster, then ramped by the RF where it takes place the bunching, and then after sufficient energy of the beam, this electrons is transferred so the TL2 TL3 to the Indus 2 synchrotron. So that is what basically the systems, but you see basically there are n number of magnets, then RF and many systems. So handling all these systems for doing the beam injection become challenging when we require the tuning of the multiple variables, because we required a very high performance of the system and there are reliability concerns. So this also need basically a handling of the system, tuning the day by day, and optimization of the systems with frequently. So to handle this challenge, we can use the AI techniques to reduce the time of tuning, and also because the operator by operator, basically this tuning may be changed, the performance may be changed. So if we want repeated performance, we required a system which do the same process repeatedly in automated manner. So repeated performance, then it also helps to reduce the intervention of the experts, also intervention of the operator. And there's also a facility of adaptability in the tuning system, because sometimes we have to change the range of the parameters. We have to operate at some other parameters. So that required basically wide range of tuning, or sometimes the small range of the tuning that can be adopted by the AI based system. So there's a n number of use of the AI in particle accelerator worldwide. So that is for the beam control and optimization, particle beam design and simulation, and sometimes fault detection or anomaly detection. So here I am using this for beam control and optimization. For that basically I am using reinforcement learning for beam tuning and optimization of the multiple parameters using the random optimization method, that is genetic algorithm and mode frame optimization. So this system you know very well. So in our system that is already covered by my colleague Sri R.K. Nathwani ji. So we want to operate this system with better performance, that is better injection efficiency by the autopilot system. So that is required good performance of the microtron, then booster, then proper transmission of the beam in TL2 and TL3, and the better injection of in Indus 2, sorry. So what is the requirement? So there are two types of the requirement. One is a day by day requirement and another is a intermittent requirement. So like day by day requirement is handling the tuning of the cathode power supply, TL1 magnets, and setting up the booster injection system. That is required to achieving the good booster current. The another is the tuning of the horizontal string coils magnet and vertical string coil magnets along with the septum magnet settings for having the good beam injection in Indus 2. Another requirement is the adjustment of the fine delay and amplitude of the kicker to achieve higher beam current in Indus 2. So that is what basically daily we have to do almost for achieving the beam injection. But there is some intermittent requirement. When we change the cathode, then we have to optimize the transmission line. Then basically if there is some change in the major change in the magnet, then we have to optimize the TL2, TL3, and many times we have to optimize the pulse magnet over a month or 2 months. That is the intermediate requirements. So that all requirements we want to fulfill by the autopilot system. So we will start one by one. So one is the booster beam current optimization using RCGA. So the booster is the injector of Indus 1 and Indus 2, and this is a pre-injector microtron which is transmitted through the transmission line 1, and you see where the horizontal string coil, vertical string coil, quadrupole magnets, dipole magnets is there. So if you want a good booster current, then you have to basically optimize this transmission line and also the good required a good microtron current for this. So what we are planning? We have planned basically the 9 string coil because we are not changing dipole and quadrupole. We are mostly changing the string magnets to optimize the beam injection efficiency. We change the position as well as angle at the injection point of the booster. So we have taken the 9 string coils for that. So this is the 9 string coils. So 4, 2 VSC, 2 HSC here. At the TL1 control system also there are the 5 string coils. So this is the 9 string coils we are taking for optimization, optimize simultaneously. And this is the scheme how this the real coded genetic algorithm controller optimizes these supplies of microtron and TL1 to having the good booster current. This is a black box optimization by genetic algorithm. So we have only the state that is the booster current for optimization. For that we are using the random optimizer. That random optimization is performing the optimization in the search space by putting the random solutions, and these random solutions converge with the iterations. So for that basically we have developed an algorithm which is a modified form of the standard genetic algorithm, that is a adaptive variable boundary based real coded geometry algorithm that is used routinely for optimizing the booster beam current. And this is the one of the example how that has optimized the booster beam currents with help of this RCGA. So here you can see basically the result. Without optimization it is a 3 milliampere, and with optimization it is a for more than 5 milliampere. The second aspect of the optimization is booster injection efficiency improvement of Indus 2 using mode flame optimization. So there is a n number of optimization algorithm is there. It is a one type of the swarm intelligence based optimization algorithm, where the modes is used as a solution and flame is basically is a target. So the moth is basically circulating in the spiral manner, hunting the search space by applying the different solutions. So what it does basically applying the different solution in the machine and checking the basically what is the solution, best solution by different modes, different flames. So number of modes and number of flame is searching the huge area of each space of the your search space. So by that basically we can able to do optimization of number of variables simultaneously, which is very difficult by the computational methods. So for that basically we have taken the first TL2 TL3 optimization using this mode frame optimization, where 14 number of string magnet are optimized using this mode frame optimization and achieving the good beam injection efficiency after the optimization. This is the scheme how we are doing. So we have used a MATLAB server based interface for setting and taking the readback of the power supplies, and also we are taking the current of the booster and current of the Indus 2 to calculate the beam injection efficiency, because our aim is to maximize the beam injection efficiency. So the ratio of this charge injected in the Indus 2 and charge extracted from the booster is giving the beam injection efficiency. So that way basically we are calculating the injection efficiency here. So that is a typical results of the optimization. So that improve the beam injection. You can see here the result. So this is the basically without optimization and this is the with optimization. Almost 40% improvement in the beam injection efficiency we have find with the help of this optimization. The another part of the injection is the pulse magnets. So we have also optimized this pulse magnet of the Indus beam injection to improve the beam injection efficiency. So we have this pulse magnet, thick septum, thin septum, and K1, K2, K3, K4, and this all is optimized using the mode frame optimization. And you can see this is a typical result of the optimization. You can see there is a increase in the beam injection efficiency with the iterations, and here we have achieved almost 60% improvement using this optimization. Then there is also a requirement of controlling the kicker power supply settings. Because of this harmonic stability, there is a slight shift in the basically the this kicker pulses, which we need to control within 10 to 12 nanoseconds in day-to-day operation. But sometimes the mismatch is better for beam injection. So what we do basically, we have developed a fuzzy control based system which control this kicker setting depending on the beam injection efficiency, not depending on only the reference. So that is making the probably the probable solutions for the kicker settings using fuzzy control system. Here what we have done basically, we have use of fuzzy controller which take the error in the amplitude and delay from the reference value, and it also take the beam injection efficiency by measuring DC-DC current of the booster and Indus 2, and finally it calculate the what is the correction level in the kicker settings, and that will be changes with the beam current. At the high beam current basically we apply almost full correction, and with in the initial portion we allow the basically some error in the kicker system. So that way basically we take the advantage of the mismatch using the low current value, and then later on basically we match with the help of this fuzzy control system. And here we achieve basically 12 nanosecond timing accuracy and plus minus 0.4% current amplitude accuracy in the kicker supplies. So this is a typical application of the this feedback system. So these all the systems we have integrated at a single place. That is the autopilot system, which is an expert system. So that having the basically facility of optimizing the all these sectors like a TL2, TL3, pulse magnets and booster optimization, and it also providing the univariate tuning based on the RL agent, reinforcement learning agents. So it also required the implementation of the emission feedback loop, because the variation in the emission may disturb this optimization. So we have also used a emission control loop where the emission of the microton cathode is controlled by the nonlinear controller, that is a SMC controllers, sliding mode controller, and you can see the effect of this controller. So there is a minimum requirement of the autopilot system, or you can say there is some limitation in the autopilot system, which is what the minimum booster current is required for that. If suppose there is a no booster current, it will not work properly. So at least basically we have to give the minimum booster current of 1 milliampere. Then there is a beam injection, because many times what happened, if suppose one power supply is not functioning proper, your beam is not going from the TL to TL3 smoothly, then there is a no injection. So what it improve? So at least there is some injection is required, and then also the another thing is basically the stability of the optics of the Indus 2. If suppose basically Indus 2 having the some excitation or some basically beam stability, then basically also we cannot have a good injection because of the only transferring the beam from booster to TL2, TL2, TL3 and Indus. So that is the limitation or requirement of the autopilot system that should be fulfilled. Then we have autopilot mode where we cater the routine operation tuning. So here we are applying a RL agent which control the basically power supply settings of the many string magnets and the pulse magnets, so the MATLAB server to accelerator system, and here from the accelerator system it measures the beam injection efficiency, which tells the interpreter how we have to modify the agent for tuning the beam. So suppose it will basically tune the
3 more minutes, Doctor. 3 minutes.
So suppose basically it have the basically TL2 or TL3 basically beam position and angle it will tune. So what it does basically, it will apply some change in the string magnets, then it see basically what is the beam injection efficiency. That will decide reward. So if this is a positive reward, it will do that in the same direction. It is a negative reward, it will change the direction. It will narrow down the basically limit also. So that way basically it learns and it applies the basically changes to the system for tuning of the beam injection efficiency continuously. So this is the basically typical user interface for the operator, where they have to enter the target beam current and the some initial value of the cathode emission, what cathode emission should be controlled at the what level, and then also the what is the injection septum value, and after that just they have to press the button start injection. After this, basically everything from optimization of the microtron, booster, TL2, TL3 and injection septum, it will do, and it will start the injection in Indus 2 till the target value actually. So here is the typical results which we achieve just after the shutdown of the January 2025. So you can see this is the curve where basically it will do the optimization, and after all the optimization tunings, there is a smooth injection in Indus 2. So this is a typical results of autopilot beam injection. So this part, this is all the technical developments is completed, and the machine, this system is in regular use. So there are basically still a requirement to upgrade this to handle the non-availability of the booster. So automatically it will take the booster current. Then upgradation is required to handle the failure of the system. Still we found sometime failure because of the speed of acquisition and other things. And we also want to include a parallel processing for the booster and for the injection efficiency. So that will be that how basically it will be better for next for the operation in future. Now I want to acknowledge this work. So I am very grateful to Sri T. A. Puntambekar, Additional Director Arcade, for his guidance and support during all this development. I am also very thankful to colleagues of the Accelerator Control and Beam Diagnostic Division and Accelerator Physics and Synchrotron Utilization Division for many discussion and support during the development. I am also thankful to Sri Raj Bhange, Head Accelerator, for providing me opportunity to implementing this continuously, and very thankful to Indus Accelerator Operation crew members. They are using this system regularly and giving me a feedback to improve the system. So thank you very much. Thank you.
So thank you, Dr. Yadav, for a very nice coverage of talk covering the successful implementation of AI optimization techniques in Indus Accelerator. So now the talk is open for questions. Is there any? Yeah, Ladji has a question.
See, very good software you have installed, which has helped in the operation. But now, up to this level, you have whatever done. What is the future course of upgradation or plan to have it more?
So actually,
user friendly rather.
Yes,
Yeah.
actually, we have to implement some user friendly methods in this at least to give the more reliable output and reduce the failure rate of this. Even there's a basically almost 15% failure basically we see with the autopilot mode. In the case of there's a some large shift in the beam position, or there's a no booster current, or suddenly booster current is dropped. So that need to be improved by the AI, making the agents who basically take care of this thing actually. And also we are planning to basically have the more optimization algorithms which is faster for improving the basically time consumption during this optimization.
And are you going to integrate with single button operation to have it better?
So actually, the one part we have already tested basically a part of this with the single button testing, single button operation. Now we are planning to operate with the single button operation basically.
Yeah. Dr.
on a
Mehta.
lighter note, will it make the operator's training irrelevant?
No. It is a support system.
I mean,
that is,
because if everything becomes automated, your previous speaker mentioned about such a huge task to get that particular training qualifications and everything. I mean, it's just this is a shortfall of AI. Will it be true or in future?
this system we are calling the operating support system for operator only. So if they want basically use this system, they can use. Basically if there is a smooth operation of the machine, you did not require this type of the system. You just load the files and system works well actually. But sometimes basically there are experts required or basically some intervention is required. That time basically this type of the system basically is very useful. Because many times in the night basically we don't want to call the experts. That time basically you can run the system and just forget it.
I think we can compare it with the autopilot of aeroplanes. We cannot do away with pilots even if there is autopilot system in aeroplane. So, yeah, Mr. Gandhi.
Surendra, it's a simple question. Autopilot control is helping machine operation, but whether is it helping in better understanding of the machine? Whether there is any analysis or type of actions that you are taking are helpful to understand the machine better.
Sir, actually, all the settings, whatever changes done by the autopilot, is recorded day to day basis. Actually. And we are in the process to include basically the analysis part of these all the settings, where we are doing the changes, why we are doing the changes. So that part basically is still in the development process.
So perhaps this is the answer to Mr. Mehta.
You have shown one limitation on booster current that this successful operation of autopilot is subjected to 1 milliampere in booster. What are the uncertainties? Because injection is anyways being taken care by autopilot in booster. So when you are, my question is that when you are facilitating the injection in booster under the supervision of autopilot, then what are the uncertainties by this limitation of 1 milliampere?
1 milliampere, why I am telling basically this 1 milliampere is not 1 milliampere only. That means basically the booster is continuous current is changing from 0.3, 0.4 milliampere to 1.2 milliampere. So if it is basically 1 milliampere, that is a possibility to go it for 0.3, 0.2 milliampere where there is no injection. And we are tuning the basically machine because of the this transmission. So in that condition basically it will be basically the error prone actually, sir.
No, my point is that when this is under the supervision of autopilot, why the autopilot itself should not ascertain to remove this condition of 1 milliampere? Are there some other uncertainties on that?
There is some limitation in the autopilot system because it cannot control the booster power supply. So the booster power supply control is not available in the autopilot system. Right, okay. That is string magnets and the quarter pole magnets. So because of that, basically, it cannot show basically about the booster current, sir.
Okay.
So let us thank Dr. Yadav once again and present a memento on behalf of Now, the last talk of this technical session is by Dr. Sista VLS Rao. He is the head of Accelerator Physics Section, IIDD, BARC. And he holds a postgraduate degree from Hyderabad Central University. And his areas of research work are design and commissioning of high current radio frequency quadrupole accelerator. He is also involved in the design and development of high current proton linear accelerator project, LEHIPA. And he is recipient of DAE Young Applied Scientist Award and Science and Technology Award. I invite Dr. Rao to deliver his talk.
Good afternoon, everyone, sir. First of all, thank you, sir, for your kind introduction. And I would like to take this opportunity to thank the organizing committee for giving me this opportunity to talk about our LINAC, Proton LINAC LEHPA. And the title of my talk is Operational Experience of LEHPA. So on behalf of our LEHPA team, I'm giving this. And outline of my talk is, first, I will talk about the introduction, and then I will talk about the beam acceleration phases, which we have done. And now here I have written commissioning experiences, because we have only commissioning experiences. Operational experiences, we have not achieved that into the operation stage. So that is why title should match with the team meeting. So that's why I kept it operational, but actual thing is the commissioning experiences. So, and then future upgradation to the operational things, and then summary. So as you all know that we have a ADS project, which is an alternative route for the thorium utilization, which is alternatively, it is a substitute. I will not substitute, it's a complement to the third stage nuclear program. So, which needs around 1 GeV and 10 milliampere. This current for a proton and heavy ions is a huge current, whereas for the electron LINACs, is considered to be a very small current. Okay, so, but protons, it is a huge current. And this LINAC, we were planned to go into the 3 phases, and everyone, I think DAE is good in making everything in 3 phases. Now, of course, now it is a 5-stage program is also there. So LEHPA, which is a 20 MeV program, and then we will go to the MEHPA, which is 200 MeV. In that first phase, MEHPA 1, which is 40 MeV, which is our near future, and HEPA and 1 GeV is a far future project. And then we have made this operationally commissioned in 2023, August 2023, we got the first beam. So this is the roadmap for our HEPA development. Definitely, whenever we are developing in phases, definitely we have to have a standalone applications also. So the choice of 20 MeV was chosen because it has an application like radioisotope production, F-18s and other things, which is in sync with the RMC per rail. But we don't need very high currents for that. But there are other nuclear physics experiments we can perform. So that is the reason why we have taken the 20 MeV. And then for the medium energy, high intensity 200 MeV project, where superconducting route we are following, there are several other applications. And then definitely this is our ultimate aim is ADS. So, but I don't know whether I can see at the future or not, that future. So, but this is the layout of this 20 MeV, where we have an ECR ion source, which is a 50 kV, and it is designed for a current of almost like a 50 milliampere current, which can be produced. Sorry, has it changed anything? Oh.
It was not shared, so they are having some settings for online sharing of this.
Oh, okay.
Just wait for this.
Up. And then this, can I start now? Okay, this 50 kV ECR ion source, which is developed by the APPD, BRC. And then there is a 4-meter long RFQ. And you can see this is a 6-meter diameter only, aperture wise. Sorry, again, it has not. No, it's okay? Okay. So, and then there is an LEBT, low energy beam transport line, which matches the beam from the ion source to the RFQ. And this is the thing which we have developed. And entire accelerator has been developed in India indigenously and in some of the MSCs and other things. So some components which we have already got the thing from the DAN physics and other things. So that's a. And then MEBT, which is a medium energy beam transport, where 3 MeV beam is directly injected to the DTL. And this DTL is a 12-meter long structure. And the thing is that there is no diagnostic elements in this 12 meter. Whatever the diagnostic elements are there are in this MEBT and in LEBT. So there is some issues which we have seen that I will talk in this lecture. So now commissioning stages, which we have done, as prior to this, we don't have an experience in RF accelerators at all. We are very good in DC accelerators, and we have taken up in the, so we thought that first we have to go into the modular stages. So that's why initially we have commissioned accelerator the beam using the RFQ, only this portion we have thing. And then later on we have added the tank 1, tank 2, and then once we got these 3 stages, then we have got somewhat overconfidence, I will say. And then we have connected all these 2 tanks in a simultaneously, and we want to start the commissioning. And this is the timeline which we have. In 2019, we got the first 3 MeV acceleration from the RFQ, and then in DTL1 and DTL2, see, the thing is, there is no much, just only 3 months, only within 3 months we could able to do the commissioning of DTL2. And DTL3 and 4, it took almost like 1 year for us to do that. And there are a lot of issues which we have faced. And now coming to each and every stage, I will talk about and what are the difficulties we have and how we have rectified it. And some things we have not yet rectified. We are investigating those things. So we have seen initially ECR and source and LEBT. This is a 3 electrode-based geometry. And between the plasma electrode and the suppressor electrode, the gap, we have fixed it. And there is no space to arrange or anything. So that is the first AND source which has been made. And it can give 25 to 30 milliamperes. But the catch is that here, the proton fraction is only 30 to 40%. It's not more than that. So out of this 30 milliampere, we get only something like 30% of the, but there is no way to separate out the species because it's a single straight line. So if we have used any bending magnet or anything, or beam filter, then we could have separated out, but we have used, in the LEBT, we have used some collimators which can focus because at this end of the second solenoid, we have a strong focusing and collimator can separate out because it can, for the same magnetic field, the high proton beam can focus very strongly when compared to H2 plus and H3 plus. So that can be eliminated using that. So, and also the emittance which we have measured is around 0.3 pi mm millirad for shorter pulse durations. Okay, so that means what we have done is 1 millisecond only we have operated it and 2 hertz repetition rate. So if we go for the longer pulses, then definitely there is a reduction in the emittance, which can go up to 0.27 pi millirad, not more than that, not less than that. And also now we have made some 2 different electrodes, which is new 3 electrode geometry and 5 is electrode geometry also. Is here and then it developed in the in our lab, and we are characterizing, optimizing all these things. Once we get the required beam and required proton fraction, then we will replace this ion source, existing ion source with that ion source. And then the solenoid is also, this LEBT is a 2 solenoid based LEBT, and use the collimator to, as I told you, to unwanted species. But the emittance at the end of the LEBT was found out to be 0.8 pi mm millirad, which is very high than the design value. So, but the possible reasons, there is the space charge force, which is increasing the thing, or the solenoid also. Solenoidal, if there is a spherical aberration coefficient of the solenoids are involved, then it can increase the emittance. So we have done some simulation studies where 3D field, magnetic fields we have taken, and then we saw that there is a growth in the emittance. And also we have for space, if I want to reduce the space charge compensation studies, if I want to do, I have to inject the gas, and as a result, the gas will be ionized and the electrons should not pass through the RFQ. So for that purpose, we have provision for the electron liberal also. And coming to the next, to the RFQ, it's a 4-meter long RFQ, and then we need around 520 kilowatt of the power to get 68 kV and 1.7, which results in the 1.7. This is the design Kilpatrick limit. Okay, generally CW operations, RFQs can keep less than something like 1.8. So we have kept 1.7 Kilpatrick. And also we measured the quality factor using two different techniques, but the quality factor was almost like 50% of the simulated value. We got it, and we have not investigated the reason right now, but theoretically we are investigating that. But we have used, because we have a margin of we have 1 megawatt Klystron, especially for the RFQ. So we have a lot of margin. So with that, okay, why can't we go with that? So that's why 520 kilowatt we have injected, but at low duty cycle. Okay. So, and it took almost like 2 months to get almost like 50 microsecond and 2 hertz and a power of 520 kilowatt of power. And during this stage, what the thing is, the Klystron, which is supplied, which supplies the RF, that is given by biased with the RHVPS, which is a 100 kV and 25 ampere. But we have, for initial RHVPS has a lot of issues. Dr. Bhagwat ji and Purushottam ji knows a lot of what are the issues we have faced. And this delayed our commissioning things by almost like 1.5 years. So it's a huge 1.5 years from a just commissioning point of view. We have everything assembled, but beam is not coming out, anything. So it took, then we have started, we thought that, okay, that is the issue with the stability issue of the amplitude and phase of the that RHVPS. So we replaced with a pulse modulator, and then we continuously monitor the forward power. This is yellow, and this is the green is the reflected power. We have 2 feeder loops into the RFQ. So 250, 250, or 275, 275. It is designed for a CW of 250 kilowatt it can take. So, but when you do the pulsing, it can go to something like 350 kilowatt. We can peak powers it can take. So we have achieved, based on the pulse modulator as a specifications of 400 microsecond and 2 hertz. So out of this flat top is of the order of 300 microsecond, and we have achieved the RF pulsing at this 250 microsecond and 2 hertz, which is corresponds to 0.05% duty cycle only. Okay, so the thing is that in future upgradations, we want to go for the higher duty cycles also. And then once that is beam comes out, then obviously beam energy and transmission. What is the transmission? Everyone wants dil mange more. So how much is the transmission comes? So that is the thing. Then we have used the spectromagnet, and we have used 3 different techniques. Rutherford scattering also, time of flight using the 2 FCTs and 1 mobile BPM can also be used for the energy. We have done all these 3 measurements and found that they are in good agreement. But the transmission was only around 65%. And as I told you that the emittance at the entrance of the RFQ is 0.8. which we have taken our emittance as 0.2 for our design work. So which is very high, and that leads to the degradation in the emittance. So now, is there any way to increase the thing? So recently we have injected some gas into the LEBT, that is nitrogen gas, and we could see transmission 80% tak improve, almost like 15% there is an increase in the transmission through the RFQ. So this gives a positive sign that we need to understand very much the space charge compensation and what type of gas we have to inject into the LEBT to get more and more transmission to this. So that is what, and fortunately in this, during this exercise, we have not seen any RF noise or anything, or beam losses ki wajah se, any radiation effects. So because 3 MeV, less than 3 MeV, there is no neutron protections. So it is very good for that. So that is why we are fortunate, I will say. Then we assembled the medium energy beam transport. We removed that bending magnet, and then medium energy beam transport line we have installed. And during this time, the COVID has come. So then we have a lot of a margin. During that time, we have done all the things. And during that time also, in between, MSD, we have done some samples, irradiation with 3 MeV beam. And once we have done the operation slightly after the COVID, what the thing is, the operation of this, once we have started irradiated and continuously operated 25 days, 24/7, 3 shifts round the clock. So we didn't have any failure. That was our achievement at the time. But now we are facing some issues. So we have to, and then we have assembled our diff tube linac, which is a 352.1, and this is simple Alvarez type. And it is 12-meter long, so we have made it in 4 tanks. And total 2 klystrons are used for this to power the 4 tanks of this. And you can see here, this is the buncher RF cavity pickup, and this is the yellow one is the RFQ, and these are the DTL cavities pickups. So, but when 2 tanks, 1 and 2 tanks, when we installed and commissioned it, we found the transmission to be almost like 94% from the 1 and 2. But when as I told you, we got overconfident in 3rd and 4th and assembled it. And during assembly, I think so. I mean, we don't know exactly what is the alignment, misalignments has happened. The transmission is only 40%. So we are investigating that issue. And recently we have done beam alignment using the BPMs and other things. What is the offset of the beam and other things? So we found it something like 4 to 5 mm offset is there in the beam. So now we have to take a decision to dismantle the thing and realign everything. That is a huge task. So the management has to take the decision, then we are ready to do that. So, and another thing which we have seen is that there is a RF leakage was noticed in this thing. And this, there is a magic T and the load is connected to this. And these loads are not 1 megawatt loads. They are very crude, lower limit loads which we have. And it is filled with salt water. Okay, and that is, from here, there is a leaks. We have seen that RF is leaking from there. And those spots, at those spots, the field is very high. And towards that, and it is picking up, the electronics is picking up those noises, and then it is giving, signal is inside the noise. So we can't do anything unless until noise is suppressed. So that is what we have seen. And then what we have done is, these loads, we have replaced with a coaxial matched loads. And now, significantly, we have reduced that, but still there is some leakage currents are there. And then also beam diagnostics and measurements we have developed a lot of beam dynamics and as beam diagnostic things. As you know, all that beam diagnostics are the senses of the accelerator. So without that, we cannot get anything, information about the beam because we can't see or we can't touch it. So these are the 2 FCTs readings of the at 20 MeV. And the FCTs we have installed at a distance, 2 FCTs at a 135 point something, 9. And then we measured the time of flights with signals between the FCT1 and FCT2, and it corresponds to 2.2 nanosecond corresponds to 20 MeV. And various diagnostics elements we have developed in-house. LSN scanners, BPMs, button pickups, and also this wall current monitor. And this is the thing which we have used for our misalignment also. I mean, actually, wall current monitors are used to sense the beam currents, but we have used these pickups to see that in which direction the beam is and how much offset is also there. So we have developed those things. And now coming to the RF systems, there are 3 klystrons total, 1 megawatt, 352.21, and 1 klystron is dedicated. As I told you, we have surplus amount of RF power, so quality factor reduced to half. Then also we thought that, okay, it should work. So, and other 2 tanks, 1 to 4, we have used the 2 DTL. And the problem here is that we are feeding from 1 klystron to the tanks 1 and 2, but these 2 tanks are independent oscillators. If the frequency, resonant frequency of these 2 are off, then there is a phase mismatch will come, and that may result in the deterioration of your beam also. So in tank 1 and 2, what we have done is we have used the mobile tuners. So we know what is the frequency detuning of this each and everything by changing the frequency, signal generator frequency. We can find out what is the offset, and we can change we know the tuning sensitivity of the tuners, and we can always tune that. But in tank 3 and 4, they are the fixed tuners. Okay, so we have not used that provision for mobile tuners. We have not inserted, and that we are planning to do that. So in this, one of the klystron, out of these 3, 2 are from CERN, which are age-old I think Purushottamji knows better about these two klystrons. And he's one of the person who has brought those, I think, klystrons to get it to the India. Okay, and one is the Thales, which we have purchased, and but that is creating a problem. And we are seeing that the vacuum is degrading. And klystron is like a black box. We can't touch anything. Okay, so that is why we want to do the reverse engineering, see what happens, but we have to see, we have to take the permissions and all of these things.
Dr. Rao,
So, yeah.
3 minutes. Please.
Yes. So now coming to the LCW systems, which is a low conductivity water, and the main thing is the stringent condition on this is a plus minus 0.1 degree, which we have achieved, but right now we are not needed to use it because the average pulses, duty cycle is very low, average power is very less, so we don't need much. So we have not used it right now, but in future, where we want to go for the higher duty cycles, we need this type of things. And now this LEPA control system is distributed control system, and it is a EPICS-based supervisory control data. LLRF and RHVPS LCW systems are not EPICS compliant, so we are planning to do all these things into the EPICS. These are the coded which are the things which are EPICS compliant. In near future, we will work all the things into that. And now I will just give we got the first beam in August 2023, and then in 1 year we have operated LEPA, and out of this, initially, operation hours, 50% is only the beam. Okay, less than 50%. Rest everything is the subsystems. We used to see what is the problem, what is the things. Several subsystems has given several issues. So only 50% of this, whatever the time is there, beam availability is there. So we have optimization and other things. And the problem is that when we start the operation shift, subsystems, when we get the proper, everything is set, then almost all the operation crew will be tired. So that is a big issue with us, right? But right now we have done all the things. And now, because of this, fortunately, this maintenance schedule we have prepared, and there is a team which will look after all the maintenance, preventive maintenance. And obviously, there are some scheduled maintenance and some unscheduled maintenance, which we have to look for the spares. So we have to make the spares availability also. So we have major subsystems like LCW and other things we have done. And you can see what is the frequency of preventive maintenance and other things. And now also we have done some experimental activities where we have carried out the 3 MeV beam utilized for, as I told you, Rutherford's backscattering experiment, which NPD has done to validate the beam energy. That has in good agreement with whatever the things which we have used using the FCTs and other things. And also we have used this 3 MeV beam for the high entropy alloy, irradiation of this high entropy alloy, niobium. And this leads to the first journal paper using the LEPA beam. And also for copper samples also, MSD is the material science division of PRC. And fortunately, I will say that right now we are only giving the beam to the divisional people, BDAE only, but not like others are giving for the universities and other things there, where you need a very reliable beam and other things. Otherwise, उनका भी time waste हो जाएगा, हमारा भी time waste हो जाएगा. But हमारा इसमें क्या है कि there is no problem in that way. And also 20 MeV also similar RS experiments we planned, and then we saw that there is a huge noise using the surface barrier detector. So that is the point where we found out that there is a huge noise is there. So we have tested it and other things and what is the locations. And also we have done some multifoil experiments using NPD, using titanium foils, and also neutron energy distribution, which we have to give as a feedback to our DSRC. So we have also done this type of thing. And then we also performed the beam optimization studies, where the space charge compensation studies in LEBT, where mainly for the compensation time, space charge compensation time, how fast the space charge compensation can take place using a particle probe, which is an innovative thing. I mean, one of our junior colleague, Pallavi, has implemented it, and it is very useful for us in future to reduce the emittance and other things. Retarding field analyzer. And also beam alignment studies also we have done. And we saw that there is a beam exiting out of the DTL at an angle, and which we have found out to be almost like 4 to 5 mm, because we have seen that some of the radiation at the right side, if you are looking downstream of the accelerator, right side, there is a huge dose when compared to left side. So we have used some quadrupoles also, 2 quadrupoles we have. We tried to focus it, but actually when the beam is off center to the quadrupole axis, then it will try to steer also. So that has reduced slightly, but not much. So we have to we are in the qualitatively we have done this, but quantitative measurements are still, and investigations are in progress we have. And then future upgradations, as I told you, beam duty cycle we want to increase by replacing the pulse modulator with an RHUPS. And this is a big decision which we have to take. And cooling system integration to the cavities also we have to do. And all subsystems will be APS compliant we have to do. And then obviously we cannot use the tuners. So we have to go with the resonance control using the LCW water system for these things and increase the beam availability on target. That is our aim. So for that, we have also done the 2 beam lines. One is the general purpose, and where neutron production and irradiation experiments and biology experiments we can perform. And another one is a RAB beam line for exclusively for the NPD nuclear physics division. And there are several partners involved in this, and IADD and several divisions of DAE. And I would like to mention this RRCAT for their support in giving the RF sources. Without that, no beam. So, and with that, I would like to summarize that LEHIPA duty factor is mainly restricted by the klystron vacuum issue. It's a repetition rate which is only 0.2, and we can go up to 250 microsecond pulse width. Presently, peak current is only 2 milliampere, and average current is 50 nanoampere. Now we got the safety committee clearances, but before that, these neutron beam energy distributions and other things, they want to find out dosages and other things. So that is why we have done the neutron experiment, beam energy neutron energy distribution in the tunnel. And several utilization proposals are also receiving, so we have to investigate that, and then we have to investigate the problems, and then we have to give it to the users. So, and also in final upgradation, there is another upgradation project which we want to do it. So in that, we have a plan to replace these klystrons, all the klystrons with the solid state amplifiers. But there's a catch. The timeline for getting a 1 megawatt solid state is a big issue. So we have to see. With that, I will say thank you.
Thank you, Dr. Rai, for presenting the commissioning experiences of the LEHIPA machine. Now we can have a few questions. Already we are running late of time. So, but we can take just 1 or 2. Yeah, Ladji.
Yes, sir.
You said for upgradation of RF, you are going in for solid state. But 1 megawatt, why? You can go for multiple feeds of 250 kilowatt, no?
Yes, sir. That's what. 250 kilowatts combiner, because we
why combine? You have 4 feeds in RFQ, no? You can also have.
Sorry?
4 feeds, different feeds.
The feed points are there,
Yeah,
but as of now, we have only 2 feed points.
No, you can, if you are going for upgradation, you can go.
The thing is that we have to, as you rightly said, that when the feed points are there, we have to be very careful that phases and other things.
That point is taken care.
That we have to really.
And for your information, 150 kilowatt solid state pulse at 325 is there in RRCAT, so you can go ahead for the production.
Sir, I am.
Contact, I am retired now, so contact the existing RF leaders.
Sir, we are very happy to take it.
Talk to him.
Yeah, sorry, I see you. I had to ask.
No, sorry, talk to Prashant Khare.
Okay, sir.
Dr. Bhagwat. Okay.
Sunny, is there any plan for, like you told, for superconducting, going to superconducting?
Yes,
which will also reduce your
Yes, sir. Yeah, we have a plan, but this is a standalone project. So this is only normal conducting. But the plan for the future is the 40 MeV, MEHIPA 1, which is in Vizag, which is our own state. So we are happy to go there, and we want to implement. And at that point, but the catch is that this between the 3 to 10 MeV, still superconducting is not advisable. Okay, I mean, in the sense that technology is not there up to 10 MeV, we will go for the normal conducting.
SSR0 was designed, right? For
SSR0 is a design stage.
Yeah.
But SSR1, I think Rajiv Mehtaji is the person who has delivered the things, and we can take their expertise for that.
Okay.
For this thing. All right, sir? Yeah, thanks. And SSR2, anyway, SSR1, if you develop the SSR1, it is very easy to develop the
SSR2
SSR2.
already developed, so we
Yeah,
can.
that you people are doing anyway.
Okay, if there are any other questions, maybe discuss during the lunchtime. So with this, I thank once again Dr. Rao and present a comment on behalf of our organization.
Thank you. Thank you, sir. Thank you very much.
Hello. With this, we come to the end of this technical session 1. I hand over the session now to the organizers.
So I request everybody to stay for a couple of minutes. On behalf of the organizing committee, I thank Shri Tushar Tambegar ji for conducting this session. And I request one of our senior members of RRCAT family, Shri Purushottam Srivastav ji, ex-director, Proton Accelerator Group, to please come to the stage and present a memento to Shri Tambegar ji as a token of our love and respect. Now we'll all break for lunch. The lunch has been arranged in Palaj Dining Hall on the first floor of RRCAT Guest House. And we can take a shorter route to the dining hall from DJ Guest House opposite Hanuman Temple. And I request all of you to gather back in this hall few minutes before 2:30 so that we can start the next session by 2:30. Thank you. And good afternoon. I welcome you all to the second technical session of the meet.
Hello,
For this
am I
technical
audible?
session, I request Shri Viraj Bhange sir to please come to the stage and chair the session. And it's my privilege duty to read a brief biodata of Bhange ji.
Am I audible?
Shri Bhange ji completed BE Electronics in the year 1990 from Shivaji University, Kolhapur.
Yes, sir, you are audible.
He then joined BRC Training School in 34th batch. The main areas of research include digital systems and microcontrollers, data equation systems, SCADA for IRFEL MOVE-P, machine vision based system inspection, and automation of lab experiments. Shri Bhange is recipient of several group achievement awards. Bhange ji has more than 65 papers in journals and conferences as author and co-author. Presently, he is Additional Director, Electron Accelerator Group and Division Head of Accelerator Controls and Beam Diagnostic Division. Sir, I request you to kindly conduct the session.
Thank you for kind introduction. Now I request Professor Arup Bandyopadhyay. Professor Bandyopadhyay has completed his PhD in Accelerator Science from Jadavpur University in 2008. His research area of work are online ion sources, isotope separation, room temperature superconducting magnets, IH LINAC, and superconducting quarter wave resonators, room temperature, and superconducting cyclotron. He is recipient of various awards, including of DAE, Group Achievement Awards. He has more than 50 international journal and conference. Dr. Arup Bandyopadhyay.
Yeah, I'm just trying to load my presentation. Give me a minute. আচ্ছা দাঁড়াও 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 ঠিক আছে এখন ওটা লাগবে না ছেড়ে দাও so here sir you have to allow me to share the slide. Somebody has to allow me to share the slide.
Sir, you can share it.
Is it visible now?
Yes, sir.
Okay, okay. Thank you so much. Hello, everybody, and good afternoon. And thank you on the organizers for giving me the opportunity to make this presentation here. And to my belief, this is this topic, that is operational experience on particle accelerators of VCC. A meeting on this topic is probably the first time in our country, and it is very important topic indeed. However, the interpretation of the topic of the theme meeting is different for different people. So I may not be covering the things which some other speakers have covered. It is my viewpoint which should be discussed in this theme meeting. So excuse me if I am not satisfying your requirements. So in my presentation, I want to talk about K30 room temperature cyclotrons, which is also known as medical cyclotron facility, K130 room temperature cyclotron, and also I'll be talking, hello, also I'll be talking about linear accelerators of the RIB facility. Now, This is the picture of the medical cyclotron facility at Chowgoria campus of VCC. This was commissioned in the year September 2018, and
Sir, can
our
you put on your camera?
pardon?
Can you put on the camera?
Yeah, just
Screen it is not visible.
is it okay now?
Okay.
Yeah, so our situation while commissioning this machine was somewhat like this blindfolded man, because the supplier IBA did not agree to commission the machine initially at the cost at which they agreed upon, because of the considerable delay in making the building. So it was made commissioned by VCC scientists and engineers, and the main bottleneck was uh, we didn't have all the elaborate drawings. So we had assembly drawings, and also we have, I think, 18 to 20 cardboard boxes and the packing list. So from that point of view, from that situation, we could commission the machine without much hassle in a very short time. That is itself is a great achievement to my feeling. And that we could do because of our long experience with the other cyclotron machines in our country. So this machine is capable of giving 15 to 30 MeV proton beam. Maximum current it can go, in principle, 500 microampere, but right now 350 microampere. And the beam power is around 15 kilowatt. We have commissioned 3 PET hot cells and 7 SPECT hot cells. And the hot cells were commissioned in 2019. VCC is responsible for the accelerator operation and maintenance, and BRIT is responsible for the radiochemistry, quality control, and supply to the hospital. So we are doing this every day morning, and by 8 o'clock, 9 o'clock in the morning, all the PET isotopes go to all the nearby hospitals within Calcutta. And these are the typical isotopes we supply. The first one is called FDG, or fluorodeoxyglucose. This is the maximum requirement. Then we have another isotope, sodium fluoride. Then we also supply 201 thallium and also 68 gallium. And these are on the right side column. I have listed what are their usages. I'm not going to go much details into this, but the operational experience of this machine is only for 2 years. So far, we have been doing very well, I believe. But the main challenge here is that we have to keep the machine running without failure every day. So even if at night, 2 o'clock, if we find that there is a situation of the machine, we have to take care of that in the night itself, because otherwise the patients will be going back from the hospital all around the city, and that's a big chaos. So in that way, it is a big commitment, I can say. Next, I will come to the other cyclotron, which is the oldest cyclotron of VCC. But before I go to the our experience point of view, I will tell a few slides, show you a few slides about the cyclotron, so that you can correlate what I am going to cover afterwards. So in a cyclotron, we have basically an electromagnet, north and south pole, that is a circular electromagnet, in which the ions get circular motion starting from the center at where the ions are injected, and gradually when they get energy because of the RF field, they come to the outer radius, and near the external, almost at the near the circumference, they are kicked out by some electrostatic field, so that they can be shifted to the external beamline. Now, this cyclotron, this is the room temperature cyclotron I am talking about, has 2 ion sources that I have shown it here also. We have a PIG ion source from the bottom, and from the top we have the ECR ion source. PIG ion source is an internal ion source, so the ion source basically, tip of the ion source come to the center of that center of median plane, Whereas the ECR ion source is an external ion source that is located at the highway of the cyclotron. As you can see, this is the ECR ion source on the highway, and through the shield wall, it is coming, and this is the point you can say more or less the median plane or the center of the cyclotron. So this external ion source, that is the ECR ion source, provides us heavy ions like nitrogen, oxygen, neon, sulfur, etc. And the PIG ion source gives us light ions like proton, deuteron, or alpha. Now, the difference between these two is that this PIG ion source can give us very high current that is required for many experiments, whereas this can give us high charge state and which enable us to accelerate heavy ions, but the current is not very high, current is moderate. This is another picture of the cyclotron magnet. It is an H-shaped magnet. Now, higher beam energy requires higher magnetic field. The accuracy and the profile of the magnetic field is very important. Profile comes into the picture because of the increase of mass as the particle gets accelerated. That is because of the relativistic factor. And the accuracy is very important because if the accuracy is not good, we will lose the synchronicity. Then, as I have said, that using the cyclotron will accelerate different species having different charge to mass ratio. So this profile of the magnetic field is also different for different charge to mass ratio. Now, in order to achieve that, you need lot of correction coils. We call them as trim coils. These are some of the parameters of the magnetic field. The interesting point to note that just to generate the magnetic field, we have main magnet coils, that is one coil. We have 17 pairs of trim coils, and we have 5 pairs of valley coils. These valley coils basically are for introducing harmonics. Trim coils, as I said, to take care of the different charge to mass ratio, and main magnet coil provides the gross magnetic field. So the corresponding power supplies you can see and the rating. So main magnet is 2000 ampere DC. Trim coil power supplies are of different ratings, and the valley coil power supplies are also rated. So you have 22 highly stable power supplies to get the desired magnetic field. So even if there is a problem with one power supply, we cannot operate the machine. Then this is the deflector side, as I told you earlier, that when the beam reaches the maximum energy towards the circumference, you apply electrostatic field to steer the beam to the user beam line. So this is this deflector. So we operate the voltage between these two concentric electrodes, which call beam extraction system or the deflector electrodes. This is the rating of the deflector electrode power supply. Now, as I said that the beam is accelerated by RF, this is the RF resonator tank, and if you open this door, within this door you will be able to see this structure. So this is basically, you can say, central conductor of the RF system, and this is the D, this is a annular structure within which the particle gets accelerated in circular path. So it is one half of the D. And this stem, what you are seeing, is basically here. So this we call movable panel. So by changing the position of this panel, we change the different frequency of operating frequency of the RF, which is required for accelerating different charge to mass ratio. So it is a very complicated structure, and each of these panels have water cooling channels like this shown here. Then we have the diffusion pump also, which is the highest capacity diffusion pump in the country, I believe. These are the parameters of the diffusion pump. 2 such pumps are evacuating the machine, because in a cyclotron you have a very strong magnetic field. So other type of pumps do not work here, like turbo pumps say. So this is the common solution. Now I come to about the operational experience. This is the operational chart I have shown here for the last 5 years. And by the way, this 16th June, that is this coming Monday, we will be celebrating 49th birthday of the cyclotron. So as you can understand, it is a very old machine, But in spite of that, the performance is very good. You can see this is the cyclotron availability. Typically, it is more than 80%. These are the planned maintenance we typically take every year at the beginning of the year so that the cyclotron keeps running. Unplanned shutdown is basically some things which we cannot anticipate, and because of certain reasons, suppose suddenly there is a huge leak which requires total disassembly of the cyclotron to repair, so all the systems are closed. Then that is called unplanned shutdown. And then also we have system breakdown. These are basically small minor problems. For example, one power supply is oscillating, so you have to take care of that. That might take 1 or 2 hours, but the other systems are running at that point of time. So you can say this is the minor operational problem and this is the major operational problem. So this part, that is the cyclotron availability increases, we to the extent we can reduce this unplanned shutdown and system breakdown. For example, the list of the maintenance events last year was in the unplanned shutdown. We have a breakage of RF cavity ceramic that has happened for the second time in 49 years. Then there was a water leak in RF lower D skin. This is the thing I am talking about. And then for system breakdown, there is the electrical power dips, West Bengal State Electricity Board changeover, power supply problems, sometimes there is a communication problem, things like that. So these are the typical things, both the values are less than 10%. We try to improve it, but you have to consider the age of the machine. Now, as I said, that in order to run such a machine, the plant maintenance is very important. So in the next few slides, I will show you what are the major planned maintenances we have taken up. The first planned maintenance which was taken up around 2017-18 was commissioning of a new high power RF amplifier for the cyclotron. Earlier we used to use 4648 based RF amplifier, but then the OEM discontinued its production and there was no direct replacements available. Now, in this frequency range, the solid state amplifiers are very difficult and very large in size. Frequent sparking and glow discharge near the central region of the cyclotron is a common event, so that is difficult to handle by solid state amplifiers. Next, amplifier is directly coupled to the RF cavity. Amplifier's output matching is dependent on tuning of the cyclotron cavity, so it is not a continuous impedance load, can only be verified in situ. And there is no isolation between the amplifier and the cavity, so the issue of the stability and high reflected power you have to handle. So in that situation, we feel comfortable with tetrod-based amplifier, and this is the new tetrod-based amplifier. Few pictures. This is the input matching circuit. This is the RF amplifier with DC blocking capacitor. This is the tetrod tube with the screen bypass capacitor. This is the solid state initial, that solid state driver amplifier. This is a picture of that. And this is actually the amplifier which is coupled directly to the resonator tank. You can see there is no waveguide or something like that in between. Next major update was we changed the electrostatic deflector. The high energy beam in the cyclotron deflected towards the extraction beam line using electrostatic deflectors. Now the surface of the original deflector eroded due to sparks and beam heating. Plus also this deflector have cooling channels, so there are many repairs were done in the cooling channels. So with time the frequency at which the repairing work was required was higher and higher because it has done, there are many repairing patches there. So we thought of changing this thing. So the deflected electrodes have a complicated profile spanning over 108 degree. It operates around 60 to 70 kV. The material is also very special, Inconel. This is the composition. Inconel is used because it has a good strength and trip resistance at high temperature and very weak magnetism property. So this is the ground electrode at the inner radius. The outer radius, you are having the high voltage electrode. And inside this ground electrode, inside the groove I am shown here, you have something what is called septum electrode made out of tungsten, because you do not want the beam to hit the deflector electrode immediately. that major heating of the beam, that is the beam loss, happens in this septum electrode, and it's the most active component of the machine. So during maintenance, this is a major issue. In the new deflector, the brazing joints have been avoided to the extent possible. Wherever applicable, welding joints have been used. Metal hose with copper gasket joints have been used for quick replacement in case of failure. And improved design of cooling circuit and modified septum design will provide us quick turnaround time during breakdown. And this actually we are witnessing for the last 3-4 years. The next upgradation of the de-insert and pull out drive system for RTC. So earlier thing was very bulky system, difficult to handle. It used shaft wheel which was prone to vacuum leaks. Means whenever you used to move, the cyclotron vacuum used to go back. And the new drive system which has been designed, fabricated and commissioned has a ball screw driven mechanism. It is controlled by high torque bipolar stepper motor having small form factor, which helps us to reduce the weight of the total assembly significantly. Position readout is done using linear potentiometer, and also instead of the shaft seal, we have used bellows seal mechanical feed through, so that has improved the vacuum also to some extent. The EPICS-based supervisory control system has been developed to integrate the new system with the cyclotron control system. This is the GUI for the same. The next and probably one of the major maintenance tasks we took is this one, changing of these movable RF panels and the gear assemblies will come. Gear assemblies are basically the assemblies which move these RF panels. So for moving these 1, 2, 3, 4 panels, you have 8 different gear assemblies, and that is driven by a single motor. The operating frequency of the RTC is varied by 6 movable RF panels. Panels are moved using a single motor. Copper panels are cooled using LCW through cooling channels, source of frequent water release. Gear assemblies had the problem of air release. Significant modification of the new RF panels and cooling channels were necessary to suit the existing steel support structure. These are the some of the pictures during the work. As you can understand, it was a very big job, and we could complete it within a reasonable time limit. And this is the gear assembly I was talking about, one of the 8 bearing housing system, and this is how it looks like when assembled to the cyclotron. The next thing happened 2 years back. We had an electrical panel, but then after the commissioning of the cyclotron, many new additions were made, where the power requirements were coming. So from the same panel we are giving. So there are a lot of makeshift arrangements. And also what we found that not all systems require DG support or UPS support. So in the earlier panel, because of the lack of space, two things got mixed. So what was done, we changes the old panel by a new one. Many changes were made during long years of operation. Majority of cases, those are non-documented properly. So we had a very difficult problem of circuit diagram, etc. So the first thing was over a gap. Whenever we used to get a break in the cyclotron operation, we used to make the circuit diagram of the existing electrical circuits. And then only we took up the challenge of removing the old panel and installing the new one. And with the new panel, as-built drawings for both the panels have been prepared for the future reference. These are some of the pictures of. The other one is a major rebuilding of the.
Sir, you have 1 or 2 more minutes.
Yeah,
Please.
I'll take maybe 5 minutes. Yeah, I'll finish as fast as possible. So repairing and overhauling of the RTC cooling tower. This is some of the pictures. This is how it looked like when it was all the old things were removed, and this is the final. So keeping if I want to summarize about the experience with the room temperature cyclotron, keeping an accelerator running for many years require continuous upgradation and addition. The upgradation should not be ignored to provide more beam time. One has to remember stitch in time saves time. Preventive maintenance is essential, which I have not touched upon in my talk. Periodic training of the personnel also is very important aspect. Next, I come to the rear end beam facilitated VCC. This is the schematic diagram. Using the cyclotron I described just now, we can produce RIBs using some suitable target, and then we feed this RIB to the ion source, and then using an isotope separator, we have a RIB of our interest at low energy, and then we use a series of ion accelerators to accelerate them to the nuclear physics energy domain around 1 MeV per nucleon and above. Now, linear accelerators are used for this type of application as a post accelerator primarily because they are high transmission efficiency. And this is how the whole facility looks like. This is the RFQ, this is Rebuncher 1, this is LINAC 1, this is, you can see LINAC 1 and LINAC 2. This is another Rebuncher. Then we go to the next case, this is the LINAC 3. This is another bending magnet. This is the charge stripper here. And then finally we have the LINAC 4 and LINAC 5. We have accelerated beam recently up to the end of LINAC 4. So that is 715 kV per nucleon. And within a few months, we hope to accelerate up to the end of LINAC 5, which is around 1 MeV per nucleon. Now, what is about the experience about this facility? First of all, this is a list. What we have? We have the two RFQ radio frequency quadruples. We have developed 5 IH LINACs. We have developed 5 rebuncher cavities. Now, also we have developed the superconducting cavities. That will be the next phase of commissioning. This is the picture of the RFQ, India's first RFQ, totally built here. And this is the RFQ which we are using regularly, operating in the CW mode till date, starting from 2008. For the RFQ, the main experience is proper cleaning after the machining is very important. And there we followed the SAN prescription. Handling of the vanes is very, in particular during cleaning assembly is very important because each of these vanes, or even if for the other type of RFQ, the vanes are very heavy. So you may be assembling it with a very high accuracy, but if it is not handled properly, it may tend to bend because of its self-weight. Thorough inspection before assembly for irregularity is also very important because no machining can be perfect 100%. So there will be some scratches or some dents. So you have to take it properly, making judicial choice. Alignment is also very critical for any RFQ. There I am trying to show the LINAC cavity. One picture. This is commissioned in 2009. This is India's first IH LINAC type of cavity. Now the main reason why I have showed here, when we started fabricating it, we need to improvise a lot because the plating was not available at that point of time. So initial idea was to make a circular cavity using copper cladded steel, or which is called rolling by rolling of cladded steel. But then that has an issue because while you are rolling and doing it, because of the two dissimilar properties of the material, the bonding may come out. So we made the cavity using hexagonal shape like shown here. So each cladded steel are straight pieces. Here we have the full penetration welding at the joints, and to give the RF connectivity, we have copper bars connected with the spring contact. And another experience I want to share that this whole structure is made of ETP grade copper, and our experience is using ETP grade of copper does not pose much difficulties from RF and vacuum point of view as far as our applications are concerned. Next, I will show you another idea. These are the rebuncher cavities. Again, when we made this, the plating idea was not very commonly available. So what we did, we made the rebuncher cavity using 4 solid copper blocks. This is 1, 2, 3, 4. So 4 solid copper blocks are taken, and then by scooping the interior, copper blocks were made. So this is all what I wanted to share with our operational experience. I don't have any thank you slide, but then I have one slide for a very important person. I want to show it to you. So I would like to congratulate Sri Puntanbakar ji for completing an outstanding career in DAE. Wish you good health and equally exciting next phase of life. And thank you for being role model for so many accelerator practitioners in our. Thank you. Thank you so much.
Thank you, sir. Any question?
Arup Lal here.
Yeah, Ladji, I can see you. Good to see you.
Hello.
Yeah.
What is the status of that RTC upgrade? Is it on now? Is it means shutdown is over? Means RTC is now put into operation?
Yes. Continue
Yeah.
operating.
After
Even
that
right now,
modification.
pardon?
After that modification.
Yes. These modification what I showed you, that is
Yeah.
the modification over the span of last 4-5 years.
Yeah.
So
Okay.
my message will be that do not ignore the modifications necessary and keep on
No, I am asking
accelerating
about the
altogether.
last one, which we were involved. Yeah, which
Yes.
we just saw.
Yes. It's
Okay. Fine.
Thank you, Dr. Bandyopadhyay, for
Thank
your
you, Pantavagaji.
wishes. Thanks a lot.
Thank you.
Any question? If no more question, then let's thank Dr. Bandyopadhyay for nice talk.
Thank you so much. Okay, bye.
From organizers, we will be sending you memento by post.
Okay. Thank you so much.
Thank you.
Okay.
अच्छा moment.
Yes, I can see it. Thank you.
Next talk is on software application for accelerator operation and management by Shri R.K. Agrawal. Shri Agrawal has done his ME from DAVV Indore. His area of work are design and development, commissioning of control system for particle accelerator, Indus 1, Indus 2, Electron Linux, and HIN source. He has also developed high availability data access and data visualization application. He was also, he has more than 35 publication in national and international journal and conferences. Shri Agrawal.
So good afternoon all. Thank you the organizers for giving me opportunity for having a talk on the software applications for smooth operation and management of accelerators. Basically, I have prepared this talk in a little bit hurry, but I have tried to keep it specifically for the participants, younger participants who are here from the accelerator operation community. So a little bit of repetition may happen, but and it would look trivial at some slides, but it would be very helpful for the younger colleagues. So the outline will be, I will talk about introduction, features and functions of the control system software for smooth operation, diagnostics applications in controls, automated operation history database, and web application as in fault finding, and web applications for operation and management. So basically the particle accelerator in Indus, it is very complex machine. We know all about that. It has 1500 signals, analog and digital, more than 20,000 data points in the software which are being logged, and then involve many interacting systems like vacuum control system, RF systems, MPS system, beam diagnostics, machine control and safety, machine safety and interlock system, LCW plant RSS. And in Indus particularly, the operation steps involved are right from microtron and going into Indus 2. So we have to inject in, get the beam from microtron, then inject in booster, and then ramp, and again then transfer it through the transport line to Indus 1 or Indus 2. So there are operation modes are also there involved. So it becomes quite complicated for the operators also. And then there is another step when we go to Indus 2, we have to ramp it. And then pre-conditions are also there that we should be ready for the cycling, and machine should be made ready. And then because of the extended period of operation and round the clock operation of the machine, we have to have, once the beam is filled, it works for 2 days. So any deviation, if it comes, we have to be giving the information to the user, to the operators and the operation crew. I will just skip this slide. This is well-known information. So what I will be covering the features and functions in the control software for a smooth operation. Basically, the machine control application is designed in such a way, with the help of the inputs from the over a long period of time, the inputs have come from operators as well as from our own experience and other experts in the ISCC. This has been improved, and they have been reached to a very good state, I would say. The GUI based operation and confirmation for various actions, so that no wrong action is happening. Any subsystem may be monitored from any of the operator console. That is another feature. So it becomes very easy for the operators to see any of the panel. Then aggregation of the multiple operations, like you have to set one power supply. It is not required. Once you load the file, it will be setting all the power supplies. And then group setting feature, then shut down all feature. These are kind of features which have been incorporated in the control system. MSIS system is incorporated for safety features. Then quick diagnostics features are involved, where we have the alarms and the parameter deviation alarms. Then the status of the health of the control system itself has to be also monitored, where we get the heartbeat and then status of the various layers of the control system. Then the history data logging, so that the machine history is available to us. We can find out the faults at any time, and even we can do the analysis for long-term operation status of the machine. And then beam kill event analysis, event action logs, fast data log, cycling and ramping verification, and sequence implementation. This is the area we have worked on in the last 3 years, last 3 or 4 years, for auto injection off. Once the beam current has reached in Indus 1 to say 124 milliampere, automatically it will stop the injection. Then active and standby mode of operation in the microtron, so that once the microtron is the source, so once the beam is filled in Indus 1 or Indus 2, it is not required anymore. So to save the cathode life, we put it into the standby mode, and then once again required, we put it into the active mode, bringing the system to the minimum values to save energy and also the life of the devices when not required. And then injection permission logs. So this is one of the GUI application, where we see that the operations like load file, the configuration, trends, we can see the status information of all the supplies. At any of the supply, we can see the status information. We can set any supply. We can do shut down all supply, but this is again protected with the password. Then ramping and repeat ramp. I will come to ramp and repeat ramp and the cycling in a separate slide. And then this is the way we have the GUI operation, and any of this GUI can be launched from any of the console panel. Then similarly, the vacuum system, the information provided like this, the DCCT current, that is the beam current, and then the beam energy. As well, we have kind of information like average pressure of the ring. So that's a handy information to the operators, so that they can find out that is any leak is happening, or is there the vacuum is proper in the ring. If any of this, that the average pressure will get affected. Then the Indus 2 beamline front end control application, which is also the application from where the beam ready declaration or beam injection permission is obtained. So this is all state based machine state based operation, that the beam energy beamline is in use. Then whether the GUI, whether the GV0 is to be opened, that is the one of the gate walls which is within the just after the beam, just after the ring part, and in the first stage of the beam lines. So we have this kind of information, and even this stops the operation automatically of the beam shutter opening if the beam line has not been operated for a long period of time or the vacuum is poor in the beam line, so as to protect the beam vacuum of the ring itself. Then one of the preconditions for operation in Indus 2 involves cycling, and the cycling is involving around 117 power supplies, which are to be put up, followed with a cycle like this. And normally 3 cycles are being done in Indus 2, so as to make them history free. So once, to make this history free, and this operation should be very reliable and should not lead to any of the supply tripping or any of the supply not following the reference, or reference is not going properly during this half an hour operation. This takes around half an hour. So it becomes quite complicated for the operators to understand whether it is not, whether it has followed or not followed. So then what we have done is, then this is being a verification scheme of the data is being deployed and it is working fine, and this allows the operators to quickly find out whether the cycling is okay or not okay. So this is done in the form of a we have certain tolerance limit data which we can also update as per the requirement of the power supplies, and the report comes finally after the cycling is over. A report comes in this form. Okay, like power supply 18 is not okay in the status readback and status DAC by ADC, all others are okay, and we can see the detailed report, and the detailed report comes in the form of status information, whether where is the problem, or even the plots of all the power supplies of half an hour duration is available. Similarly, the ramping operation is also involved, and a similar ramping verification scheme has been deployed. And recently what we have done is a low emittance optics were requiring certain modifications in the ramping, so as to allow us the ramping without dipole being getting ramped up. Dipole remains the same, the energy is not ramping, but the other power supplies are to be synchronously ramped. So that has been relaxed, and accordingly the ramping verification process has been updated. And this is also a very quick diagnostics tool in the hands of operators, and the machine shift operation is very easily they can find out whether the problem is or not. So this is one of the case that this is a proper steering profile is being followed for the ramping, and this is a green signal coming from the analyzer that this is verified and it is okay, and this is saying that this is failed for a particular supply. This is the supply number 24 is failing here. So that kind of information is available, and this information all this is logged for all the periods, and one can see it through web applications. So that is also possible. The another diagnostics tool for the health monitoring of the control system is the station status, the field stations which are working, whether they are healthy or not, whether the intermittent layers of communication and the computations are working properly or not. So that comes in the form of API running or not running for various kinds of applications. That the application programming interface is a communication manager that is working or not, whether the station is healthy or not. Like this station is not healthy. Actually, this is a standby station which is kept off. But this is normally, this is the way we used to give the very quick identification. If any of the station fails, a yellow or a red color will appear here, and the operator will come to know, and then they will be able to either take certain steps, what is to be done, whether reset is to be done, or whether we have to power cycle the station, or we have to contact the experts. Then in the similar way, not only the communication healthiness, but we also have in specific cases the status of the IO boards, whether they are working properly or not. In the stations, the control computation stations, whether the IO board is working or not, or whether it is healthy or not, is being taken for the MSIS system, the machine safety and interlock system, which is one of the important systems for machine operation. And the kind of information is available, rather whether the beam ready is there, TL3 shutter. Once the beam is being injected in Indus 2, then the TL3 shutter should be open. After that, the TL3 shutter should be closed. So that status is also being displayed here. And then similarly, the status of various VME power supplies are given here. So Next is the parameter deviation alarm. The objective is to find out whether any of the power supply is deviating from its set reference value over a long period of operation during the injection and in the long period of operation of stored beam. If any of the power supply is deviating, it may lead to a fast decaying of the beam, or may also lead to beam kill. So we have a parameter deviation alarm which is working in both the mode, DC mode as well as ramp mode, and any of the deviation is quickly identified and comes in the centralized alarm panel. Then the machine safety and interlock system, the requirements are very clear that the system should take the decision autonomically without operator intervention. Indus operation crew should be able to identify the trip events. When the fault is rectified, crew should be able to authenticate and acknowledge the fault before the operation is resumed, and the operation should be fail safe, and other critical components should be backed up by redundant protection system. So this is there is a bypass mechanism is also available, but that is followed with a strict regulatory feature. And then the functions are protect critical machine components from overheating, melting, protect the human from high radiation zone. This is MSIS system is a secondary safety system. The primary safety systems, wherever the fast interlocks are required or they are to be they are hardwired. So this is a secondary systems. Trip of power supplies and trip of RF stop the injection, and this is the condition when this is happening. The what feature I was just talking of, that this panel I have already described for the health systems, but this is the MSIS system is providing the station status each card, whether it is okay or not okay, and this is being done every minute. In certain cases, the IO boards, IO contacts are being checked and logged. Another important thing is the fast data acquisition system which has been deployed for identifying any fast trip. The operator can quickly find out that this is available in the control room, and one can see if the beam is getting killed, whether these fast events which are being which cannot be monitored using the 1 second data logging. There we have to have a very fast logging in the and this system is logging at the rate of 50 kSPS and finding out within the 20 microsecond. This is RF gap voltage is decaying fast over here, and then after some time the beam got killed, and there is a delay of around 70 microseconds between the two events. Then similarly, the RF trip beam partial loss. One of the station gets tripped and beam gets partially lost. So this kind of events are now we are able to identify with the help of these systems. And the operator, this becomes at the end a win-win situation for the developers and experts as well as the operators. Operators can quickly find out, and the experts have not to dig up the data and find out whether what has happened. They will be able to find out it very quickly. So this is the kind of display available in the control room where we can see the trends of the various devices which are interfaced to the various signals which are interfaced to the fast DAQ systems, and based on the events, this is on event log. Whether any event is happening, the event is partial kill or any full beam kill or any power supply trip or any RF deviation trip, then this event will log the information into a 2-minute file, 10-second file, and that would be given to the operators. So this data is also now available in the history information. We can retrieve it from the web-based application. So this is the plot from where we can select any of the device, any of the channel, and then we can find out whether what has happened. Now this becomes tedious right now, that 80 channels we have incorporated, and which channel has got faulty for the particular event. It becomes difficult to see all the 80 graphs and then find out manually. So we are now working on the AI model so as to find out that this particular channel, we can quickly directly give that this channel was the culprit, and we'll be able to find out. Though we have done some statistical calculations. From that statistical data, we can also find out to a certain probability of 0.9 or 0.8 that this is the case. Then another feature is repeat ramp. Ramping process itself involves calculation of data. But what we have done is to avoid recalculation and make it fast. All the data is whatever been calculated for the ramping profile that are available. And if no power cycling has happened to the lower layer control station, then we can repeat the whole process. Within a minute, it would be done instead of 10 minutes of calculation of time. So this also allows the operator to make only few clicks with the help of repeat ramp. In case of ramping process, it involves certain steps, 4 or 5 steps, which the operator has to do. But with repeat ramp, they can avoid those steps. So this is, they have to just click the repeat ramp button on the MPS panel, and then they will get, okay, this is allowed or this is not allowed. And then they will get the information, and then ramping will be started. That is what the process is. The next is, we have also given interfaces to other machine applications. I think my colleague Surendra Yadav, Dr. Surendra Yadav might have given a talk. He has given a talk on optimization of booster current, then optimization loop for Indus 2 injection process and microtron beam current optimization. These, so the control system has given an interface to them, and they have he has written in the MATLAB applications and interacting to that. The conditions for the interactions are checked here in the control system. Even if the MATLAB function is
2 to 3 minutes more.
Yes, sir. So this is happening like that. So that operation is also possible, and we can now the Indus 2 beam current limiting I have already described for Indus 1, but for Indus 2 LSSS facility is available after 200. If the beam current is more than 210, it will not be allowing the injection to ramping to be done. And when ramped beam is available, 200 milliampere, more than 200 milliampere, permission may not be given to the BLFE user from BLFE panel to the beamline users. Microtron standby mode I have already described. This is the panel from where we can see this is the standby mode, and these are the two. This is the status of the information. These are the activation two buttons, the standby mode or the active mode. So once it is in the standby mode, then we can click for go to the active mode. So it is doing certain operations like putting off the RF, setting the cathode, setting the dipole. This is certain sequence is there that is to be followed for proper bringing down, and similarly the reverse process is followed for getting the beam from the microtron. So single button operation we have already tested, and it would be deployed very soon, so as to from the booster the beam is available, and then extraction to injection and even ramping. This would be done with a single click of a button, and all the status information will be available. Some preconditions will be monitored, and even the cycling and ramping operation will be performed, and this will be possible with the help of a single button click. So operator will become very useful for them. It will be very useful for the operators in the future. Now I'm coming to the web applications, which is one of the very important part of the control system. And for the operation management, we have varieties of all the historical data is logged, and that historical data in the form of presented in the form tabular, graphical, synoptical, and that is also downloadable in the form of CSV file or GIF files. And data query can be customized, queries can be given multiple data sources से भी आप data ले सकते हैं, microtron का data, and if you want the data from the power supply and vacuum, both of them simultaneously, that is possible, and it is a useful application. The web applications have certain other features which are very useful for the operators for regular operation, like multi-parameter graph display, beam loss probe, data download feature, and 3D trend plotting. So this is the one of the views where we can download the data and view in the tabular format. This is the historical data. You can save it locally, or you can see in the next 1 hour, whatever period you have queried for. And this is the beam loss probe. You just give the information that from the beam loss 0.5 or more duration, then it will give quickly identify that इस duration में ये वाली event हुआ है, and from that event you can find out whether any of the supplies you can get the data of each. Like the events we have find out, these are the events for that particular case, and the deviations in the power supply we can see that this is, and this is saying that this quadrupole has certain change, others have not changed, and it is a trend is available. That trend within plus minus 2 minutes is available, and that quickly identifies this is happening because of this. So beam loss probe is available on the web. So we can, even the operators can use within the control room to find out this is happening. Another feature is multi-parameter graph. The multiple parameters can be used for seeing the information, and this is recently added 3D graphs for the vacuum as well as the beam orbits. And we have the dashboard which are being regularly used by the beamline users. Reports are being generated, and that is available to the users. Reports can be seen, daily report is available in the PDF format. And then now the operation and management web applications. So these web applications involve e-logbook, f-logbook, and e-planner, Indus Online. These are the applications. This provides diagnostics functions for analysis of history data, beam loss probe, MSIS strip analyzer. These are another features, but these are the e-logbook, f-logbook are regularly used. That is available through website. I have just cut down over here. The emailing feature is no more available right now because we are now no more connected to the RRCAT Infonet. So we have the fault log screen in the control room available like this. The operator can fill up the various information, and this fault log report is generated. The experts can see and log in over here the reason of that and the rectification carried out, and even the statistics can be seen from this. And similar, the electronic logbook, now logbook is electronic format available and being used regularly. So this is the, after electronic logbook, the report is generated, and this report is regularly discussed in ISCC. So 2 or 3 more minutes. So this is the operation work plan is displayed over here. This is being fed up regularly by the experts, the machine control, and then the shift crew members, their statistics, everything is available. And Indus parameter display within the control room is also available in the form of large format displays, which is all over also available within the user area. This kind of screen is available where we are giving both Indus 1 and Indus 2. And this is the work plan, today's work plan, standing instruction. This is kind of, this is done here. And if anything is new, it is color coded in. This is also possible to give in the color code form with the formatting information that is available. Then beamline booking manager, any beamline is to be operated, then the booking is to be done. That booking comes to control room, and then there is a whole cycle of operation. That booking is to be done, then approved, and then the approved beamline bookings are given in the, sorry, I cannot go back. So thank you very much. I will just, if it permits me, no.
Any quick question? If there is no question, let's thank
questions. Thank you.
Agrawal ji.
Thank you, sir.
For his nice talk on industrial control systems. On behalf of organizer Agrawal ji, we would like you to present small memento. We are running slightly late. So next talk is on operational experience of E-beam accelerator by Shri R.I. Bhakt Singh, APPD BARC. Shri Bhakt Singh has he is from training school batch 03, 2003, MTech OCEP Park. His area of research work are development of HV power supplies for DC electron accelerator, societal application of EB accelerator in EBC, Kharghar, demonstration of 4.6 MeV LINAC-based Indian cargo scanner, pulse power sources for electronic vulnerability experiments. He is recipient of various group achievement awards. He is executive member of Power Beam Society of India. He participated in testing of superconducting magnets in Large Hadron Collider CERN Geneva in 2006. He has more than 65 papers in journal and conferences.
You will be here, no? Okay. Good afternoon, everyone. Thank you, sir, for giving the opportunity and for the organizing committee of this team meeting. It has been very much interesting to hear the operational experiences of IUAC and various accelerators of RRCAT and our BRC, TFR, various accelerators. I would be touching upon the industrial type of electron beam accelerators, which are ranging from 500 kilovolts to 10 MeV range, and then extending up to 30 MeV also. Changing thing.
This one, left, right.
Left, right. Okay.
Or right.
Okay. So this is the outline of my talk. So there are about 6 to 10 industrial accelerators we have been developing from the scratch in BRC, BTDG and Electron Beam Center, our accelerator pulse power division. So I will be just touching upon some of the aspects or some of the experiences which we have faced. Introduction to DC and RF electron accelerators, operational aspects, and then utilization, various utilization we have tried, process development, demonstration of RF LINACs for industry and security applications, and development of RF devices and components indigenously. This is the important stressing factor for our industrial accelerators in general, and we will be concluding on that, and the accelerator simulator for training of operators. So if you see the spectrum of accelerator, pointer, center button, okay. From 300 kilovolt to 30 MeV, various applications are just outlined you can see from the lowest energy for the surface treatment, which is used for textile, automobiles. You take any of the object which are available, which we are seeing, you take the cables or the car plastics, or take diamonds, you take any of the object which you are seeing, which you may not be aware of it also, even the stent which are put inside the heart, which is medically sterilized by electron beams. And there are so many applications, food preservation and grains mutation and various applications are available using the electron beam. So a need was first of all understood, and in 1990s an initiative was taken in BRC to develop indigenous accelerators and to demonstrate to our fellow people in India. And before we take it to the full and get the full experience, already so many accelerators have been imported also from China, Russia and other countries. So I will be touching upon some of the accelerators which we have developed. So first one, we have developed a DC accelerator, 500 kV DC accelerator based on Cockcroft-Walton generator, and we have inaugurated in 1998. And then we have developed a 3 MeV dynamitron type accelerator, which has been used for flue gas treatment, and then later we have started wastewater treatment also. And then we have switched over to 10 MeV RF LINAC, development of 10 MeV RF LINAC, which are having various applications. And then 6 MeV RF LINACs, which are for the cargo scanners. And this 10 MeV can be used for food, agriculture, and various industrial uses which have been demonstrated. So these are some of the accelerators which we have developed RF, and a fleet of accelerators. This 9 MeV is in presently ECIL, Hyderabad, for neutron radiography, and 6 MeV radiography, and presently we have made a 6 MeV compact X-band LINAC for medical therapy, which is under incubation, and 6x4 MeV is for the dual energy cargo scanning. Without opening the cargo container, we can scan the objects. And presently we are having 1 MeV high power 100 kilowatt wastewater treatment accelerator in EBC Kargar. So to give just a nutshell, when we start thinking about making an accelerator, operating or maintaining or demonstrating, we go through various stages. I have reduced one slide because the audience are from the RRCAT and other community. So you are dealing with the ERB stipulations, and we are dealing with BSc and DSRC, our various committees. And I am very thankful to Dr. Bhagwatji and all the senior mentors who are here, who have mentored us for making the safe and various operational aspects of electron accelerators for industrial application. Some of the points I have lined up here. When during the installation, first we need to make the building, and that is the stage 1, siting and layout approval we have to take. And then second stage we will be for the installation and initial beam trials. And third, we will be taking for the regular operation, and then further it will be under RIT, various regulatory monitoring committees. So when you start installing the system, we are facing with alignment of all the beamline components. In our accelerator, within 100 micron accuracy, we have to align all the components, and baking and vacuum conditioning of high voltage multiplier, high voltage accelerating column, and in the RF LINAC is LINAC cavities. Some of you might have participated in the CERN magnets testing. So we used to train the magnets, and once the magnets are being trained, it will hold that point, holding that current and field. So that is one of the fundamental thing I have understood in the vacuum conditioning or high voltage conditioning of the accelerator and linear column. Just now we were discussing outside about the arcing situations. So this is one of the practical difficulty we face when we are using this accelerator. I have not given the basics of the accelerator. The any charged particle, electron or proton or heavy ion, they need the high electric field. For example, the DC accelerator. This is one of the picture of the DC accelerator. This is typically 1 million volt per meter is the electric field which can withstand. And when you go to normal conducting RF Linux, 10 million volt per meter, a thumb rule. And then when you go to switch over to superconducting, it is about 50 million volt per meter maximum. Up to 100 also some people have tried. And then laser wake field accelerators, you can go up to 1 gigavolt per meter. So this is just a thumb rule for the electric field. So whenever you start conditioning things, we have to take care that there should be no sparking. In some places we need to make spark, like our gas igniter, we are making spark, or in the automobiles we need to make spark. If spark is not there, the vehicle will not move or accelerate. But here in accelerator, we should not make any spark. It should be very silent. So the insulation system, whether it is vacuum or oil, transformer oil, or whether it is SF6 gas or nitrogen gas or solid insulation material, anything, whatever insulation material used, it has to withstand perfectly and it has to be trained also. It should be slowly conditioned, because you may be knowing practically any object which are kept in the air which will be having absorption of moisture, dust, or any projections. So all these things are polished and conditioned and trained to accelerate the charged particles or to hold the electric field which has to be there inside. So this is one of the practical aspect which we have gone through. And once you condition the accelerating column, then beam conditioning, and to get the rated power in stages. So we used to go to the design safety review committee again and again to get the things checked and clarified before going to the high power or the rated powers. And then initial beam trials, safety interlocks check, characterization of beam parameters like emittance, beam size, beam transmission, efficiency, everything. Long-term trials for thermal stability, and then radiation mapping and regulatory clearance. Beam parameters and making the approved SOP, training, all these aspects are coming in the regulatory concerns of the industrial accelerators, and which are applicable for any R&D accelerator, whether it is electron or proton, any accelerator it is needed. So this is one of the accelerator which we are now presently operating for wastewater treatment, which has been already operated for about 2 to 3 hours, 63 kilowatt power, and the various conditioning curves are given, beam power, high frequency transformer voltage, how it is maintaining, and then vacuum condition and various parameters, temperatures were mapped over a period of some time, and then it is taken. So these are some of the parameters of the DC accelerator. This is a symmetrical Cockcroft-Walton accelerator, which is used for textile or tannery water or pharmaceutical waste to reduce the COD, chemical oxygen demand and biological oxygen demand, which has been simulated and done at EBC Kargar. And some of the critical components are accelerating tubes, which are known to the accelerator community, which we are importing right now, and we are making indigenous component. And these capacitors, all high voltage capacitors earlier imported, which are now made in Kerala, in one of the CDCom, one company they are making, and it is employed in our accelerator. And when there is an arcing between the high voltage dome and the accelerating vessel, pressure vessel, that will be sending a high voltage discharge through this high voltage multiplier back to the power supply. So anything in the line power supply gets ruptured. So we have made surge limiting protection devices all through the multiplier, and we have made it operational. This has been tested up to 1050, that is 1.05 million volt and 25 kilowatts for 24 hours. And presently we are using N2 and SF6 95 plus 5% at 6 bar pressure. And moving on to RF LINAC, this is one of the accelerator which are complementing with the RRCAT have already gone ahead to 15 kilowatt power and 20 kilowatt. We have learned lessons basically on the LINAC improvement, RF LINAC, in the cavities between the iris and the meridian, the temperature difference was about 12 to 15 degrees in the earlier time, because we were using coiled water cooling in the beginning times. So later thermal analysis was done and jacketed water cooling was made, and temperature is variation is less than 2 degree. And E-field uniformity is improved from 5% to 0.5% by adjusting the initial cavities. Stop band is reduced to 10 kilohertz. Earlier it was in megahertz. Optimization of beta factor in the first 3 cells, which have improved the capture, bunching and acceleration. Introduction of pre-buncher to improve the transmission efficiency from 30 to 65%, which we are now under trials now. So we are inching towards the rated power of 10 kilowatts. This accelerator is demonstrated for various applications in the electron mode and X-ray mode. And other important component is the RF line components, klystron and circulator and water load. All those RF components are being imported presently. And we are having lot of forums on that to develop it in India. Some of the components are under development. Siri Pilani has taken initiative, but it could not achieve to the required power of 5 megawatt peak power and about 20-25 kilowatts of average power. So we are stuck with importing the device so far. And all other conventional things, electron gun, we are using LAB6 heated cathodes, which are being made in BRC itself. Material Science Group is able to make LAB6 pellets. And they are now going for dispenser type of cathodes also, next stage. They have made some samples. All other things are indigenously made. This is a picture of the 10 MeV RF LINAC control room, and the output dose at dynamic mode and static mode. The first one is 0.1 meter per minute speed and 1 meter per minute. This is one of the standard operational parameter, and this is static mode with different depths. And we have taken the depth dose curve also, and for a given 1 kilowatt of average power, the beam energy is 9.95 MeV, and this is for 2 kilowatt, 3 kilowatt powers. We are varying the peak RF forward power and the peak beam current. And the applications, it is various non-conventional applications. We were discussing with the RRCAT colleagues. It is a kind of unregulated things. So it is not taken FDA clearance or any other thing, but wherever industrial applications are there, so where very fine stability is not needed, you need the dose only. For example, Calandria tubes were corroded in Kakrapar, and these samples were brought because of carbon dioxide corrupted or by the some of the components, and the Calandria tubes were corroded. So that was studied and simulated by this electron beam, giving 650 megagray in various days, continuous 8 hours operations. It was given and conducted. ISRO solar cell has been characterized in our facility. BHCL power diodes for improving the TRR from 100 to reduce the TRR by 50%, and then various agricultural products like pesticides, ketosine irradiation, and food irradiation. Food samples were done for BRC, our local divisions, wastewater treatment, and then some e-waste experiments were carried out, and of course artificial diamonds also were carried out. And this is one of the interesting applications which we are presently going through. This is a national security requirement, whether it is in the airport or seaport or land port, wherever we are crossing the borders, or if you go to a seaport, Jawaharlal Airport Trust or Chennai or Kolkata, or about 200 small ports are there. In all the ports, only 2% of the containers are being scanned because of the shortage of these scanners. And each scanner is costing around 40 crores. One cargo scanner, that is 6 MeV, 6 by 4 MeV making X-ray making machine, small Linux, which need about.
You have 3 minutes.
Yes. Can you play that video? Now presently we are having the challenge of making. You can see here, right? 40-feet container. The driver is sitting and going through the X-ray scanner. But you see that the X-ray point is not yet come. The travel time of this container is total is about 45 seconds from entry to exit. Our HPD person, Dr. Srinivasan, is taking the radiation dose mapping here. So it is less than about 1 microsievert per hour. Okay. We have mapped the entire area. Now only X-ray is starting. After the driver cabin is crossed, X-ray has to start. So this is the challenge given to us. We have to keep the accelerator ready, and within 1 second, the beam should be switched on once the container starts. And once the container is crossed the X-ray line, the X-ray should be switched off. And X-rays should be stable, and it should be running at 400 Hertz PRF, interlaced 4 MeV and 6 MeV. So that means 1 megawatt, 2 megawatt, 1 megawatt, 2 megawatt pulses of magnetron has to be powered. You can come out. So this is some of the RF components are to be made indigenous. Efforts are taken, and the challenges are given here. I'll just drive through. So, yes, sir. Output here. So these are the color discrimination. So we, if you see the thing, as per the standards ANSI N42.26, we have to penetrate the 330 mm of steel we have to penetrate. That has been carried out. And 1 mm wire resolution. Then 4 colors have to be identified as per IEC standard. And it has been qualified EMI, EMC as per this standard. The entire campus in Gamma Field, BRC Trambe. So this is a gantry based scanner which can scan maximum 15 to 20 trucks per hour. But the challenge given to us was we have to make 80 to 100 trucks per hour in the seaport. So this is about the X-band LINAC, and we are using biperiodic on axis coupled cavities. This is one of the important parameter, this S-band klystron, which we are developing in collaboration with RRCAT also, and various divisions are involved in BRC. This is each one component is costing roughly about 2 crores, and which is not available for BRC, for example. And I know for RRCAT also, for everybody is facing the trouble. This is S-band 2856 megahertz, 6 megawatt peak, and 24 kilowatts or 36 or 38 kilowatt is needed as per the present requirement. So for this, the solid state modulator also has been made in BRC. So which is having advantage, we can change the pulse width and all the adjustments are possible with this solid state controller modulator. This is made in BRC, and this RF window also attempts are made to make inside BRC. So this will be joined with this klystron, braced with the klystron at the output window, and electromagnet we are able to make it in India, and the cathode is again an import component which we are having a challenge. So we have made the accelerator simulator for training people, and these are summary of points. DC and RF Linux are developed and demonstrated for few applications in BRC, and we have not fully gone in a plant mode operation. We are demonstrated and R&D. The first field trial or deployment will be happening in JNPT. It has been, MOU has been signed, and for the building construction, clearance has been taken from BSc, and we are proceeding for the next step. Once this challenge is done, within 1 second, we are now testing in EBC. We have to switch on the microwave, because if it is a single energy, single power, it is easy to control the closed loop AFC. But you have to switch 4 and 6 MeV, and you have to keep the resonance point clear. So for that, we have to keep the RF on, and then beam will be switched on whenever needed. So this attempt will be taken shortly. We are testing for 400 Hertz operation, and development of RF components are pursued, and which are told already. Developing and hand-holding potential manufacturers in India. Already Pan Asia, they are one of the potential fabricators, manufacturer of linear cavities. One more vendor also we have identified in Hosur, and other vendors are there in Vasai. So, but 20 micron accuracy, it has to be fabricated, and so these are challenges for manufacturers in India. Enabling E-beam as a complementing technology for gamma irradiators. This is for the Amrit Kal program. As you all may be knowing, we have to switch over from gamma to electron beam Linux and X-ray or electron beam irradiators by 2047. Amrit Kal program and Atmanirbhar Bharat. So we have to work out on this area. Otherwise, we are making it for medical therapy, and 30 MeV will be developed for in Vizag for radioactive ion beam production in collaboration with various divisions in BRC. So I sincerely thank and acknowledge all the people, all the officers who are involved in this collaboration activities, and thanking my senior mentors and the safety committees, regulating authorities, and RRCAT for the opportunity given to share and to learn from each other. Thank you, sir.
One or two quick questions. If there are no questions, let's thank Dr.
Thank you for the nice presentation. I have a small doubt when you have shown this cargo scanner.
Yes.
When it was passing through the detection system. So how do you control the exposure to the driver city?
Yes, that is a very good question, sir. That is one of the challenges which we have posed. how we are controlling it. 1 minute. Here, if you see the specifications, as per AERB stipulated limit, dose to the driver should be less than 0.25 microsievert per scan. We have so far, that is done by some 2-3 stages of collimators, X-ray collimators. First primary collimator is tungsten collimator, which will have a slit of 3 mm slit. Then after that again outside there is a tungsten collimator, 3 to 4 mm. And then the third collimator also will be there, and there will be a very narrow path for the X-rays, and the X-ray scattering in all directions are limited, and driver dose also is limited. And we are going to put radiation monitors. We will be demonstrating it in gamma field first thing. And this design has been made by HPD for the various collimators, so that the scattering is limited to effectively 0.2 microsievert per scan. And for the entire container, it will be 25 microsievert per scan. One container passing through is 25 microsievert, but for the driver, it will be less than 0.2 by the collimators.
Okay, thank you.
And one more point is on the shielding, sir, that LINAC has to be totally shielded by lead shielding, and X-rays and any leakages have to be reduced. That also I have written here. It should be less than, as per AERB, it should be less than 0.1%, but internationally if you go, it is 0.002% Rapiscan is claiming. So we have taken up a challenge of 0.05% in the beginning now, using lead shield. And with this itself, we are able to give the protection to the driver.
Let us thank Shri Bhakt Singh on behalf of organizing committee of team meeting. I would like to present a memento to Shri Bhakt Singh.
On behalf of organizing committee, I thank Shri Viraj Bhangeji for conducting the session. And I invite one senior member of DA family, Dr. Pramod Bhagwat, former head Peletron Accelerator Facility TIFR, to please come to the stage and present a memento to Shri Bhangeji as a mark of our gratitude. Thank you, Dr. Bhagwat. Now we'll break for tea for 15 minutes, and we'll gather again in this hall at 16:25 for the remaining part of this technical session. The tea is arranged on the first floor of this building.
Raja Ramanna Center for Advanced Technology, Indore, a unit of Department of Atomic
Hello, hello.
So, good afternoon. I welcome you back to the last part of the technical session of this theme meeting. I request Shri Jishnu Dwivedi ji to please come on the stage and chair this session. It's my pleasure duty to read a brief biodata of Shri Dwivedi ji. Dwivedi ji holds BE degree in mechanical engineering. He has completed BRC training school course in 31st batch. His areas of research work include 10 MeV industrial Linux, process control for electron beam processing, high throughput electron beam food irradiation, and indigenization of accelerator systems. Some of his main achievements are development of multi-domain electron beam radiation processing technology, qualification of electron beam radiation processing facility, which is working in commercial mode and has been used to sterilize more than 8 million medical devices till now. Development, manufacturing, qualification, and installation of more than 5,000 precision alignment jacks for LHC CERN and new injector microtron for Indus 2. Presently, Shri Dwivedi is Director, Technology Development and Support Group, RRCAT. Sir, I request you to kindly conduct the session.
So, thank you, Amit. The first talk in this session is by Pankaj Kumar on operational experiences of ARPF on sterilization of medical devices. So I invite Shri Pankaj Kumar to make the presentation. So you have 20 minutes. I'll give you a bell 3 minutes before that.
So good afternoon to all of you. I am going to talk about the operational experience of ARPF for sterilization of medical devices. Outline will be as follows. First, chronology of industrial linac development at RRCAT, then ARPF facility layout and e-beam sterilization, and medical device sterilization, advantages of e-beam sterilization, regulatory framework and process control, sterilization protocols, QMS implementation, commercial sterilization services, other e-beam applications at ARPF, other linacs developed by their team at RRCAT, future plans and conclusion. So this shows this chronology of industrial linac development at RRCAT. So in 2017, 10 MeV 6 kilowatt linac was developed. 2020, 2 such linacs were deployed at EB facility at ARPF. 22, commercial sterilization of medical devices started in October 2022. Then in this year, 9.5 MeV 10 kilowatt linac with energy limiting system was tested. And this is specifically designed for food irradiation applications. 2023, 10 MeV 10 kilowatt linac Kirti 1010. This was installed at Microtrol, Bangalore, and it has made operational now. 2024, 9.5 MeV 15 kilowatt linac tested, full irradiation linac. It has also energy limiting system. MOU with ECIL has been signed for co-development of this linac up to 20 kilowatt beam power. This year, just in May, we have reached more than 1 crore of medical device sterilization at ARPF. So till now, this is the chronology of development. So this is the ARPF layout. You see the products come in here, is received, QMS, incoming QMS is done here. Then these products are loaded on incoming conveyor. It goes inside. There are 2 linacs. At present, this linac is operational. Then after passing through this linac from one side, this again comes back and it passes through second side. Then it comes back and the irradiated products are unloaded here in the irradiated product zone. This is the control room. This is the equipment area. And this is the dosimetry system lab, QC lab. These are other offices. These are the 2 linacs shown in the picture. This is the conveyor system. This is the scan horn beam window from which this beam is coming. This is the products going on the conveyor. And this we have regulatory licenses from AERB and CTS CO, Central Drugs Standard Control Organization. It gives this certification licenses for sterilization of medical devices. We have licenses for risk class A and risk class B medical devices, and risk class C and risk class D medical devices are also awaited. Audit has been successfully carried out. Then ISO 9001, 13485 certifications are there. Yeah, CDSO notified body audits are being done, CE audit being done. Processing capacity is 200 kg per hour for 25 kilogram minimum dose for this box dimension. 590 kg along the beam and 430 along the conveyor. 430 along a scan width and 340 along the conveyor direction. And this beam availability is 100% at whenever we have products, we are able to treat the products, operate the machine. So medical devices are categorized in 4 classes depending on the risks involved. A, B, C, D. Risk class A is that which has interaction with outer skin like cotton gauze, dressing material, gloves, sewn air. Risk class B is syringes, intravenous cannula, catheters shown in these 2 pictures. Risk class C is burn healing dressing, dialysis units. This dialysis unit is shown here. Risk class D is orthopedic implants, heart stents, heart valves, etc. shown here. So this sterilization process is a validated process to make these devices free from microorganisms, and it is defined by the sterility assurance level, SAL. So for these medical devices, SAL is 10 to the power minus 6. Like if SAL of 10 to the power minus 6 achieved, then they call it that it is sterilized. 10 to the power minus 6 SAL means 1 in 10 lakhs devices may be non-sterile. Out of 10 lakhs devices, 1 may be non-sterile. So this sterilization is being done by many techniques. First one, that's Gen 1 is steam sterilization. Gen 2 is ETO sterilization, ethylene oxide sterilization, and major part of this sterilization is at present also being done by ethylene oxide. But world over there is a concern on this because it is a cancerous gas. So US Environmental Protection Agency also has put a target to reduce this ETO commercial sterilization by less than 90%. Like it has to reduce it up to 10% of the present level in coming years. Medical devices market size is very huge and it is fast growing. Global market is about US $542 billion with cumulative annual growth rate of 6.3%. But in India, $12 billion with cumulative CAGR of 16%. For medical devices, gamma radiation, cobalt-60, cesium-137 is approved. Electron beam energy less than equal to 10 MeV approved. X-ray beam energy less than equal to 7.5 MeV approved. But recently, these standards have permitted the beam energy up to 11 MeV, electron beam energy up to 11 MeV. So these are the advantages of E-beam. A switch on off device, terminal sterilization, like the sterilization in final packaging, does not leave any residue, no radioactivity induced, safety security concerns are minimal, eco-friendly technology, less product hold up time, like it has very high dose rate. So the products pass very quickly in the radiation zone, unlike with cobalt-60 gamma-based plants in which products have to stay for longer durations in the radiation zone. The quickest processing time, high dose rate and unidirectional radiation, so high utilization efficiency. And here we can customize the batch sizes. Even the small batch size can be treated, not a full batch size, a big batch size is needed. Less material degradation and color change relative to the cobalt facility. A scalable and sustainable technology. So here this LINAC one pictorial presentation is given. This is electron gun, LINAC structure, a scanning magnet, a scanner, and beam coming out from beam window. Product is going on the conveyor in front of it, and the irradiation is done in 2 passes. In first pass, this is the dose depth distribution profile. Shown here also, like when you apply beam from first pass, the half of the devices are sterilized along the depth. Then from the second side, irradiation is done and both doses from both sides are combined and a complete volume is irradiated up to the required range of doses. Medical devices at typical density of 0.15, so it has about 55 centimeter penetration depth in double-sided irradiation. The medical devices we are sterilizing, it is 0.12 and 590 mm, 59 centimeter is our box depth. This is a small video.
Raja Ramanna Center for Advanced Technology, Indore, a unit of Department of Atomic Energy, has set up an electron beam radiation processing facility, ARPF, based on linear accelerator developed at RRCAT, Indore, Madhya Pradesh. First of its kind electron beam facility in the country, it offers electron beam modality for sterilization of medical devices on commercial basis. The facility is accorded with AERB license, CDSCO FDA license for different risk classes of medical devices, and accreditation for ISO 13485 and ISO 9001 quality management system to provide terminal sterilization services in conformance with ISO 11137. Let us get an insight about the radiation sterilization of products being carried out here with process control and integrity. This is the layout of the facility. The heart of the facility is a 10 mega electron volt linear accelerator, which has several advantages over the conventional radiation sources, such as the radiation can be switched on and off very fast, no chemical residues, does not induce radioactivity in products, environment friendly, sustainable, and scalable technology. The plant is operated and process parameters are monitored from specially designed control room in real time to ascertain the integrity of irradiation process. The products are being unloaded and stored in a clean and hygienic incoming product area. The radiation processing is done without opening the pre-packed boxes. Weight and dimensions of boxes are checked to make sure the boxes are in conformance with predefined specifications. The radiation processing batches are prepared and the boxes are loaded onto the conveyor. A unique barcode is affixed to track and identify the product, and dosimeters are placed in a few of the boxes. After quality control check, the quality control person scans the barcode. The operator loads the treatment recipe developed during process qualification dosimetry and starts the machine. The conveyor system transports the batch into the irradiation vault and transports the product in front of the electron beam at a predetermined speed to deliver the required dose. For homogeneous delivery of radiation dose, the product is irradiated from both sides. After processing, the boxes are unloaded into the irradiated area, which is physically isolated from non-irradiated area. Dosimetry is a critical component of radiation processing and is used for product qualification as well as for routine process control. The dosimeters that were placed in a few of the boxes are retrieved to quantify the dose. After that, the boxes are ready for dispatch. That's how electron beam irradiation of medical devices is done. It is worth mentioning that the linear accelerator can also be utilized for food irradiation, gemstone coloration, mutation breeding, and many more applications. We at ARPF are committed to provide all kinds of electron beam solutions to the customers.
So, this medical devices sterilization has to follow many regulations. So, these are the regulations which are to be implemented. ISO 11137, medical devices rules, some guidelines of Indian pharmacopoeia, ISO 13485, and AERB guides or LINACs, then some IAEA guidelines. So, when we have to establish a LINAC for medical devices sterilization, first we have to do the installation qualification, operational qualification, and performance qualification. In installation qualification, we measure and establish the parameters of the machine like beam current, beam energy, scan width, pulse repetition rate, these critical parameters. In operational qualification, we measure and establish the conveyor speeds, variation of doses with respect to the conveyor speed, variation of doses with respect to the currents, and the complete operating range of the machine, including the conveyor, LINAC and conveyor. Then in performance qualification, the complete volumetric dosimetry is done, that whether we are able to provide the doses in a different density of products from minimum to maximum in a dose range. So after this, these qualifications are to be done, then a QMS is to be established, and then we have to apply for the regulatory audits. Then FDA approved notified bodies does audits of the facility, and based on their findings, they provide some non-conformances, areas of improvements, and if those are further implemented, then they provide the licenses. And ISO accreditations are also to be taken, ISO 9001 and ISO 13485. So this is the first stage. After completing this stage, we are ready to invite any client for irradiation, doing commercial sterilization. Then when the client reaches us, with some devices, then for that those particular devices, we have to establish the dose range, dose minimum and dose maximum. Sometimes they have prior knowledge of this dose range, and they want to verify it. Otherwise, sometimes they don't have prior knowledge. Then we give various doses to the different devices. They test it at their center sterility assurance level and other mechanical tests of their devices. Then these dose ranges are established. Then client and product registration is done, non-disclosure agreements are signed. Then in stage 3, the volumetric dose mapping is done, process parameter optimization is done, and the process specification is created. A file is created in which all the process parameters are established, and the LINAC has to be run on those parameters only. Stage 4 is the commercial irradiation, in which irradiation service agreement is done. The company has to take loan license based on our irradiation service agreement from FDA. Then bulk processing of these devices are done. Irradiation certificate is generated and dispatch is done. So this ARPF has these licenses, ARB license, ARB approvals, ISO 9001 is there, ISO 13485 is there. Then CDSCO FDA license for this class A and this class B medical devices. These are the devices covered. These are the different devices covered in A and B. Then recently, just last month in May, CDSCO audit for this class C and this class D has been carried out. And these are very critical audits that CDSCO Mumbai experts came here along with the Indore experts. They carried out the audit, and we are happy to say that they could not find any non-conformance. They actually suggested some area of improvements which we have implemented in QMS, and they have agreed for providing the license, and we are waiting for the formal license copies.
3 minutes. 3 minutes.
So these are the safety interlocks which are in general accelerators, this everybody knows. Plant qualification in IQQ qualification is done, performance qualification is done. We first do the beam alignment trials, then total scan with measurement, then scan uniformity, dose uniformity, surface dose uniformity along the scan width, beam energy determination, conveyor speed versus dose, and many other measurements. QMS has a very versatile like documentation is required. Total 33 number of SOPs, 63 operational SOPs, 85 these forms and formats. Then AERB auditing, our internal auditing, CDSA auditing, vendor audit, all these are to be faced. Process control and quality assurance is met by product specification and tracking, then plant maintenance, system calibration, operation by trained manpower, electronic monitoring of radiation system, and process-based dosimetry. We monitor the critical operational parameters, and you see all these parameters with PRR, Klystron high voltage, average beam current, this conveyor speed, beam scan current, minimum and maximum are well within 3% range. If it is more than plus minus 5%, we trip the machine. And we provide the reference dosimeters on first and last boxes, 2 dosimeters on each side, one first box, one and other side, then last box, this and that both sides. So 4 reference dosimeters, and you see for around 250 batches, these doses of these reference dosimeters are well within the acceptable limits. Then this SAL, sterility assurance level tests are done in NABL certified labs. Commercial sterilization services are being provided to Becton Dickinson for IV cannula and Triveni polymer. This is Gale Seamer, and for PP vials.
Request you to complete the presentation, please.
Thank you. These are different products for which EV qualification has been done. At this 20 October 2022, we released the first batch. This is the photograph. And in May 2025, we have reached 100 lakhs devices sterilization. We have very good feedback, customer feedback from Becton Dickinson. We have done many successful irradiation for seed mutation also, for mutation building, seed irradiation. These are some of the results of color changes of flowers. We have done some color modification gems also. And this is the 10 MeV 10 kilowatt LINAC Kirti 1010 at Microtrol Bangalore. And they are awaiting for FDA license for final approval. It has got type approval also. This is the 10 MeV 15 kilowatt LINAC for food irradiation. And we have plans for installing 2 food irradiation LINACs in a facility which will be constructed in the adjacent area vacant adjacent to present ARPF. This is the layout of that facility. So in conclusion, RRCat has successfully developed 10 MeV electron-ELAC technology, and our e-beam facility is providing medical devices sterilization to the customers throughout the India, from across the India. We have reached a milestone of sterilizing 100 lakhs medical devices. 10 MeV 10 kilowatt LINAC successfully made operational at Microtrol Bangalore. And this 15 kilowatt food irradiation LINAC has been tested, and we are now planning with a food irradiation facility for these twin LINACs at ARPF. Thank you for your kind attention.
Thank you, Mr. Pankaj Kumar. Since we are short of time, if there are any questions, these can be discussed with Pankaj Kumar later on. And on behalf of the organizers, I have the pleasure of presenting you a memo.
Thank you. And at this occasion, I would like to actually put our sincere thanks to Sri Puntambekar ji, who has been instrumental in providing all sorts of help in during the guidance, help and guidance during development of this LINACs, and the Executive Management Authority for ARPF during all sorts of licensing and audits. And till now, actually, without his support, it would not have been possible. So sincere thanks to you, sir, from the team.
Anuja is there? Yeah. So the next talk is on operation of ILU electronic accelerator at Vashi for more than 3 decades, expanding the applications of EV radiation technology by Dr. Tanu Jha, BARC, RTTD. So request you to complete the talk within 20 minutes.
Yeah.
I will give you a bell 3 minutes before that.
Okay, sir. Thank you. So very good evening, everyone. On behalf of ILU EBA team, I am presenting some of the highlights and experience in operating the accelerator for more than 35 years. It is in operation. So I have joined the department in 2014. So after that, some developments and some previous experience that I have been gathered and told from my seniors, I will be sharing with you. So it is currently, the accelerator is located in BRIT Vashi campus, BRC Vashi complex. Previously, it was in Trombe. So this is our ILU beam window, and the dimension of irradiation window is 80 centimeter by 8 centimeter. It is in stationary mode. When the accelerator is operating in conveyor mode, then it can be extended very high. And this is first commercial EV accelerator of India. It is procured from BINP, Russia, Budkar Institute of Nuclear Physics, Russia. And as I said earlier, that from 1988 to 2000, it was in BRC Trombe, and from 2001, it is in BRIT complex. So currently, we have the operation license valid up to 2026 April, and our section and division is headed by Dr. Virendra Kumar, and the machine is now being operated by
Ravindra Patkari, and we have a supporting staff, Mr. Vittal Srimangle. And as you all may be knowing, Mr. Kadir, S.A. Kadir, he just retired last month from the facility. So he was the most senior employee of our section. So, and I am taking care of the radiation safety aspects of the accelerator, as well as I am involved in some research and developmental works. So just some basic slides I'll be giving, and from operation point of view, I think as I am in IRCAT and you people are, I mean, it's not only in India, internationally experts, and you have a competency in operation and maintenance and developments of accelerator based technology. So I'll give more emphasis in the application part of the EV accelerator. So as in from mode of operation wise, it is DC and RF based accelerator. Our accelerator is RF based accelerator. And from energy point of view also, it can be categorized into three parts: low energy, medium energy, and high energy. So our electron beam currently it is operating in 3 to 5 MeV range. So it is in medium energy accelerator. It has been upgraded. So it was in ILU 6 previously. It was operational in 2 MeV range, 2 MeV. And now it is upgraded to 5 MeV, and it is operating now 3 to 5 MeV energy and 15 kilowatt power. So maximum beam current it can give is 3 milliampere. And this is the accelerator, and this is the design layout. You can see from here. So in a single cavity, it can increase the energy of electron to 5 MeV, and it is a RF based accelerator. This is our conveyor. This is a power roller conveyor, and we have a mesh conveyor below the beam horn. And lanthanum hexaborate is used as electron gun in this accelerator, and we have titanium foil and beam current, as I said earlier, also 3 milliampere. It is an industrial type EV accelerator, and it has two type of accelerator. And the main component of the accelerator, some of the main components are vacuum. So vacuum system is very important to for operational of the electron beam accelerator. For accelerating tube and extraction system require very high vacuum. So we have sputter ion pump as well as turbomolecular ion pump to generate the vacuum of 10 to the power minus 7 torr in that range. And we have then cooling system is also very necessary part of this accelerator. DM water as well as forced air cooling system is there in our accelerator. We have a titanium foil of 50 micron in a concave mode to withstand the vacuum and to withstand the electron beam facility. So now this electron ILU 6, as I said, that was machine. This was up to 2013. The machine was in operating in 2 MeV energy and 20 kilowatt power. So beam current it could generate was 10 milliampere average beam current. So using this technology, there were many development and technology development done from using this parameter. But the problem was the energy is low, so penetration was a factor. Penetration was not as much as we expected, but the beam current was high, so dose rate and total dose was very high. Using this thing, the machine was operated for last 22 years, and specifically the technology that was targeted was curing, coating, polymerization, cross-linking of polymer, degradation of polymers, and coloration of diamonds and many other precious stones. These 4 or 5 applications were mainly attained from ILU 6. So this is a very basic slide. I don't want to spend much time in this. This is like advantage and disadvantage of radiation processing compared to other conventional techniques. And this is how radiation, high energy radiation reacts on a material, radiation processing. As we are talking about radiation processing, so we should have a small brief idea about what it does with the material. If we irradiate some matrix, what it does. So mainly it can interact with the material in 3 main ways. It can degrade the matrix, it can do cross-linking to the material, or it can do grafting. If we add some other second kind of molecule into the matrix, it can do grafting also. So mainly these 3 are the applications of EV radiation processing that is possible. So like you see, the low dose application, if you see the cereal grain, meat, irradiation, medium dose applications are mainly medical product sterilization and modification of polymers. And high dose applications are cross-linking and degradation of polymers and irradiation of precious stones. So first, we will focus on high dose applications. Like I said that it was in 2 MeV machine, it could generate very high dose rate because beam current was 10 milliampere. So in a very small time, it could give very high dose, but penetration was not as required. 2 MeV to maximum 1.1 centimeter it could go. So that was why
the feasible applications that we targeted is application in cross-linking polymer wires and cables. So whatever radiation technology can generate it mainly does improve the property of the polymer by improving the thermal stability, chemical resistivity, it improves the mechanical property. So wire and cable industry, it got very good wide application, and if you see the number of electron beam accelerator used in commercially, they mostly have application in wire and cable, and number of accelerator is increased. Now it is more than 50 electron beam accelerator commercially operating as on 2024 or 2025 you can see. So it has increased very sharply, which was 4 to 5 accelerator in maybe 1995 or 8. In 2014 it was 19 electron beam accelerator. Now it has become more than 50. It crossed the number of 50 plus accelerator in India. So mostly they are doing wire and cable cross-linking, gemstone irradiation. These are the main applications they are targeting. As now medical sterilization application is coming out, so number of electron beam accelerator is expected to increase very soon. So these are some of the products that has been irradiated using the electron beam accelerator. So these are the plastic parts, wire and cable, these are O-rings, gaskets and vacuum shaping tube. So from the product itself, you can see that the thickness of the product is not very high. So this can be irradiated using our ILU6 condition, and very high dose is needed. So as the machine is operating in 10 milliampere average current, so in a very short time, very high dose can be given, and that has been done, and these products are, these technologies has been transferred, and very good mechanical property as well as thermal resistivity has been imparted on the polymers. So you can see this is unirradiated polymer. If it is heated, it is got deformed, but after irradiation, it can retain its shapes. And these are the some of application of heat sinkability of the polymer. Irradiated and partially cross-linked polymer can have heat sinkability property, which is having very high industrial value. Then you can see this is a one setup of wire and cable irradiation using ILU6. It also has very good property improvement, and these are the some of the vacuum moldable sheet and heat sinkable tubes which are being irradiated, and these technologies are very well proven nowadays. Then another application of this low penetrating but high dose rate giving electron beam accelerator is degradation of polymer. PTFE is very common polymer, but it is very stable, it does not degrade after use. So to recycle the polymer and to add some value on that, degradation of PTFE is very widely practiced application of electron beam. Apart from this, this PTFE degradation, very recently some degradation and recycling of viscose pulp, reclamation of vulcanized butyl rubber, these technologies are also coming in near future. And this very widely spoken application of electron beam accelerator of this diamond irradiation and precision stone irradiation. So it generates color center into that, and it is increases the value. So these all are done using our ILU6. So that is 2 MeV and 10 milliampere average current. So now in 2012 and 13, this ILU6 has been upgraded. So you can see this was 2 MeV, now it has become 5 MeV and 15 kilowatt power. So beam current is now decreased from 10 MeV to 3 MeV, and now the power rating and the condition of the machine, it is now operated in 3 to 5 MeV and 9 kilowatt power. So beam current now is even less. So the parameter and the operation condition we have tuned to increase and develop newer technologies using this. So now as the machine is operating in high energy, so penetration is high, but our beam current is low. So dose rate is very low now. So this we have used in the next slide. It will be very clear how it is used to develop newer technologies. So major modification during the upgradation is done is the shielding. As energy is high, so shielding has been improved, and then there was RF cavity is changed, and some part lead shielding has been added, and some minor modification is done in high voltage power supply, scanning system and control circuits. And this is now operated using lab window software, and this is the gateway, how it is shown in the software. And different pulses we monitor using the oscilloscope, anode voltage, grid current, energy and beam sensor is there, and we can navigate on the electron beam whether it is working or not. Then these are the interlocks that are there in our accelerator: high voltage, RF, vacuum, cooling system, ventilation, and these all are interlock position. So before switching on the machine, this has to be sequentially followed to ensure better safety. And major safety aspects that are involved in this is radiation safety, and persons should not be entrapped into the cell area as it is very high dose rate electron beam is a very high dose giving radiation, so it generates huge amount of ozone. So protection against the noxious gas is also an important factor that we should take care of, and efficient protection and safety against all any other conventional industrial hazards should be taken care of, and we should be always focusing on human safety, equipment safety and product safety during the operation of accelerator. And these are some of the alert and caution system that we have to indicate and to avoid any kind of emergency situations. And we have an option of manual shutdown, and there is a scram button also for any kind of emergency. The machine can be switched off immediately. There is a interlock with the delay entry in the radiation cell, as there is a ozone and noxious gas present. So there is a 15 to 20 minutes of time lag there to avoid any kind of human intervention into the cell after irradiation. And the operation machine operation is done as per the SOP, logbook, operation maintenance and frequent checkups and repairs is being done. Effective maintenance is done, periodical, routine, preventive and breakdown to ensure the health of the machine so that it can be operated and function very smoothly. And there is quality assurance for safe operation, there is quality assurance for dosimetry as well, product dosimetry as well as personal dosimetry. Personal dosimetry, there are TLDs allotted to every employees, and RSO is taking care of that. Well documented procedure and radiation the data of every quarter is monitored. There are area monitor device as well as handheld monitors always in backup to ensure if there is any changes in dose or dose rates in the control room or nearby area, that is very precautiously monitored. And these are the some of them. Now I will discuss some of the new applications from generated from the upgraded EV. So as I said earlier, now the energy is high, so penetration is more, but dose rate is low. So using that, some sewage water system which is having some pathogen and bacteria has been irradiated, and research has been done systematically, and it is seen from this figure that in control there are some colony forming bacteria, but after irradiation of 0.75 kilogray, there is no sign of any bacterial growth in the water. That means even less than 1 kilogray, all the bacteria and pathogen has been killed. So this was not possible if the machine was operated in a very high dose rate, because we need only few kilograys to kill the pathogen and bacteria. But we should also have a proper penetration as well as homogeneous distribution. That is why high energy is required. So we have played with these parameters, and then this is a textile dye. This is a very common problem, especially in Gujarat and industrial belts area. The textile dye is a major problem. So a lot of water can be used for agricultural purpose also because of the presence of the dyes. So these dyes can be degraded by using electron beam radiation, and this is also needs very low amount of dose. 3 to 5 kilogram of total dose is needed for dye degradation. And some of my previous speakers also shown these slides, like the irradiation of food products, frozen meat, frozen foods that can be irradiated using electron beam. Those are also needing 10 to 15 kilogram total dose and can be irradiated. Sterilization, as my previous speaker has spoken a lot about sterilization. As you see, the sterilization has not been propagated much using the 5 MeV machine because of the penetration. Penetration is more compared to 2 MeV, but 5 MeV is not penetrating enough to homogeneously sterilize the medical product. That is why I think RRCAT has developed 10 MeV machine and is working very fine, very nicely. And then another interesting application that has evolved recently, that is radiation induced grafting, electron beam induced grafting. So grafting means it is one material will have a basic property, and onto that we will attach some kind of monomer into the base polymer. So the base polymer's intact property will be intact, and the new monomer that is being grafted on the polymer, the basic polymer will have the average of these two property. So we can get benefit of the two system in a single system by using radiation grafting. But problem with electron beam was that dose rate is very high. So at very high dose rate, what happens? A lot amount of energy is deposited into matrix. So the monomer gets recombination and it forms homopolymer. That is a major problem with electron beam. That is why most of the grafting literature, if you find that it is done by using gamma radiation, because dose rate is very low. But here we have tried to utilize electron beam for radiation grafting as well. And these are some of the potential application of radiation grafting: adhesion enhancement, surface wettability modification, preparation of polymer blends and composite, antibacterial material, sorbent for selective separation can be achieved using radiation induced grafting. So this is one work that is done in our group. So this we have prepared cotton based super absorbent. So the cotton, as a natural cotton, you know, it is absorb water and all both. So after radiation assisted grafting, it has become super hydrophobic. Hydrophobic means it will repel water and it will absorb oil. We have added one oil philic molecule onto that, the base cotton, and using radiation, electron beam radiation, the molecule has been grafted. And after modification, if you see, this is a water drop. This is pure cotton. This is, so water drop immediately it absorbs water. So this is hydrophilic and oleophilic also. But this is modified cotton. It does not absorb water, but it absorbs oil. So it is super hydrophobic. And it is chemically stable also. In a very harsh chemical, it can sustain very harsh chemical environment. And this is the modification process, you see. So we have used that molecule I said into the system, we soaked the solution and then we have irradiated under the electron beam. This is our ILU6 conveyor, and in this packet the cotton, gauge cottons are there in the solution, and during irradiation we have given a certain amount of total dose, and we have optimized the processing parameter. We operated the machine in such a way that per pass it is giving 0.125 kilogram of dose, very low amount of dose. We put the frequency very less, machine frequency very less, 2 Hz machine frequency, and very low beam current.
3 minutes.
Yeah, sure. So very low beam current, it could go very low dose rate, and that is why we could achieve the grafting, successful grafting using this EB accelerator. And then after modification that I said, it does not absorb water but absorbs oil. So now this absorbent prepared using EB accelerator is being used for separation of oily liquids or any hazardous oily compound from water surface. It can absorb from surface, it can absorb, this blue dyed is the oily compound, it can absorb from under the water also. So this has various applications in our DAE as well as in various industries, and this technology we have patented, Indian patent, we got grant in 2020, and the technology, many industries have taken the technology and it is under process of commercialization. And using the similar pattern, we have prepared a super wettable cotton fabric, any kind of fabric, the shirt we are wearing. So as monsoon is coming, I think you should all appreciate the importance of super non-wettable fabric. So water drop will not pass through the fabric. So this is also done using this our electron beam accelerator. It's a similar kind of work that the cotton, but the thing is that matrix is different and some different parameters also we have to play with the parameter to attain successful grafting. And this we got Indian patent in 2024, and this technology is, we are about to put the technology with TTCD BRC. And then we have modified jute fabric, hydrophobicity we have generated, and that is used to separate microplastic. In the water, this figure if you see, these are the blue dyed microplastic. Microplastic is a very burning problem of today's world. So you see any disposable cup, we are drinking tea, even our plastic water pipe, PVC, nowadays the metal pipes people are not using, we are using PVC pipes. So after a certain time, 5-10 years, it degrades, the pipe, it generates PVC microplastic comes to our tap water. So microplastic is a very burning problem. So we need to separate microplastic from water, and this super hydrophobic jute, this can separate this microplastic from water, which has been prepared using our ILUEB accelerator. And this technology is under incubation, and maybe in coming days it will be ready, and this paper is communicated, and yeah, done. So I thank and I am acknowledging our Associate Director YK Bharadwaj, our Head Viri Kumar, S. Rai Chaudhary, and our team members for their contributions, and thank you all for your attention.
So thank you, Atanu. If there are any questions.
It is actually Russian terminology. So normally it is industrial linear unit.
Industrial linear
unit.
Unit.
Yeah. So
I thought it is irradiation.
Some Russian term is there.
You explained about the PTFE scrape irradiation process.
PTFE, yes, sir.
Yeah, for scrape also you have explained about.
Yes.
What is the preparation required, because scrape come in any form, the what and the addition, you are adding some powder into it also.
No, powder we are not adding. We are using the scrap.
Scrap only.
PTFE scrap only we are irradiating.
Okay.
Because PTFE, as if you see the pure PTFE, that is very costly material.
Yes.
We don't need to degrade that. That is having very good property.
Yes.
Once it is used, there is no value in that. Then it becomes scrap, and the scrap we are irradiating to make it powder.
Okay.
So any form, it can be any form. But film means it will be thin enough. It should not exceed the thickness. That is our main concern. If it is thin, any form, it can be irradiated.
Okay. Thank you.
So if there are no more queries, let me thank Atanu and request all of you to give him a good applause. Because he's a young man and he will carry forward the accelerator programs in BARC. On behalf of the organizers, I have the pleasure of presenting you a memento.
On behalf of organizing committee, I thank Shri Jishnu Devadi sir for conducting this session. And I request a senior member of RRCAT family, Shri Mahen Lad sir, ex-director, Proton Accelerator Group, to please come on the stage and present a memento to Shri Jishnu Devadi ji as a token of our gratitude. Thank you, sir. Now, as the last leg of this theme meeting, we'll have a panel discussion. I'll request senior members of our fraternity to please come on the stage as the member of this panel. I request Dr. Rajiv Mehta from IUAC, Dr. Pramod Bhagwat, Shri Purushottam Srivastav ji, Shri T.A. Pundampekar ji, Shri Mahendra Lad ji, and Shri Jishnu Devedi ji. I request Shri T.A. Pundampekar ji to take the role of the moderator of the panel discussion.
Thank you, Amit. First of all, I take this opportunity to thank ISPA for supporting the organization of this theme meeting, because what I believe or understand that this is the first time a focused theme meeting has been arranged on the specific topic of accelerator operation and what are the issues, challenges in accelerator operation. It has provided a very good platform to all there are wide variety of accelerators which have been represented in the talks by the respective experts, and very good presentations we heard on what are the issues faced by them and how these were solved through the various improvements, upgradations, or the technologies which were developed. So, in my view, when we talk of operation, it is okay. Accelerator operation, we should differentiate between the accelerator which is we are say just for R&D purpose we are developing in the development phase. But once an accelerator goes in a deployed for user, for some user, end user may be a researcher or industry or medical application, then what matters is how reliably the accelerator is operating and providing the beam, the intended beam, to the final target with the required specifications and quality without any breakdown. So in this sense, I feel that the accelerator, once we are now, as we have seen that the number of accelerators are increasing, which are now deployed for various applications. So we as accelerator designers and developers should also take care of the various reliability aspects while designing the systems, the quality and this thing, so that the uptime of the accelerators is kept high. And if any fault comes, it should be rectified in a very short time. So those type of provisions have to be kept in the design of the accelerator itself. Because this we have understood by operating large, so many years. For example, I am personally associated with Indus operation. We know that users, there are beam lines. Say today there are 18 user beam lines on Indus 2. And a user from a university, some student maybe coming for 1 week for doing an experiment on the beam line. And if we are not able to provide the beam during that period, then his whole effort or trip in coming to Indore, coming to RRCAT, and that thing will not be, he will not be satisfied with the outcome of that. So in that sense, same thing applies to, we also had experience of our industrial accelerator. We have gone through a long route of R&D model up to the industrial scale model and what problems come and how we have solved them. So these things have to be kept in mind, I think, whenever we talk of the operation, accelerator operation for some end use. And I hope that this platform will continue, this forum of discussion among accelerator centers. So such theme meetings arranged every 2 years or something like that can be arranged. And maybe with more participation, because there are a large number of, this time I think we have tried to, organizers have tried to get our from Tata Memorial Center, so that
frequency.
So, but somehow that talk could not materialize because of some reasons. So maybe in the next, we can also invite the medical fraternity or medical doctors who use accelerators, because in therapeutic application also, mostly we are dependent on the imports. So finally, we have to have indigenous accelerator, whether it is electron, proton, or carbon, or whatever particle as per requirement. And that is also one of the important thing, because that is also needed by India at this time. So with this, I also take this opportunity to compliment and thank the organizing team of this theme meeting, because they have, I have seen the whole organizing team has worked tirelessly throughout to organize this and make all the necessary arrangements. We have seen that all the arrangements were very nice, and it was a success. Thank you. Maybe I will request now one by one to give their, so we can start with Dr. Bhan.
Thank you, Mr. Putampekar. Actually, I'm quite happy to be here today, because I am a retired person. And normally people forget a retired person. So being a ISPA member, I got a mail. Okay. And then I decided, okay, I saw the mail and then organizing committee convener is RK Sahu. तो मुझे ऐसा लगा कि अरे ये तो हमारे परमाणु नगर के हैं, इनसे बातें क्यों नहीं किया जाए। उसके बाद की स्टोरी मैं नहीं बताऊंगा। You are intelligent enough to judge. But I am here today and I am quite happy that you called me here. You means RRCAT called me here. So thank you for the same. Now, my entire life was in I spent entire my life in particle accelerator. And of that life, at least 80% was in accelerator operation. So that's what I was quite excited to come here. So to all my young colleagues who are sitting on the last few rows, you know, accelerator operation is quite challenging. And every day you learn something. Oh, yesterday that problem was there. Today is different problem. Day before yesterday that problem was there. So you must take it as a challenge and you should enjoy that. Like a musician enjoy his instrument when he's playing every day.
Microphone
He
देखना
enjoys
उधर.
it. So you should enjoy
Microphone.
it.
Speaker.
And why I am saying so?
Select another speaker.
Because when I joined and when I became in charge of Peloton Accelerator facility at TFR, I found that quite often accelerator operation group used to complain, you know, accelerator operation is quite monotonous. Then I used to ask him, what is monotonous in that? It is so challenging. Every day some one or other problem is coming. But slowly those problems are solved by other techniques. And so it is quite challenging. And it is very important to, as Guntam Bakerji said, to organize this kind of meetings on accelerator operation and learn from each other's experience. And I remember Mehta is around here on the stage that the IUSC when came, then they got a lot of feedback from us on Peloton accelerator facility, and that is how that facility came so fast with our experience. And one aspect which probably we should have included in that, that is the safety aspect of this accelerator, particle accelerators rather, because accelerator safety is quite important. And I was chairing the BRC Safety Council Accelerator Committee for a very long time. And I have seen all accelerators working. Their safety problems are different. And at a personal level, I have learned a lot from that. And as on today, I am again a member of a ARV Safety Committee, and quite often RRCAT accelerators come there. So it is nice to organize this kind of meetings, and I have told today SPA president that he should organize a accelerator safety committee meeting like this, a theme meeting or something like that. And to know that accelerators are working very well, it's a very proud moment for me. And let me tell you very frankly, every day when we take a evening walk in Parmanu Nagar, Dr. P.D. Gupta is always with me. And very often, Indus 1 or Indus 2 rather, topic comes and he is very proudly tell many stories and the way Indus 2 is working. And when I saw it today, then the performance of the Indus accelerator, in fact, it is a very proud moment that all accelerators of our DE facility today, whatever so that performance is superbly high, and that is very encouraging, this one. Even during Corona call, people have run the accelerator. That is very important thing. And that means people have that passion for the run the accelerator and so the accelerator operation. So I will not take much time, and I wish ISPA and RRCAT should organize such theme meetings quite often, and I will be happy if you invite me. Thank you.
Regarding operation of accelerators, if we break down the challenges that we face while operating the accelerators, we can broadly put them in two categories. One is challenge of workmanship or quality of the machine, basic machine or the system that has been built. And second is the availability of spare. So quality of workmanship of the system can be improved by putting in place a quality control, quality assurance procedure during manufacturing or design. And when such problems are faced by our intensive efforts, we are able to overcome them. But the problem of spares, specifically which are imported, those problems are really very hard to resolve. And specifically for accelerators operating in public domain, if one of the imported system fails, it is a very unmanageable situation. And with the increasing geopolitical situation, as you can expect, as the India becomes more and more prosperous and powerful, there will be more and more challenges in importing things. Other countries sometimes may give you things and sometimes may not give you things. So it is very important that we have very high capability to develop our own spares in case we face uncertainty in the supply. So in case of Linux, for example, industrial Linux, or also our injector Linux, we need to have our own clistrons. And if we depend on imported clistrons, the operation may always remain uncertain. And development of these type of components, clistrons, for example, or any other component like a circulator, or they actually require a multidisciplinary approach. So the teams who are leading these developments have to have a very intensive, open interaction and a program of developing several iterative prototypes. Because any such component when we develop for first time, it will not meet all the requirements. So we have to have these programs behind our accelerator operation programs. So this is the dilemma we face when we put accelerator in public domain, that if we lose a klystron, because last year we lost 2 klystrons quite unexpectedly. So that is a big problem, and the suppliers, the manufacturing industries who have shifted to electron beam processing, their business will be affected very adversely, because medical devices or even the food products, when we start doing, the whole approval process for those products for Indian market as well as for export to other countries, whole food processing chain has to be approved by the regulators. And one process in between getting not available will be a big problem. So we have to be immune to imports, import problems, import embargoes. So that is one point I wanted to mention.
Yeah, I agree that indigenization is very important, particularly those components for which we are dependent on import. And I think during impact also, I suggested that in the next impact, particularly if we can have one session on the efforts or developments of this indigenization of import components, that will be nice. We'll do a focus session on that particular thing. Thank you for your, I request Larji to.
Yeah, so much have been said on all these aspects of accelerator. So I agree with Jishnu and whatever Tusharji has told. I will also mention the same thing that I will first give a brief about the theme meeting. So I congratulate the organizer Sahuji and the team for organizing this theme meeting on operational, because this is a very, very important topic. The development, what Jishnu has also did, development in the lab is I think 50 to 60% job only. But running and putting into the 24/7/365 is really challenging. And for that, the prototype system should not go into the machine. So we should have a prototyping qualification process in place, which is necessary for our future machine like HBSRS and future Linux. So vendors should be developed for all the, in addition to indigenous component development, which is a very, very important and critical field. So I think this we should have open mind now, because whatever we have done in past, we should slightly improve as far as new machines, HBSRS like, which have a lot of demand from the user side. Because now if the government puts money, then they expect also in terms of whatever contribution, scientific plus others also. So I think that is a very, we should always, and during the talks, I have seen that now all the subsystem people are very openly putting all the upgradation mode, and they are continuously doing it. So we all have the technical competency and expertise, but vendor development is another part which we have to further take up further for all the machine. So this is what my takeaway for all the subsystems people, so that our machine will operate reliably. And of course, redundancy should be one of the also in design features. We should take care of that also. Yeah.
Thank you, Larji. Yeah. Dr. Mehta.
ओके
श्रीवास्तव जी,
मेरे लिए बहुत मतलब सौभाग्य की बात है कि मैं आपसे विशेषकर ऑर्गेनाइजर्स और साहू जी को धन्यवाद देना चाहता हूं कि मैं फिर से जुड़ पाया। और इंडस सबसे पहला मेरा कार्य था माइक्रोटॉन से लेकर के आगे तक, जो मैंने सीखा अपने सीनियर से और आपस में सहयोगियों से, उसमें एक इम्पॉर्टेंट चीज जो है वो है, देखिए ऑपरेटर का जो एक हम कहते हैं कि ऑपरेटर जो है, जो ऑपरेट करता है, प्रचालित करता है, he is a very important element of this complete chain of accelerator or any operation, any of this subsystem. And of course, first operator is the developer. Unless he operates it and proves it, it will not come to a stage where it goes into 24/7 operation. Or best operator is nature actually, without asking for any sort of credit. Nature does the operation. You can see the systems, you can learn from the nature how perfectly the system operates. Everything falls in place and goes on. Apart from operation, you have the maintenance and then also the upgrade. Because more and more operators tell you because I have seen the difficulties in the initial stage of our operations, Linear operations also. This team has done an excellent job. The Indus team also has done an excellent job. Congratulations to all the accelerator developers and operators at all the centers of India, IUSC, BRC, RRK, and all. Not only that, I'm missing here the defense and space people. They are also deeply using this, and recently I had interacted with them. So maybe next time we can involve them. We had been helping ISRO and defense for their machines. Whenever they needed any help, we had been helping them for the non-destructive testing of rockets as well as for many other things which I cannot tell here. So that is also important. So maybe some of the sessions we can involve them as users, and maintenance, of course, is a very important part. I think we should also think about that. Not only in that, whenever there is a failure, and, then it is a blessing in disguise. And that recalls, I recall that this Russian Lineage we had, it had failed because of electron gun. We struggled a lot. Finally, we made an electron gun, and I'm very happy that it has come to a maturity level here. So these are the examples where the operation of a machine actually and its maintenance calls for an upgrade. And then we, of course, you have seen Indus 1, then Indus 2, now Indus 3, HBSRS. So these are the stages depending on the applications. And I'm very happy Vineet is here. He has done an excellent job in making that mega science vision document. In fact, he was the person behind all these efforts. So I would request you to again go back to that mega science vision document, and most of these things are incorporated. When I say accelerator science, technology and applications. So applications actually incorporates operations. Application in itself has the operations, because unless you operate, you cannot apply. And applications also are emerging for strategic thing like जिष्णु जी अभी बता रहे थे, आत्मनिर्भरता बहुत जरूरी है. क्लाइस्टॉन अगर हमको अभी चाहिए तो मुश्किल से मिलता है, उसमें लीड टाइम भी बहुत ज़्यादा है. एंड इंटरनेशनल सिनेरियो क्या चेंज होता है, इसी तरह से नायोबियम जैसे है. Choksey ji has done a good job. His team has done a good job with NFC to develop niobium with NFC now. Triple R more than 300 is made now. But it is not sufficient. Vikas has done a lot of efforts on that. So these are the examples. When you do this, transfer it to the next level. And ऑपरेटर के लिए मेरे को कई बार मेरे को पूछा भी जाता था कि सर मेरे को ऑपरेटर ऑपरेशन टीम में क्यों डाला है. That is the only way to really understand what should an accelerator do. अगर मैं कोई एक्सेलरेटर बनाता हूँ और वो ठीक से मैं ऑपरेट नहीं कर पाता या एप्लीकेशन उसकी नहीं हो पाती, तो इट इज ऑफ नो यूज. सो वी हैव टू स्टार्ट फ्रॉम द एंड एप्लीकेशन, कम बैक. एंड एक और मेरा सजेशन है, what we are lacking now, we are inching towards the most advanced accelerators now in proton as well as in electron. So we have to now slowly concentrate on QA QC. I don't see a sort of a team which is dedicated to quality assurance, quality control. Like when you see these aerospace, ISRO, they've got ESS Penta 5, they've got MIL standards. So we have to evolve these standards so that there is a endurance, sustenance, and obsolescence. These things are also becoming important for all accelerators. For example, when you go to ADS, we have to be 100% reliable, because that will be the accelerator has to be operated. And apart from that, cost effectiveness is also important. Suppose you make an accelerator which is 3 times, 4 times costlier. Of course, it comes as a stage in the next development, like 10 MeV Linux, it has now become quite cost effective and we are able to compete. So that also has to be taken in the design stage, and also during operation also it becomes important when you go for understanding the subsystems, because for an operator it is the only front panel which is there, but he has to also understand, and I'm sure because of this TQLC, all our operators are well trained and they know the subsystems also. So it is not only the screen you are seeing, it is the vacuum system, their efforts, RF system, magnet, power supplies, all those things are very important. So these are some of my thoughts which I thought to share. And an excellent job done here by the team to organize this team meeting, and it should continue. Thank you.
I think the last, most of the things have already been informed and we all know. So yes, this is a very important aspect. And I just wanted to have one, it's when we go to any doctor for this, doctor just do some diagnostics first. And then they go say, okay, this could be the issue or this could be the problem. In our case, operators are the people who know from the down the time, what is the problem? And they, in fact, in our IUAC, almost 60 to 70% of the problem are solved at their level only. They don't even report to those people. So they are the one. My request would be to the organizer, next time when we have this kind of meeting, maybe we have more involvement of those people who are actually doing this and working out it. And that'll be a major treasure. And sir, one request for sir, you, I think with your like ocean of knowledge you have regarding operations, if you can come out with like a memory down the lane, I mean, some kind of a book or something, it'll be certainly useful for the most of the people who are here. And one more thing I would like to add, normally I have seen, because IUSC, we have hosted 3-4 such meetings. And once the meeting gets over, it becomes very, very difficult to have a follow-up on this. If we can create some kind of a digital book or somewhere where people can put their ideas, their issues, which can be accessed by the people in general, then it'll be more useful. And also one suggestion, if like sir has mentioned, if in impact, if we can have a one dedicated session, maybe half a quarter of session or something only on operational aspect and challenges, that makes it more professional and more this thing rather than having once in 2 years. So that's my suggestion. And thanks to the organizers. It is one of the topic which has been least talked about and the most important and critical. And I can tell you from IUC perspective, morning I shared the slide. If you are spending 5 lakh, 3 to 5 lakh rupees per 8 hours, any loss of even an hour is a very, very critical. So the operation maintenance and as we do, I know you must be doing it, all lab must be doing it. We have a technical calendar where we make a preventive maintenance and everything. Preventive maintenance is the buzzword. If you follow that, I am sure we will not have much problem with any operational aspect. So if you have a technical calendar, follow it to the T's and I and see, most probably things will be sorted out at the beginning itself rather than taking it to very long this thing. Thank you, sir.
Yeah. Acha. Okay, okay. So, Thakurdaji, hello. Can you hear us?
Yes, Mundamega.
Yes, yes. Boliye, sir.
Yeah, I listened to almost all the talks from right from the beginning till this session, the ongoing session. It was quite informative, and I learned a lot about the recent developments too. I was given to understand some time back that a dedicated crew is being trained for the purpose of operation and maintenance. I'm not sure whether that has materialized or is the training process still in progress.
This, the current batch is going on. It is almost like all the things are completed. Yeah.
Okay.
So it's
Okay.
going on.
I personally feel that, I mean, the operation crew, I mean, as we call it, should be given some, I mean, good amount of responsibility on the maintenance part as well. I guess that has been, I mean, taken care of, and more responsibility I felt should be given to operation crew in the sense that the design team, I mean, shouldn't, I mean, interact every now and then over minor problems with the operation crew and come over to the site and interact with them. I mean, it's as if without their intervention, nothing can proceed. I mean, operation crew should know a lot about, I mean, how to do the maintenance and how to go ahead. In fact, the decoupling part of the design team from the operation team should be taken up in full swing so that the operation crew can do a job with minimum assistance from the design team. Every now and then, I mean, design team doesn't have to come and do the repair job, or like that of course is to be supported by good amount of documentation. A set of documents which is complete in all respects should be available with the operation division, an operation and maintenance division, rather, I don't know what the name right now is, whether it takes care of operation only or it takes care of operation and maintenance.
Same
Both.
operation division, yeah.
Okay, so with minimum assistance from the design team, if the operation crew can do the job in a relatively intimate, I mean, it cannot be decoupled entirely. I mean, there has to be an interaction. So, like, for example, when you do machine experiments, through the results of machine experiments will have to be passed on to the operation crew, to the design team as well, so that both gets benefited and on both sides the information gets updated. I mean, the summary of what I meant to say is operation team should work with minimum assistance from the design team. The
Yes.
maintenance, the repair, for that, I mean, lots of preparation is needed. First of all, there has to be good amount of documentation so that, see, I mean, without assistance, if the documents convey something to the operation crew, this means the documentation is nearly complete. If for everything, I mean, they need to call the person from the design team and say, sir, this is what I could not understand. I mean, that means that the documentation is not complete. So one
Yes,
should
sir.
cover.
We agree. Actually, for this, the first thing, as you have mentioned, documentation is the first thing that has to be there. And in my experience, I have seen, including me, because I am not other than that, we make the systems, design the systems, deploy the systems, but we lack in the professional documentation, which can be used by a third person who has not designed the system to maintain the system. So maintainability requires that. So definitely that aspect is there. So we have to take care of the documentation.
When you say a third party, I call the operation crew members as the third party.
Yeah, yeah.
I mean,
Means
if
not
you
the
go
person.
through the
What I mean
document,
is
if
some person other than who has designed the system that he should be able to maintain.
and for that there has to be a, I mean, good stock of the spares. And spares, I mean, doesn't have to be at component level. It can be module level also,
Module.
card level also. For example, if some fault crops up, I mean, to solve the problem, I mean, there has to be some guideline given during the training of the operation crew that if such and such things happen, you need to change this particular PCB. Not, I mean, one doesn't have to take the PCB out and change some component, a particular component. One can simply change the PCB and then go ahead. So probably that would help in course of time.
Yeah.
But it will take some time because first of all, documentation is a must. Then spares in the form not just of components, spares in the form of cards, modules. So if anything
One-to-one
goes bad,
replacement. Yeah, definitely.
yeah,
We'll take all the
that's right.
solutions and definitely this will be very helpful in
So
our future
basically, it's a
accelerators because
graduate,
there,
trying
as
to
we go
graduate
ahead,
from,
we
it's
have
trying to
to
graduate from
go for
design
these
level
things.
to operation. I mean, trying to decouple design,
Yeah,
R&D, and the operation part. So I
definitely.
thought, I mean, people would talk more about the operation aspects, but not much was covered on that. And it was, today's presentation was basically a mix of R&D and operation. It was okay. It was good. I mean, in fact, I mean, that is something we do expect. But when we talk about operation per se, I didn't see any, I mean, for example, uh, problems really one came across during operation. No, nobody talked much about that. So that, I mean, what problems one faced and how the problems got solved, uh, whether they had
Yeah, yeah,
adequate number
definitely.
of
See, this
spares.
is what I feel is this is the first of such kind meeting
Yeah.
that we have arranged. And in this type
It
of,
was well arranged.
for
No,
example,
no,
I saw in the presentation by Dr. Mehta also, he presented
yeah,
very nicely some problems that were faced and how
yeah,
they were solved, which led to improvement. And some other also upgradations also were spoken. But definitely, we have to focus more on the problems and the solution because that is what the knowledge sharing.
yeah.
Except of only
What
bringing
we have
out
done
very
has to be
good
passed
part,
on to the
good
operation
evenings.
crew. That's
You
what.
have to bring what problems we are facing and how those things are solved. So definitely,
Yeah.
as we go, when we do the next edition of such theme meeting, these things will be given more importance and more focused things will be given. And as Dr. Mehta also suggested that operator, the person who is operating should also be there. He should be involved in this type of team meeting. So those things also will take care. So I request the organizers to take note of this. And with this, I thank all the panel members.
Any comment?
Shri Gurnam Singh ji also is there, I think, online. Is there any comment or anything? Okay, I think. Okay.
Fortunately,
Seeing you all.
can IUAC can host the next
This is very good
meeting.
Yeah, it's good. Very nice suggestion. Yeah. So with this, I thank all the panel members for their thoughts and views, which will definitely help the accelerator community to go see when we go for the next generation accelerator projects. So these thoughts and this views will definitely help us in making more reliable systems, more rugged systems. So with this, I thank again all the panelists and hand over to organizers. Thank you.
I request all the panel members to remain on the stage for the next ISPA function. And I request Shri Vijen Prasad ji, President ISPA, to join the panel. And I invite Dr. Vikas Kumar Jain, General Secretary, ISPA, to take the function further from here.
Thank you, Amit. So we will start the ISPA function. मेहता साहब शायद आपका फ्लाइट है इसलिए जल्दी जाना है, नहीं तो रिक्वेस्ट था कि आप भी यहाँ पे बैठते। भक्त सिंह साहब हैं क्या यहाँ पे अभी? शायद वो निकल गए। तो BARC से राव इज देयर? अच्छा, ओके। So sir, this function is especially for Sri T.A. Puntambekar ji, and ISPA would like to felicitate him. I request Sri Jishnu Dwivedi ji for giving a brief about Puntambekar ji, and then we'll start our function.
Okay. Good evening. So Tushar Puntambekar ji is my batchmate, and I have known him since August of 1987. And of course, all of you know that he is a very talented person. And talent is not a word which, because my mother tongue is not English, so I may not be able to use the right word. But मैं हिंदी में उसको कह सकता हूँ कि उनमें कई अनोखी प्रतिभाएं हैं जो सामान्यतः कम ही मिलती हैं, और उनकी जो एकेडमिक कैपेबिलिटीज या अचीवमेंट्स हैं, उसके अलावा की मैं उन प्रतिभाओं की बात कर रहा हूँ। किसी भी विषय पे बहुत सोच विचार के अपने निष्कर्ष पे पहुंचना, और हमेशा किसी भी अगर अपन उनसे बात पूछे तो उसके पीछे उनके एक सोचा हुआ एक कारण होता है जो उनके निर्णय को प्रभावित करता है। और कोई भी निर्णय मैंने उनको कभी अकारण लेते हुए नहीं देखा, और उनका जो कारण होता है वो हमेशा एक समाज की भलाई के लिए या सर्वसाधारण की भलाई के लिए उसमें एक उसका अंग होता है जो एक थोड़ी रेयर क्वालिटी होती है, हमको एक्सेप्ट करना चाहिए कि बहुत सारे लोग बहुत स्वार्थी होते हैं, पर उनमें उस चीज का बहुत ही कम उसका वो एक भाग है। दूसरी बात मैंने उनको देखी है कि बहुत ही एक्सेसिबल है। अगर अपन किसी भी दूसरे व्यक्ति से तुलना करें जिसमें इस तरह की प्रतिभा उपलब्ध होगी, उसको आप एक्सेस नहीं कर पाएंगे या वो अपने चारों तरफ एक दीवार बना लेगा। तो ये करने का इसके लिए एक साहस की आवश्यकता होती है और इसके लिए आपके अंदर ये एक विश्वास होना चाहिए कि हर ह्यूमन बीइंग में कोई ना कोई गुण होता है, इसीलिए मैं भी सबके साथ समान व्यवहार कर सकता हूँ। क्योंकि ये समझ कहने में सामान्य लगती है, हमको धर्म ग्रंथों में भी सिखाई जाती है, पर उसको सीख बहुत कम लोग पाते हैं। और उनके साथ कोई भी व्यक्ति किसी भी विषय पे अगर एक डिस्कशन करने बैठेगा, तो कितना भी यंग व्यक्ति हो, उनके साथ बराबर वो बहस कर सकता है, तर्क वितर्क कर सकता है और एक अच्छे निष्कर्ष पे पहुंच सकता है। ये एक बहुत ही बड़ी बात है। उन्होंने जो अच्छे गुणों का हम लोग परिचय देते हैं, उन अच्छे गुणों को उन्होंने समझा है, उनको आत्मसात करने का साहस दिखाया है और उसको हम सबके सामने प्रस्तुत किया है। तो ये उनके बारे में कुछ व्यक्तिगत गुण हैं, जिनको मैंने वर्षों में देखा है। दूसरी चीज उनकी जो है वो है हमारी एकेडमिक की जो उनकी प्रतिभा है, वो हमारे बैच टॉपर हैं। और बैच टॉपर जब भी कोई होता है, तो आजकल तो उतना कंपटीशन बीएआरसी की जॉब के लिए होता नहीं है। हम लोगों के जमाने में बहुत कंपटीशन होता था और उस कंपटीशन में मुझे ऐसा मोटा मोटा ध्यान आता है कुछ 230 240 लोग कुछ होते थे और एंड देवर ऑल एटलीस्ट आप मान लीजिए कि उसमें 30-40% तो होते थे, काफी मेहनत से पढ़ते थे और बाकी अपन मान भी लें कि चलो 60% लोग नहीं करते थे। तो उस 30-40% में भी जो कंपटीशन, टफ कंपटीशन है, उसमें सारे देश से लोग आते थे उसमें। एंड आई थिंक ही वाज फ्रॉम इंजीनियरिंग साइड एंड उनका जो परसेंटेज में अंतर था वो भी एक सिग्निफिकेंट अंतर था उनका। तो उनकी जो प्रतिभा, मैंने उसको व्यक्तिगत रूप से जो देखा कि किसी भी अगर डॉक्यूमेंट को देखते हैं तो उनकी रीडिंग स्पीड बहुत ज़्यादा है और जब किसी भी डॉक्यूमेंट को देखते हैं तो बहुत कुछ कैप्चर कर लेते हैं जो हम लोग पहली बार पढ़ने में कैप्चर नहीं कर पाते हैं और हमें 2 या 3 बार पढ़ना पड़ता है और कई बार उसके बाद भी वो बताते हैं कि उसमें ऐसा लिखा है। फिर अपन देखते हैं तो फिर दिखता है अपन को कि हाँ उसमें ऐसा लिखा है, जबकि वो उसको एक बार में पकड़ लेते हैं। तो ये इतने गुणों के बाद भी एक्सेसिबल बने रहना, मैं उसको सबसे ऊंचे पायदान पे रखता हूँ। क्योंकि जनरली लोगों के अंदर थोड़ी सी अकड़ आ जाती है और वो एक छोटापन दिखाते हैं। उन्होंने इसको बहुत ही साहस के साथ हमको ये दिखाया है, हमारे सामने उदाहरण पेश किया है, हम सबके लिए अनुकरणीय है और मैं उनको बहुत ही आदर भाव के साथ आगे के जीवन के लिए शुभकामनाएं कहता हूँ।
सर इसी के साथ हम तंबेकर जी के लिए श्रीवास्तव जी से रिक्वेस्ट करेंगे कि एक सैपलिंग उनको भेंट करें। प्लीज ब्रिंग दिस सैपलिंग। थोड़ा लोगों को जल्दी है इसलिए हम थोड़ा कट शॉर्ट कर रहे हैं प्रोग्राम, बट अभी ऑनलाइन वाले भी लोग थे जो बोलने वाले थे, फिर शायद उन्होंने बोला कि अभी टाइम हो गया है। अब मैं श्री लाड साहब से रिक्वेस्ट करूंगा कि वो भी एक और, आज सर आपके पास बहुत सारे सैपलिंग होने वाले हैं, एक सैपलिंग पूरा मैं रिक्वेस्ट करूंगा भागवत साहब से कि वो भी एक सैपलिंग सर को दें। सर एक जैसे इसलिए बुला रहे हैं ताकि ये नहीं लगे कि वो रिपीट हो रहे हैं। इसके बाद सर सभी लोगों से रिक्वेस्ट है कि वहीं रहें, और इस्पा का एक छोटा सा प्रोग्राम जो पहले इम्पैक्ट के टाइम छूट गया था कि हमें जो अवार्ड विनर्स हैं इस्पा के उनको चेक देने थे, उनको सर्टिफिकेट तो हमने उस दिन दे दिए थे। तो आज मैं रिक्वेस्ट करूंगा कि 1 बाय 1 आप लोग आएं और पुंताम्बेकर सर और बाकी यहाँ पे जो गणमान्य व्यक्ति हैं उनसे ये चेक ग्रहण करें। श्रीमती रिंकी उपाध्याय, she won the best posted award on AC power distribution of 40 kilowatt 650 megahertz solid state RF amplifier. श्री SV कोकिल, बाकी जो बाहर के RRCAT से बाहर के हैं उनको ऑनलाइन हम उनका अकाउंट नंबर ले लिया है, उनको ऑनलाइन देने वाले हैं। श्री PK साहनी, कोकिल जी का था डेवलपमेंट ऑफ सेकंड साउंड बेस्ड क्वेंच डिटेक्शन डायग्नोस्टिक सिस्टम फॉर SCRF कैविटी बीइंग प्रोसेस्ड एट RRCAT। और साहनी जी का है रेडिएशन डैमेज in insulation of quarter pole bus bar at Indus 2 RRCAT. श्री अजय कुमार सोनी, इनका है डिजाइन एंड डेवलपमेंट ऑफ बेलो इंटीग्रेटेड बीम पोजीशन मॉनिटर्स एंड कंपैक्ट BPM फॉर इंफ्रारेड फ्री इलेक्ट्रॉन लेजर सेटअप एट RRCAT. डॉक्टर आकाशदीप गर्ग, अच्छा अभी थे वो, आकाशदीप गर्ग जी का है डेवलपमेंट ऑफ इंटरफेरोमीटर बेस्ड इलेक्ट्रॉन बीम साइज मेजरमेंट सिस्टम फॉर इंडस 2 RRCAT. इसके बाद यंग इंजीनियर अवार्ड जो कि स्प्लिट हुआ था बिटवीन BARC और RRCAT के बीच में, उसके लिए श्रीमती कृति पाठक RRCAT यंग इंजीनियर अवार्ड. And Sri Ram Prakash. Ram Prakash ji has bagged 2 awards. First is the best student poster on RF loading effect of field emission current in SRF cavities. And he stood first in the student poster award. Second and very important, and this is the only award and not shared, that is Young Scientist Award. So big round of applause for Sri Ram Prakash for bagging 2 awards. Thank you, sir. Now I will just read. I request everyone, if in 2 minutes, if you be there, then we will start the felicitation. On behalf of Indian Society for Particle Accelerator, ISPA, we are delighted to felicitate Sri Tushar A. Puntambekar for his extraordinary and enduring contribution to accelerator community, with the special emphasis on his groundbreaking work in electron accelerator. Sri T. A. Puntambekar, OS, Additional Director, RRCAT and Director, Electron Accelerator Group, was born in Indore on 1st July 1965. So his birthday is coming after 18 days. He did his schooling from Bal Niketan and Sri Vaishnav Vidyalaya, Indore. He studied engineering from GSITS, Indore, and obtained his bachelor's degree in electronics engineering from DAVV, Indore in 86. He joined 31st batch of electronics and BARC, and he stood first rank among all the discipline. He joined RRCAT as a SOC in August 1988 and worked in the field of accelerator beam diagnostics. He led the beam diagnostic team in various capacities for planning, design, development, installation, and commissioning of various beam diagnostic systems of Indus 1 and Indus 2 synchrotron radiation sources, such as beam position monitors, beam profile monitors, beam current monitors, beam current monitors, then tune measurement, feedback systems, transverse multi-beam feedback system. He also contributed immensely in the commissioning of these Indus 1 and Indus 2 machines. Later, a number of upgrades in the beam diagnostic system of Indus 2 has been carried out under his guidance, which have enhanced its performance. He was designated as Associate Director EAG in October 2019 and then Director EAG in Feb 2020. He was designated as Additional Director RRCAT in July 2024. He is a life member of Indian Society for Particle Accelerator, Indian Nuclear Society, and Indian Society for Radiation Physics. He has more than 90 publications in journals and conferences as an author or co-author. He is the recipient of Homi Bhabha Prize for securing first rank in the 31st batch of BARC Training School, DAE Scientific Excellence Awards, and many group achievement awards where he was as a team member. Now I request Jishnu Dwivedi sir to felicitate him with Sol. श्रीवास्तव सर आप श्रीफल दे दीजिए. Now I request President ISPA, Sri Brijen Prasad ji, to give certificate of ISPA, and I also request him to read the certificate.
So I'll read this certificate. Indian Society for Particle Accelerators is pleased to felicitate Sri Tushar A. Puntambekar, Additional Director RRCAT, Director Electron Accelerator Group RRCAT, for his outstanding lifetime contribution in the field of particle accelerators.
With this, we have come to the end of the function. I request everyone to raise. Yes. सर के सब तो हमने वैसे सुने, फिर भी सर अगर कुछ बोलना चाहेंगे तो आप छोड़ेंगे थोड़ी.
First of all, I would like to thank Indian Society of Particle Accelerators for giving this honor to me. और इसके साथ ही मैं मेरे मित्र श्री जिष्णु द्विवेदी जी का भी आभार व्यक्त करता हूँ। उन्होंने बहुत ही अधिक मेरी तारीफ की है, शायद उतना सब कुछ थोड़ा अति की है तारीफ, तो मैं इसके लिए उनको धन्यवाद देता हूँ। और मैंने एक्चुअली जो भी मैंने यही कहना चाहूँगा, क्योंकि अभी समय नहीं है, ज़्यादा बोलूँगा नहीं मैं। मेरे लिए जर्नी ये जो थी मेरी बहुत मुझे इट वॉज ए वंडरफुल जर्नी फॉर मी. I was associated with Indus program right from my beginning when I joined, and I have seen among those who have seen the full journey right from scratch when nothing was there to today's date when Indus is operating successfully around the clock mode. But I would like to say that everything was done. Means this was possible only because of my team members. I have been associated with the beam diagnostic system for most of the part of my career. और वहाँ पर मेरी जो टीम है, whatever gradations or the improvements in beam diagnostics we could achieve is all because of my team that who have worked on this. Similarly, the success of Indus machine is also due to its designers, developers, and now the team which operates the machine. So I thank all of them, without whom this was not possible. Once again, I thank again to all for this honor and your kind words. Thank you.
Thank you, sir. And now we are closing the function, but before we close the function, I just request everyone to raise and clap for Sri Puntambekar ji for his. Thank you, everyone.
सभी को धन्यवाद.
ये सर ये छोड़ देता है. हाँ ये सर. Okay. ये सर गाड़ी में नहीं सर मैं तो फिर जाऊंगा. नहीं तो अभी आप सुबह